Hi there. I'd like to tell you a few things about using and navigating this video. Though if you're in a rush, you can look at the video chapters and skip around as you please. This video consists of 55 fully solved AP Calc AB and BC free response questions. Each solution has been checked with the College Board scoring guidelines to ensure that they would all earn full marks. The problems have been sorted by topic, and within each topic have been sorted by year. Naturally, each free response question meaningfully deals with multiple topics in the AP Calculus curriculum. So in the pinned comment, you can find timestamps just like the video chapters, but with a little bit more detail to better help you in finding questions relevant to your needs. That pinned comment will also contain notes and corrections regarding any errors found in the video after its release, though there should not be any meaningful errors because I have watched the entire video to check. Each topic is also preceded by a brief intermission where I'll try to give you some helpful advice for the upcoming section. There's a link in the description to download a free PDF that contains all problems we've solved in this video in their proper order. If you're looking for more general calculus content, there are links in the description to my Calculus 1 course and Calculus 1 exercises playlists, which together contain hundreds of additional videos. If you have any questions about the solutions presented in this video, please don't hesitate to leave a comment, but please do include a timestamp. Lastly, I've spent hundreds of dollars just on hard drive storage while creating this video, so if you find it helpful, I hope you'll consider supporting what I do by joining Wrath of Math as a channel member for access to exclusive and early videos. You can also donate on Patreon or PayPal. There are links in the description, and every bit helps. Good luck studying, good luck on the exam, and thanks for watching. First up is the graph analysis section. I encourage you to be very aware of what graph you're actually looking at. Is it the graph of the most important function in the problem? Or is it the graph of that function's derivative? Or is it the graph of some other function entirely? Also recall that the slope of the graph at any given point is the value of the function's derivative at that point, and that the area underneath the curve in the graph is the value of an integral. This is problem 5 from the 2010 AP Calc AB exam. This was part of the no calculator section. We got a nice picture here. Let's take a look at what the question is. The function g is defined and differentiable on the closed interval from -7 to 5 and satisfies g of 0 equals 5. The graph of g prime of x, the derivative of g, consists of a semicircle and 3 line segments, as we can see here. So make sure you notice this is the graph of g prime, not the graph of g. Part A is to find g of 3 and g of -2. Let's start off with g of 3. This is pretty simple to find if you remember how integrals and derivatives work. We have a given value of g, which is g of 0. We know g of 0 is 5, so we can find g of 3 if we take 5 and then add the sum of the change of g from 0 to 3. By that, I mean we have to add the integral of g prime of x dx from 0, because it's at 0, that we know g is 5, and that's our only known value, so we have to start there. And then we accumulate these changes, these g primes, up to 3, the desired value. If this isn't clear at a glance, you might be more comfortable noticing that the integral of g prime of x from 0 to 3, just this part here, is clearly going to be g of 3. We're undoing the derivative because of the integral, and then plugging in the upper bound, so g of 3, minus g of 0, right? And then, well, g of 0 we know is 5, so if we have this addition of 5 on the left, that's going to cancel out with the g of 0, and all that's going to be left is g of 3. Clearly the equation is true then. G of 3 equals g of 3, exactly what we want. Now let's go ahead with evaluating this. We're going to have 5 plus this integral. Now to evaluate this integral, we can look at the given graph of the derivative. The integral of the derivative gives us the area under the derivative. So we can calculate this integral by calculating some areas. In particular, we need the area under the curve, the area under the derivative, from x equals 0 up to x equals 3, which is right there. So we need all of this shaded area. And we can see that this shaded area is made up of a quarter circle, half a semicircle, and this right triangle. The area of this quarter circle is 1/4 the area of the whole circle. The area of a whole circle is pi r squared, and r, the radius, in this case is 2. So this is going to be pi times 2 squared, or pi times 4, but we only want the area of a quarter of this circle, so we have to multiply it by a fourth. So that's this area here. Now we just need the area of this right triangle. That, of course, is 1/2 base times height. The base from here to here is just 1, and the height we see is 3, because that's the y-coordinate of that upper point. So the base of 1 and the height of 3. And then we just have to simplify this. 5 is the same as 10 halves. I'm writing it in terms of halves because here at the end we have 3 halves. So let's add 3 halves over there. And then the pi term will leave at the end. 1/4 pi times 4 is just a whole pi because the fourth and the 4 cancel out. Finally, 10 halves plus 3 halves is 13 halves. So our final answer is 13 halves plus pi. Again, we start at the known value. We know that g of 0 is 5, and then we have to accumulate g's changes by integrating its derivative from 0, where we started, to 3. If we do that, we get g of 3. It's 13 halves plus pi. We're not done with a yet, though, because we also have to find g of -2. We find g of -2 in the same way. Take the point we already know, 5, right? G of 0 is 5. And then we need to accumulate backwards to -2. So this is the integral from 0, where we are starting, to -2. We're adding up those rates of change. So we're integrating g prime of x with respect to x. This is just going to be 5, and then the integral of g prime again is the area under the curve. But because we're going backwards from 0 to -2, which I'll shade in blue, that's this area here, from 0 to x equals -2. Because we're going backwards, we're just going to have to hit this area with a negative sign. This area we can see is again just the area of the same sort of quarter circle. We already calculated that area as pi, so this is just -pi. Again, it's negative because we're going backwards from 0 to -2. So this is going to be 5 plus -pi. Basically, what's happening is that we're starting at g of 0, which we know to be 5, and then by integrating backwards, we're undoing the change that occurred from -2 to 0, and thus that gives us g of -2, which we find is just 5 minus pi. And now we can move on to part B. Find the x-coordinate of each point of inflection of the graph of y equals g of x on the interval from -7 to 5, and explain our reasoning. In order to find the points of inflection of g of x, we're going to have to look at the graph of the derivative. A point of inflection is where the derivative goes from increasing to decreasing, or decreasing to increasing. So, by looking at the graph, we can see that those occur at x equals 0, 2, and 3. At x equals 0, the derivative goes from increasing to decreasing. At x equals 2, the derivative goes from decreasing to increasing. And at x equals 3, the derivative goes from increasing to decreasing. If we look at another point like x equals -2, the derivative is increasing on both sides of -2. So that would not be a point of inflection, just for a counterexample. And there it is written out. Again, we find the points of inflection by looking at where the derivative switches from decreasing to increasing, or from increasing to decreasing. So those are our points of inflection at x equals 0, 2, and 3. Moving on then to part C. The function h is defined by h of x equals g of x minus a half x squared. We want to find the x-coordinate of each critical point of h, where x is between -7 and 5, and classify each critical point as the location of a relative minimum, relative maximum, or neither, and explain our reasoning. Let's begin by taking the derivative of h so that we can find the critical point. Since h of x equals g of x minus a half x squared, h prime, the derivative, is going to be g prime of x, and then apply the power rule for this part. That's going to be minus x. Okay, g prime of x minus x. Let's write that down here for part C. H prime of x is g prime of x minus x. Now, to find critical points, we need to see where this derivative either doesn't exist or where it's equal to 0. We're only interested in the interval between -7 and 5, and we were told that g is differentiable on that entire interval. And of course, there's no problem subtracting x on that interval either. So there's nowhere on the interval where the derivative doesn't exist. So the only critical points are going to be where this derivative is equal to 0. Now, if this equals 0, g prime of x minus x equals 0, then of course we have that g prime of x would equal x. So where does that occur? It may help to think about this geometrically. G prime of x equals x wherever the derivative, g prime, intersects the line y equals x. So let's come back to our graph of g prime and graph the line y equals x. The line y equals x passes through 0, 0. It passes through 1, 1. It passes through 3, 3. So the line should look something like this. The points we're looking for are where this derivative, the graph in black, intersects this line, y equals x. That would be where g prime of x equals x. We can see clearly this occurs at the point 3, 3. That's a point where g prime of x equals x because they're both 3. And it also appears to occur at one point on this semicircle and nowhere else. Now, to figure out exactly where it occurs on this semicircle, it will help to write an equation for it. So you have to know how to write the equation of a circle centered at the origin with a radius of 2. The equation of a circle centered at the origin with radius 2 is right here. We're only interested in the semicircle that's above the x-axis. We can find that by just solving for y, and that's going to be the square root of 4 minus x squared. So the derivative, g prime of x, between x being -2 and 2, the derivative is this, the square root of 4 minus x squared. That's an equation for this semicircle here. Again, this is between x being -2 and +2. Now, with this equation, we can figure out at exactly what x-coordinate it intersects the line y equals x. So we'll just write x equals the square root of 4 minus x squared and solve this. To do that, we'll square both sides. So x squared equals 4 minus x squared. Add x squared to both sides. So 2x squared equals 4. Divide both sides by 2, so x squared equals 2. And then we find that x equals the square root of 2. It's not the case that x equals -√2, even though that would satisfy this equation. We can see just from our picture that the point we're looking for has a positive x-coordinate. Thus, where does g prime of x equal x? Where are these critical points? That would be at x equals 3, and as we just found, x equals √2. Now, we just have to classify these critical points. In order to classify the critical points, we need to think about the behavior of this derivative around these critical points. If the derivative switches from positive to negative, for example, that means that the function h switches from increasing to decreasing, and a point like that would be a maximum. So let's take a look back at our picture and focus on these critical points, x equals √2 and x equals 3. If we look at x equals √2, we can see that to the left of this, so over here, to the left of this, the derivative g prime is greater than x, right? It is the upper function. So if we were to look at g prime of x minus x, which is h prime, right? H prime is g prime minus x. Clearly, to the left of root 2, that's going to be positive because g prime, we see, is bigger than x. Okay, so it's positive there. Now, what about to the right? Well, to the right of root 2, x is above g prime. So to the right of root 2, it's negative, and it stays that way. Afterwards, we see that y equals x remains above g prime. So at root 2, the derivative h prime switches from positive, because this is bigger than this, to negative, because now this g prime is smaller than this. And here that reasoning is written out. We could clearly see that between 0 and root 2, g prime of x is greater than x, and thus h prime of x is positive. On the other hand, between root 2 and 5, we found that h prime of x is less than or equal to 0. It is non-positive because g prime of x was less than or equal to x. We see g prime is underneath y equals x. Okay, so at root 2, it switches from positive to non-positive. Thus, h has a relative maximum at x equals root 2. It's positive derivative, so it's increasing, and then it's either staying the same or decreasing based on our evidence. And neither a minimum nor a maximum at x equals 3. That's because at x equals 3, that's in this interval, and we see that the derivative doesn't switch sign in that interval. Throughout that entire interval, which contains x equals 3, the derivative h prime is less than or equal to 0, so there's no switching of signs. In fact, the only time the derivative is 0 on this interval from root 2 to 5 is at that critical point, x equals 3. Everywhere else in this interval, h prime is negative, so certainly that would not be x equals 3, the location of a min or a max. And that completes our solution to free response question 5 from the 2010 AP Calc AB exam. This is free response question 3 from the 2016 AP Calc AB exam. No graphing calculator allowed. We're not going to need one. Let's take a look at the problem. The figure above shows the graph of the piecewise linear function f. So each separate piece here is a line. For x between -4 and 12, the function g is defined as an integral of the function f from t to x. Part A asks, does g have a relative minimum, a relative maximum, or neither at x equals 10, and we need to justify our answer. In order to determine if there is a relative minimum or a relative maximum here at x equals 10, remember we're talking about the function g, so we need to consider g's derivative. And since g is defined as the integral of f of x, the derivative of g is actually just f of x. And so what we have here is a graph of the derivative of g. So this is a lot of information. So here for part A, we know that g prime of x is actually f of x, because g is defined as an integral of f of t. So when we look at this graph, we're looking at g prime, and we're asking, does it have a minimum or a maximum or neither here at x equals 10? Well, for it to have a minimum or a maximum, g's derivative would have to go from positive to negative, meaning it's increasing and then decreasing, or it would have to go from negative to positive, meaning it's decreasing and then increasing. And if we look at x equals 10 here on this graph, the function just is negative the whole time. It doesn't switch signs. And again, this is the derivative of g because it's f of x. And so, in fact, g does not have an extreme value at x equals 10 because its derivative, which is what we have a graph of, does not change sign at x equals 10. And there is our answer written out. The function g has neither a min nor a max at x equals 10 because the derivative of g, which is f of x, is less than or equal to 0 between here and here. So when it passes 10, it doesn't switch signs. It's just negative that whole time. So no minimum, no maximum. On to part B. Does the graph of g have a point of inflection at x equals 4? And we need to justify our answer. A point of inflection occurs when the second derivative switches sign, which means the first derivative would have to switch from increasing to decreasing, or from decreasing to increasing. Now we have a graph of the derivative here, so let's look at x equals 4. That's right here. Does the derivative switch from increasing to decreasing or vice versa? Yes, it does. Because this graph is the derivative, we see that it's increasing here, and then right at x equals 4, it switches to decreasing. So in fact, there is a point of inflection in the graph of g at x equals 4. There's our solution. The function g does have a point of inflection at x equals 4 because g prime of x is f of x, and we see that f of x switches from increasing to decreasing at x equals 4. So yes, there is a point of inflection. On to part C. Part C asks us to find the absolute minimum value and the absolute maximum value of g on the interval from -4 to 12 and to justify our answers. Now, to find the absolute max and min, we want to make sure we check all candidates. So let's first note where the relative mins and maxes are. That would be where the derivative switches sign, and we see that happens at x equals -2, it switches sign. At x equals +6, it switches sign, and that's it. But we also have to check the endpoints on this interval, -4 and 12. So we'll check the value of g at all of these candidates, the endpoints, and where the derivative switches sign, and we'll see where the max and where the min occur. Here is a table to organize our information for part C. We need to check the value of g at these 4 candidates, beginning with x equals -4. By definition, g of -4 is the integral from +2 to -4 of f of t dt. So this is the area underneath the curve from 2 to -4, which looks roughly like that. Now this is moving in a backwards direction from 2 to -4. So what we'll do is just throw a negative in front, and then we can calculate this as if we're moving in a positive direction from -4 to +2. First, going from -4 to -2, we need the area of that triangle there, which is 1/2 multiplied by the base of 2 multiplied by the height of -4. And then we have to add the area of this triangle from -2 to +2. That's going to be 1/2 multiplied by the base, which is 4, multiplied by the height, which is 4. And then just do the arithmetic. This is going to be -4. So g of -4 is -4. Let's move on then to g of -2. By definition, g of -2 is going to be the area under f from +2 to -2. So we just need to find the area of that triangle and then multiply it by -1 because again, we're moving in a backwards direction. All right, so that's just going to be 1/2 multiplied by the base. The base is -4 because we're going from the positive to the negative, so -4, and then multiply by the height, which is 4. Like I said, we need to multiply the area of the triangle by -1, which is what we're doing right there. We're treating that base as a negative. All right, so this turns out to be then -8. So g of -2 is -8. Now g of 6, if we look at the picture, that's pretty easy. G of 6 is just going to be the area underneath the curve from 2 to 6, which is just the area of that triangle there, which is just 1/2 multiplied by the base of 4, multiplied by the height of 4, and that is equal to 8. So g of 6 is 8. Lastly, we have to evaluate g of 12, which is going to be the area underneath the curve from +2 all the way up to +12. So it will look something like that. Now, these two triangles are actually just going to cancel out, so we can just focus on this area here between 10 and 12. That's going to be 1/2 multiplied by the base of 2 multiplied by the height of -4, and so this turns out to be -4. So g of 12 is -4. Thus, by looking at the table, we checked all the possible candidates. We can see that the absolute maximum is 8, which occurs at x equals 6. So the absolute max is 8, which occurs at x equals 6. And the absolute minimum on this interval occurs at -2, where we have a minimum of -8. Absolute minimum is -8 at x equals -2. Finally, part D. For x between -4 and 12, so this whole interval, we want to find all intervals for which g of x is less than or equal to 0. Now remember, g of x is the area under the curve, but starting at 2. So for example, this area of the triangle appears that it should be positive because it's above the x-axis. However, because we're moving in this direction in the negative way, because we're starting at 2, so we're moving in the negative direction, this positive area is actually negative. So all of this space is a place where g of x would be negative. Now, some of that negative area would start to get canceled out because this area that actually looks negative is going to be counted as positive because we're moving in the backwards direction. However, even though this cancels out some of this, it doesn't cancel out all of it. So all the way from +2 to -4, g is going to be negative that whole time. We can think through a similar thing going the other direction. Starting at 2, if we go this way, g is positive this whole time because the area is above the x-axis and we're moving in the positive direction. But that positive area gets exactly canceled out by this rectangle here. So by the time we get to x equals 10, g is 0. And then afterwards, it's going to be negative because this area here will be negative and we're traversing it in the positive direction. So in total, g is going to be negative from 2 all the way over to -4, and it's going to be negative from 10 to 12. So for part D, we can say that g of x is less than or equal to 0. Is that what the question asked? Yes, less than or equal to 0. G of x is less than or equal to 0 when x is, like we said, between 2 and -4. So we'll say when x is less than or equal to +2, greater than or equal to -4. And it is also less than or equal to 0 when x is greater than or equal to 10 and less than or equal to 12. So we'll say it's also less than or equal to 0 when x is greater than or equal to 10 and less than or equal to 12. And there's one more look at our solution. That completes free response question 3 from the 2016 AP Calc AB exam. This is free response question 6 from the 2017 AP Calc AB exam. This is part of the no calculator section, and there's quite a bit going on here. It says, let f be the function defined by f of x equals cosine of 2x plus e to the sine x. Let g be a differentiable function, and we have a table right here giving values of g and its derivative g prime at a few values of x. Finally, let h be the function whose graph, consisting of 5 line segments, is shown in this figure here. So we have one function given algebraically, one function in a table, and one function in a graph. Part A. Find the slope of the line tangent to the graph of f at x equals pi. To find the slope of a tangent line, we just need to take the derivative, so we'll find f prime, and then we'll plug in x equals pi. So here for part A, the slope m of the tangent line is f prime, the derivative of our function, evaluated at pi, right? We're looking for the slope of the tangent line at x equals pi. So let's take the derivative of f and plug in pi. The derivative of cosine 2x is negative sine of 2x, but by the chain rule, we also have to multiply by the derivative of the inside function. The derivative of 2x is 2, so we multiply by 2 out front. So negative 2 sine of 2x, that's the derivative of cosine of 2x. We also have to add the derivative of e to the sine x. The derivative of e to the power of a function is just e to the power of that function multiplied by that function's derivative. The derivative of sine x is cosine x. So this is our derivative, f prime, but we want to evaluate it at pi. So let's go ahead and replace these x's with pi's, which of course is going to work very nicely with these trig functions. All right, after plugging in pi's, what do we get? Well, sine of 2 pi is 0, so this whole term goes away. Sine of pi up here is also 0, so this is e to the power of 0, which is 1. So all that's left is cosine pi, and surely you can remember your unit circle. Cosine pi is over there, where the x-coordinate is negative 1. So that's just going to be then negative 1. That is the slope of the tangent line at x equals pi, the tangent to this function f. All right, part B. Let k be the function defined by k of x equals h of f of x. F of x is the function we were just working with. H, remember, is the function shown in this graph. The question is to find k prime of pi. So let's go ahead and write part B here. We are looking for k prime of pi. So let's just find k prime of x, and then we'll plug pi in for x. K is a composite function. It's h of f of x. So to find the derivative, k prime, we need to use the chain rule. The chain rule begins with the derivative of the outside function. The outside function is h, so that's h prime of, leave the inside function unchanged. Then you just have to multiply by the derivative of the inside function. In this case, that's f prime of x. All right, but we, of course, want to evaluate this derivative at pi. So k prime of pi is going to be h prime of f of pi multiplied by f prime of pi. But we just evaluated f prime of pi in part A. We know that's negative 1. So let's just replace f prime of pi with negative 1. All right, now let's see, what is f of pi? Well, looking up at our function, what f of x actually is, we can see that f of pi would be cosine of 2 pi plus e to the sine pi. Now, cosine of 2 pi is the same as cosine of 0, which is 1, and e to the sine pi is e to the 0, which is also 1. So this is 1 plus 1, or 2. So we can rewrite this as h prime of f of pi is 2, so this is h prime of 2, multiplied by negative 1, so we'll still put that negative 1 there. Now what is h prime of 2? Well, we'll have to look at our graph to figure that out. Since we want to know the derivative of h at 2, we're looking right here. So here's x equals 2, and we're focusing on this line segment. The derivative of h is the slope of h, which is easy to figure out when h just behaves like a line. What is the slope of this line? Well, we see that when it goes down 1, it goes over 1, 2, 3. Rise over run, so the slope is negative 1/3, down 1 over 3. Okay, so h prime of 2, the slope of the function h at x equals 2 is just the slope of this line, which is negative 1/3. So this is negative 1, which I'll move to the front, negative 1 times negative 1/3, which of course is just positive 1/3. All right, let's move on to part C. Let m be the function defined by m of x equals g of negative 2x times h of x. We want to find m prime of 2. So this is a lot like the previous questions, except now we're getting the g function involved, which is in this table, and we're going to have to use the product rule because, of course, we're now dealing with a product of functions. We're dealing with g times h. So let's put problem C down here, and we're trying to evaluate m prime of 2. Let's begin by just finding what m prime of x is, and then we'll plug in x equals 2. We, of course, need to use the product rule. u prime v plus v prime u. So looking at this product, let's start off with the derivative of g. The derivative of g with that negative 2x inside of it is going to be g prime of negative 2x and then multiply by the derivative of the inside function. The derivative of negative 2x is negative 2. So that would be the u prime in the product rule. U prime v, so we also have to multiply by the second function here, h of x. U prime v plus v prime u. V prime is the derivative of the second function, so h prime of x, times the first function unchanged, g of negative 2x. All right, that's m prime of x, and now we just need to plug in x equals 2. What is m prime of 2? Well, it's going to be negative 2 multiplied by g prime of negative 4, because that's negative 2 times 2, multiplied by h of 2, plus h prime of 2, but h prime of 2 we already figured out was negative 1/3. That showed up in the previous problem. H prime of 2 is negative 1/3. So let's just replace that with negative 1/3. Get a little head start there. And then we have g of negative 4. All right, hopefully we can figure out what all of these values are. Let's consult the table for the values of g and g prime. G prime of negative 4 we see is negative 1. And g of negative 4 is positive 5. So we can rewrite this expression. It's going to be negative 2 times g prime of negative 4, which we know is negative 1. So negative 2 times negative 1 multiplied by h of 2 plus negative 1/3 times g of negative 4, which we see is positive 5. So this is times positive 5. Now we can simplify and also figure out what h of 2 is. For starters, we have negative 2 times negative 1, which is just positive 2. And then looking at the graph, what is h of 2? X equals 2 is right there, and so h of 2 is the y value right there. Now, how do we know what the y value here is? Well, we know that this line segment starts at the origin, 0, 0, and we already said that its slope is negative 1/3. So if we move over 2 units, we must go down 2/3. So the y-coordinate is negative 2/3. That is h of 2. So we'll replace that right there. We're replacing that with negative 2/3. And then over here on the right, we have negative 1/3 times 5. So that's minus 5/3. Finally, this is negative 4/3 minus 5/3. So that's negative 9/3, which is just negative 3. That completes part C. So let's finish with part D. Is there a number c in the closed interval from negative 5 to negative 3 such that g prime of c is equal to negative 4, and justify our answer? For this, part D, we must use the mean value theorem. We know that g is differentiable, and thus it's also continuous on the closed interval between negative 5 and negative 3. We are told as much. G is a differentiable function, and we have some values of g and its derivative. That's what's going to let us use the mean value theorem. Since g is differentiable and continuous from negative 5 to negative 3, the mean value theorem tells us whatever g's average rate of change over this interval is, there must be some point in the interval where its instantaneous rate of change, its derivative, equals the average rate of change. So let's calculate g's average rate of change from x equals negative 5 to x equals negative 3. To do this, we'll set up a fraction. The calculation is as follows. G of negative 3, the ending value, minus the starting value, g of negative 5. This tells us how much g changed over the interval. And then we have to divide by the interval width, which is just the endpoint, negative 3, minus the beginning point, negative 5. All right, so this is how much the function changed divided by the interval width. G of negative 3, we see from the table, is positive 2, and g of negative 5 is positive 10. So this is 2 minus 10, and then the denominator, negative 3 minus negative 5, is negative 3 plus 5, which is just 2. We see then that this is 2 minus 10, which is negative 8, divided by positive 2, So this is -4. Since the average rate of change over the interval is -4, we know by the mean value theorem that yes, there does have to be some point C in this interval such that the derivative of g at this point C is -4. The instantaneous rate of change has to equal the average rate of change at some point on this interval. And there is that conclusion written out. And that completes our solution to free response question 6 from the 2017 AP Calc AB exam. Next up is the continuity section. For this section, just recall the definition of continuity. It's important you know how to use it. We say that a function is continuous at a point x equals c if the limit of the function as x approaches c from the left equals the limit of the function as x approaches c from the right, and both of those limits equal the function's value. This is free response question 6 from the 2003 AP Calc AB exam. Let f be the function defined by this piecewise expression. F of x equals the square root of x plus 1 for x values between 0 and 3, inclusive, and for x greater than 3, but less than or equal to 5, f of x equals 5 minus x. Part A asks, is f continuous at x equals 3? Explain why or why not. By definition of continuity, in order for f of x to be continuous at x equals 3, the limit of f of x from the left must equal the limit of f of x from the right, and they both must equal the function's value at x equals 3. Let's begin by evaluating the limit of f of x as x approaches 3 from the left. As x approaches 3 from the left, the behavior of f of x is this, the square root of x plus 1, because x approaching 3 from the left means that x is less than 3. Now, the square root of x plus 1 is continuous at x equals 3, so to evaluate this limit, we can just plug in x equals 3. So the limit of f of x as x approaches 3 from the left, this is the limit as x approaches 3 from the left of the square root of x plus 1, which is just the square root of 3 plus 1, which is the square root of 4, which is, of course, 2. It's also worth pointing out that this is the function's actual value at 3, because this is the function's behavior when x is less than or equal to 3. From the left, the function's limit is 2, which is also the function's value at 3. Now we just have to check the limit of the function as x approaches 3 from the right. When x approaches 3 from the right, x is greater than 3, and so the behavior of the function is 5 minus x. Clearly then, the limit of the function as x approaches 3 from the right is 5 minus 3, which is 2. So yes, indeed, this is a continuous function at x equals 3, because as x approaches 3 from the left, the function approaches 2. The function's actual value at 3 is 2, and the limit of the function as x approaches 3 from the right is 2. So yes, it is continuous. Therefore, I'll use the 3 dots for therefore. F of x is continuous at x equals 3. Moving on to part B. Find the average value of f of x on the closed interval from 0 to 5. To find the average value of a function over an interval, we just accumulate the function over that interval, which means we integrate it, and then divide by the interval length. It's like adding up the values in a data set and then dividing by the number of values. So what we need to do is integrate our function f of x on the closed interval from 0 to 5, so we integrate from 0 to 5, and then divide by the interval length, so divide by 5. Dividing by 5 is the same as multiplying by 1 over 5, so we'll write it like that. Now, the only thing that makes the integral a little bit tricky is that we have to split it up, because the function's behavior changes at x equals 3. So our first integral will go from 0 to 3. From 0 to 3, the behavior of the function is the square root of x plus 1. And then we will have to add separately the integral from 3 to 5. From 3 to 5, the behavior of the function is 5 minus x. Now we just have to proceed with this integral. So we have the 1/5 out front. Now beginning with the integral of the square root of x plus 1. The square root of x plus 1 is the same as x plus 1 to the 1/2. We're just using the power rule to integrate this. So add 1 to the power, bringing the power of 1/2 up to a power of 3/2, and then divide by the new power, which means we multiply by its reciprocal. And we'll have to evaluate that from 0 to 3. And then we have this other integral, the integral of 5 minus x. That's just going to be 5x minus 1/2 x squared. Again, we're just using the power rule, and we are evaluating that from 3 to 5. All right, so let's begin to evaluate this. We have 1/5 out front, and then plugging 3 into this expression gives 2/3 multiplied by 4 to the 3/2. 4 to the 3/2 you can think about as applying the square root first, so the square root of 4, which is 2, and then cubing it, which is 8. So 2/3 times 8, so 16/3. And then if we plug in 0, we are just going to get 2/3. So 16/3 minus 2/3. Then we have our other integral. Plugging 5 into this expression is going to give us 25 minus 25 over 2. And that is just 25 over 2. So we will just write 25 over 2, right? If you have 25 and you take away half of 25, you get half of 25. And then if we plug in 3, we will get 15 minus 9 over 2. 15 minus 9 over 2. 15 is the same as 30 over 2. So this is 30 over 2 minus 9 over 2, which is 21 over 2. And because this resulted from plugging in the lower bound, we need to subtract it. So minus 21 over 2. Now we can finish this up. We still have 1/5 out front. 16/3 minus 2/3 is 14/3. And then 25/2 minus 21/2 is 4/2. So plus 4/2. Now 4 over 2 is the same as 2, and 2 is the same as 6 over 3, so that we have common denominators now. This then is 1/5 multiplied by 20 over 3, and then we can cancel a factor of 5 out of the numerator and denominator, giving us a final answer of 4/3. And that's the average value of the function over the closed interval from 0 to 5. Moving on to part C. Suppose the function g is defined by, and here we have a piecewise function similar to f of x, but a little bit different, and k and m here are constants. We're told that g is differentiable at x equals 3, so using that information, we must find the values of k and m. Now, since g is differentiable at x equals 3, firstly, we know that means that g is continuous at x equals 3. So the limit from the left must equal the limit from the right, which means these two expressions have to equal each other at x equals 3. But also, g is differentiable at x equals 3, so if we take the derivative of the top and the bottom, those derivatives must equal each other at x equals 3. There can't be a sudden change in the slopes at x equals 3 since g is differentiable. So let's put all this stuff into equations and get to solving. Beginning with continuity. Like we said, since g is differentiable at x equals 3, that implies g must be continuous at x equals 3. So the limit from the left must equal the limit from the right. Now the limit from the left is found by looking at this expression, and the limit from the right concerns that expression. So let's plug in x equals 3 to both of these expressions and set them equal to each other. The first one becomes k multiplied by the square root of 3 plus 1. So k multiplied by the square root of 4, which is just 2k. And because g is continuous here, it must equal this guy with x equals 3 plugged in, which is just 3m plus 2. We will use this equation, but before we do, let's go back to differentiability. Not only must the limit of g of x as x approaches 3 from the left equal the limit of g of x as x approaches 3 from the right, but this must also be true about the derivatives g prime because g is differentiable at x equals 3. So let's take the derivative and see what equation that gets us. Taking the derivative of this part of g produces k over 2 multiplied by x plus 1 to the negative half. We're just using the power rule, and keep in mind we're differentiating with respect to x, not with respect to k or m. K and m are both constants. The derivative of mx plus 2, of course, is just m. So at x equals 3, it must be the case that these two things are equal. Now, plugging in x equals 3 makes x plus 1 become 3 plus 1, which is just 4. K over 2 times 4 to the negative 1/2 is k over 2 times the square root of 4. And so that's just 2 times 2, so k over 4. Because, of course, 4 to the negative 1/2, that's just 1 over 4 in a square root. So that's why you have that root 4 in the denominator. So m equals k over 4 because g is differentiable at x equals 3. Now we can plug that equation into this one, which resulted from continuity, and then we'll be able to solve for everything. So we have that 2k is equal to 3 times m, but in terms of k, that's 3k over 4, and then plus 2. Then we can subtract 3/4 k from both sides. 2k is 8/4 k, so in total we have 5/4 k equals 2. Multiply both sides by 4 over 5, and we get that k equals 8/5. Plugging this into our equation for m gives us that m equals 8 over 20, which is the same as 2 over 5, and so that's our value for k, that's our value for m. And that completes our solution to free response question 6 from the 2003 AP Calc AB exam. This is free response question 2 from the 2011 AP Calc AB Form B exam. This is part of the graphing calculator section. A 12,000 liter tank of water is filled to capacity. At time t equals 0, water begins to drain out of the tank at a rate modeled by r of t, which is measured in liters per hour, and r is given by this piecewise defined function. So the way in which water is draining out of the tank changes at t equals 5. You can see that sudden change there. Part A asks, is r continuous at t equals 5? And show the work that leads to our answer. In order to determine if r is continuous at t equals 5, we need to see if the limit from the left, which is this behavior, is equal to the limit from the right, which has this behavior. Here these limits are written out. The limit of r of t as t approaches 5 from the left. Based on the definition of r of t is equal to this when t approaches 5 from the left, because when t approaches 5 from the left, t is less than or equal to 5. On the other hand, when t approaches 5 from the right, the behavior of r of t is this, because when t approaches 5 from the right, t is greater than 5. Now we have to evaluate and compare both of these limits. For this one, we can just substitute 5 into the function. 600 times 5 is 3,000, so this is just 3,000 divided by 8. 8 goes into 225 times, which means it goes into 1,125 times, which means it goes into 3,375 times. Now on the bottom, we can also just substitute 5 into this function, and we'll bust out a calculator for that. This is about 367.88 if you plug this into a calculator. So we can see as we approach 5 from the left, we get 375. 375 is also the value of the function at t equals 5. You can see this is t less than or equal to 5. We have that behavior. So this is also r of 5. But that's not equal to the limit of the function as t approaches 5 from the right. As t approaches 5 from the right, the limit is about 367.88. They're not equal, hence r of t is not continuous at t equals 5. Part B says find the average rate at which water is draining from the tank between t equals 0 and t equals 8. The rate at which water is draining from the tank is this piecewise function. So to find the average rate, we just need to integrate this function over the interval in question from 0 to 8 and divide by the interval length, which is 8. So for part B, we need to integrate our function, r of t, that's the rate of change of water in the tank. We need to integrate this from 0 to 8 and then divide it by 8. Dividing it by 8 is the same as multiplying by 1/8. So let's go ahead and do this. This integral, though, because the function is piecewise, we're going to have to split it up at the point where its behavior changes, at t equals 5. So we will write the integral from 0 to 5, and from 0 to 5, that's the behavior of the function, 600t over t plus 3. And then separately, we will add the integral from 5 to 8, and from 5 to 8, the behavior of the function is this, 1000e to the negative 0.2t. And we will consult the graphing calculator for this. I'll save the multiplication by 1/8 for the end. I'm going to press Math, and then option 9, the integration function. We are integrating from 0 to 5 for this first integral. What we're integrating is 600 times t, but it's more convenient to use x on the calculator. So 600x divided by x plus 3, using a lot of parentheses here. This integral, of course, is with respect to x, and then we're adding the second integral. So again, I'll press the math button and option 9 for the integration function. Integrating from 5 to 8, 1000 multiplied by e, let me rewrite that, e to the power of negative 0.2x instead of t. Integrating with respect to x, we get about 2064, and then I'll just divide this by 8. So then our answer is about 258.053. And remember, this is an average rate of change of water, so this is in liters per hour, right? That was the volume and time measurement we're using, so liters per hour. All right, let's move on to part C. Part C says find r prime of 3. Using correct units, explain the meaning of that value in the context of this problem. So we can take the derivative of r at t equals 3. The behavior of r at t equals 3 is given here, so we could take the derivative of that using the quotient rule, but we might as well avoid the trouble and just use the calculator since we can. As far as the interpretation, which we will write out what the meaning of this is the rate of change of the rate at which water is draining out of the tank. Water is draining out of the tank, but not at a constant rate. That rate is changing, and r prime is how much the rate is changing. It's the rate of change of the rate of change. So coming back over to the calculator in order to calculate r prime of 3, again, I'll press the math button and then option 8 for the derivative function. We're taking the derivative with respect to x. We're going to use x here in the calculator. And because t equals 3, we're looking for the derivative at t equals 3. This is the expression we're using. So 600x divided by x plus 3. And we're evaluating this at 3. And we get about 50. And because this is the rate of change of the rate at which water is draining out of the tank, this is liters per hour, so liters per hour squared. And here is our written interpretation of this derivative's value. At time t equals 3 hours, the rate at which water is draining out of the tank, which is r of t, that rate is increasing because the derivative's positive. It's increasing by 50 liters per hour squared. More water is draining out of the tank more quickly. Finally, part D. Write, but do not solve, an equation involving an integral to find the time A when the amount of water in the tank is 9,000 liters. Let's do part D up here, where all the information is conveniently available to us. We know the amount of water in the tank began at 12,000 liters because it said it was filled to capacity. So it must be that 12,000 minus the accumulation of the rate at which water is draining out of the tank, as in the integral of that rate at which water is leaving, from some time zero, or I should say the time zero, the time at which water begins draining, to some time a, that's the unknown, this must equal 9,000, right? If water drains from t equals 0 to this unknown time, a, then eventually there will be 9,000 liters of water left in the tank. And we do not have to solve this, so we are done there. Just explaining this again, the initial amount of water in the tank is 12,000 liters. We subtract the accumulation of the rate at which water is leaving from 0 to the unknown time a, and the time a is some time that satisfies this equation, that if we were moving water for this long, we would have 9,000 liters left. And that completes our solution to free response question 2 from the 2011 AP Calc AB Form B exam. This is free response question 4 from the 2012 AP Calc AB exam. Let's read it. The function f is defined by f of x equals the square root of 25 minus x squared, which you may recognize as the equation of the top half of a circle centered at the origin with radius 5. And x is between negative 5 and 5. Part A is very straightforward. We're just looking for the derivative f prime of x. So let's go ahead and find the derivative of f of x. In order to do that, it may help to rewrite f of x first. Note that a square root is the same as a power of 1/2. So the square root of 25 minus x squared is the same as 25 minus x squared, all to the power of 1/2. And this makes it more clear that to find the derivative, f prime, we'll simply need to use the power rule and the chain rule. We have to use the chain rule, of course, because f of x is a composite function. The outside function is this power of 1/2. How do you take the derivative of something to the 1/2? Well, you have to bring that power of 1/2 down as a factor, leave the inside function unchanged, 25 minus x squared, and then reduce the power by 1. So now the power is negative half. That's just the power rule. But then by the chain rule, because we have a function inside of this, 25 minus x squared, we also need to multiply by the derivative of that function. And the derivative of 25 minus x squared is negative 2x. And this is f prime of x, although there is a little bit of simplification we can do. We can bring the negative to the front, and of course the 1/2 and the 2 cancel out. So there is our answer. F prime of x equals negative x times 25 minus x squared to the negative 1/2. Again, we wrote the negative and the x out front, and the 1/2 and the 2 cancel out. So that's our answer for A. Part B. Write an equation for the line tangent to the graph of f at x equals negative 3. Okay, for a tangent line, we need two things, a point and a slope. For the slope, we will be able to use the derivative that we just found, and the point is even easier than that. The point, we know, has an x-coordinate of negative 3. To find the y-coordinate, we just need to plug negative 3 into our function, because we know the tangent line has to meet the function at x equals negative 3. So plug negative 3 into the function to see what the y-coordinate has to be. Here's our function. Let's plug negative 3 into it. F of negative 3 is going to be the square root of 25 minus negative 3 squared is 9. So this is the square root of 25 minus 9, which is the square root of 16, which is 4. So the point that our line is tangent to is negative 3, 4. That's where our tangent line is intersecting the curve. We can find the slope of the tangent line at this point by plugging negative 3 into the derivative, which we just found. So let's plug negative 3 into this derivative. That's going to be negative 3. Remember, there's that negative out front. And then in parentheses, we have 25 minus negative 3 squared, which is just 9. And this is to the power of negative 1/2. Now what is this? Well, the negative in the front cancel out, so we just have a 3. And let's go ahead and write this as a fraction. This has a negative power, 25 minus 9, so I'm going to give it a positive power by putting it in the denominator. Then we would have this 3 in the numerator, and in the denominator, we would have 25 minus 9 to the 1/2. 25 minus 9, though, is 16, so that would be 16 to the 1/2. But a power of 1/2 is the same as a square root. So this is the same as 3 over the square root of 16. The square root of 16, of course, is just 4. So this is 3 over 4. That is the slope of our tangent line. Then we can use point slope form to write the equation of the tangent line. Y minus the y coordinate, which we found to be 4, equals the slope, which we found to be 3 over 4, multiplied by x minus the x coordinate, which of course is negative 3. But x minus negative 3 is the same as x plus 3, so let's just write it that way because that looks nicer. And that's it for part B. Moving on to part C. Let g be the function defined by g of x equals a piecewise function. It is equal to f of x when x is between negative 5 and negative 3 inclusive, and it's equal to x plus 7 when x is greater than negative 3 and less than or equal to positive 5. The question is g continuous at x equals negative 3, which is where its definition switches. At negative 3, it switches from f of x to x plus 7. So is it continuous there? To answer this, we must use the definition of continuity. The definition of a function being continuous at a point, let's say negative 3 in this case, is that the limit of g of x as x approaches negative 3 from the left should equal the limit of g of x as x approaches negative 3 from the right, and those one-sided limits both have to equal the function's value at negative 3. That's what it would mean for g to be continuous at negative 3. Now, when x approaches negative 3 from the left, g of x behavior is f of x, because x approaching negative 3 from the left means that x is less than negative 3. So the behavior of g of x would just be f of x. Now, what is it approaching then from the left? Well, we can find that by just plugging negative 3 into f of x. We've already done that, and we know that it would equal 4. So the limit of g of x as x approaches negative 3 from the left is 4. Now, what about from the right? If x is approaching negative 3 from the right, then the behavior of g is here, because it is here where x is greater than negative 3, so it can approach negative 3 from the right. The behavior of g of x is that it's x plus 7. So what's the limit from the right? Well, plug in negative 3. Negative 3 plus 7 is positive 4, which was the same as the limit from the left. Finally, if we actually plug negative 3 into the function g, what does it actually equal at negative 3? Well, it is equal to f of negative 3, because remember, it's on this piece of the function where x is allowed to equal negative 3. So g of negative 3 we see is just f of negative 3, which is 4. So yes, it is continuous, and let me write those details out. Here's the argument we just went through. G is continuous at x equals negative 3, and we justify this using the definition. That's how we were asked to do it. We know that the limit of g of x as x approaches negative 3 from the left is the limit as x approaches negative 3 from the left of f of x, because that's g of x's behavior when x is less than negative 3. It behaves like f of x. And this limit we find by just plugging in. It turns out to be 4, which is also the value of g at negative 3. It is 4. Now, if we approach negative 3 from the right, we found that it also equaled 4 when it's behaving like this line, x plus 7. It's also approaching 4 as we go to negative 3 from the right. So the function's value equals the limit from the left equals the limit from the right. Indeed, g is continuous at x equals negative 3. That is part C. So let's go ahead and finish with part D. Find the value of the integral from 0 to 5 of x times 25 minus x squared dx. Of course, you can see f of x is showing up in this integral, which is why this is another part of this problem. All right, I've just copied this integral down. Here is part D. You should notice at a glance that this is a pretty easy u substitution problem. If we let u equal 25 minus x squared, so I'll write that, u equals 25 minus x squared, well then du is just negative 2x dx, which practically matches the remainder of the integrand, x dx, and we can make them match exactly if we multiply both sides of this equation by negative half. If we do that, then on the left we have negative half du, and on the right we just have x dx. So you can see how we'll be able to make that replacement and cleanly write this integral in terms of u. One other thing I'll point out, notice if this x was not here, this x that enables us to use u substitution, then you would have to notice that this is the equation of the top half of a circle, like I mentioned earlier. And then finding the area underneath it is pretty straightforward since its radius is 5 and we're integrating from 0 to 5. So you'd actually be looking for the area of a quarter circle in that case. It'd actually just be a very straightforward geometry problem if you recognize that. But that's not the problem we've got. We've got this x here, so let's proceed with the u substitution. So this is the integral. We can rewrite the bounds so that they are appropriate for u. If x is 0, then u is 25 minus 0 squared, which is just 25. So in terms of u, the lower bound is 25. Now if x is equal to 5, then u is 25 minus 5 squared, which is 0. So the upper bound for u is 0. Now what are we integrating? We're integrating the square root of u, because 25 minus x squared is u, and then the x dx is getting replaced by half du, with of course a negative as well. Let's just bring that negative out front, and you know what? Let's put the negative half out front as a whole, and then we just have the du there. Okay, let's proceed with this integral. This is pretty straightforward. Again, you should recognize that the square root of u is the same as u to the 1/2. So this is a simple reverse power rule integral, you might say. We will have a negative 1/2 out front, and then to do the reverse power rule, we increase the power by 1. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. So u to the 3/2. Then divide by this new power. Dividing by this fractional power is the same as multiplying by its reciprocal, 2/3. And we are evaluating this from the lower bound, 25, to the upper bound of 0. All right, we'll proceed with this. We still have that negative half out front. If we plug the upper bound 0 into this, what we're going to get is 0. And then subtract, plugging in the lower bound. So we're subtracting 2/3 multiplied by 25 to the power of 3/2. Finally, this is negative 1/2. The 0, of course, doesn't matter. 25 to the 3/2 is the square root of 25 cubed. The square root of 25 is 5, and 5 cubed is 125. So what we have in brackets, which I'll just use parentheses now, is negative 2/3 multiplied by 125. Again, we got that by first applying the power of 1/2, which is just a square root. Square root of 25 is 5. And then we apply that power of 3, cubing the 5, to get 125. All right, we're nearly there. The negatives will cancel out. In the numerator, we would have 2 times 125, which is just 250. And in the denominator, we have 2 times 3, which is just 6. Now we just have to reduce this fraction. We can reduce both things by a factor of 2. The numerator divided by 2 is 125, and the denominator divided by 2 is 3. We, of course, could have just canceled the 2's up here to begin with. And hey, look, that's our answer, and that completes our solution to free response question 4 from the 2012 AP Calc AB exam. Next up are a few IVT and MVT problems. For these problems, recall that the intermediate value theorem requires continuity, while the mean value theorem requires continuity and differentiability, although of course, differentiability implies continuity. The intermediate value theorem says how if a function is continuous, it can't pass from a value f of a to a value f of b without also hitting all of the intermediate values. Whereas the mean value theorem says that whatever a function's average rate of change is over an interval, it must be that its derivative is equal to that average rate of change at some point in the interval, of course, provided that the function is differentiable. Good luck. This is free response question 6 from the 2006 AP Calc AB Form B exam. A car travels on a straight track. During the time interval from 0 to 60, where t is measured in seconds, the car's velocity, v, measured in feet per second, and acceleration, a, measured in feet per second, are continuous functions. The table above shows selected values of these functions. You can see time is in the top row, then velocity, then acceleration. Part A says, using appropriate units, explain the meaning of the integral of the absolute value of the velocity function from 30 to 60 in terms of the car's motion. Then approximate this integral using a trapezoidal approximation with 3 subintervals as determined by the table. Let's start with the first part of the question, the meaning of the integral of the absolute value of the velocity function. The absolute value of velocity is speed, and if we integrate speed, we get the total distance traveled. If we were to just integrate velocity, then positive and negative velocities would cancel out. In the end, you would just get the displacement of the vehicle. But since we're integrating the absolute value, which is the speed, we're going to get the total distance traveled. Whether it's negative velocity or positive velocity, it's all counted the same because of the absolute value. So for part A, this integral is the distance in feet that the car travels from t equals 30 to t equals 60. It's not the displacement, it's just the total accumulated distance traveled. Alright, the other part of part A is to actually approximate this integral using a trapezoidal approximation with 3 subintervals as determined by the table. Going from 30 to 60, you can see in the table there's only 3 subintervals that we can use, going from 30 to 35, 35 to 50, and 50 to 60. For a trapezoidal approximation, it may help to do a quick sketch. Let's say that t equals 30 is right there. So our first trapezoid is going to go from 30 to 35. And at 30, the velocity is negative 14, but we are integrating the absolute value of the velocity. So this is actually going to be positive 14. So maybe positive 14 is right there, and this is going up to that. And then at 35, the velocity is negative 10, but again, we've got absolute value, so that's getting changed to positive 10, and maybe that's about that high. And so there is our first trapezoid. Now the next trapezoid, which I guess I'll do in a different color, goes from 35 to 50. So maybe over here is 50. Equal spacing here doesn't really matter. We're just doing a quick sketch so that it's clear how we're going to calculate the area. The velocity at 50 is 0. So in fact, our second trapezoid is actually just a triangle. And then lastly, we go from 50 to 60. The velocity at 60 is 10. And so that's going right back up here to 10. And that gives us that triangle there. And I should label this is at t equals 60. So to approximate this integral from 30 to 60, the integral of the absolute value of the velocity function, approximating this using a trapezoidal sum, let's see, what are the areas? First, we have the area of this trapezoid, which is the average of the bases, 1/2 multiplied by this side plus that side. The length of this side, which is a base of the trapezoid, is 14, plus the length of this side, which is the other base of the trapezoid, which was 10. So 1/2 the sum of the bases multiplied by the height. The height of the trapezoid is this distance here, which is 5. So that's the first area. We can just go ahead and cut and paste that down here to our answer. And now let's move on to these two triangles. The area of this triangle is 1/2 times its base, which is 15, multiplied by its height, which is just this distance here, which is 10. And then the second triangle right here has an area of 1/2 times the base, which is 10, multiplied by the height, which is also 10. So we just need to add all of these areas together to get our approximation. Doing the math here, 14 plus 10 is 24, times 1/2 is 12, times 5 is 60. And then 1/2 times 15 times 10 is 75. And then finally, 1/2 times 10 times 10 is 50. So the approximation is 185. And the unit, because this is just distance traveled in feet, this is 185 feet. All right, let's go ahead and just shrink this approximation down so we have a little bit more room to work with and move on to part B. Using appropriate units, explain the meaning of the integral of acceleration from 0 to 30 in terms of the car's motion and find the exact value of this integral. Now, acceleration is change in velocity. If you accumulate or integrate change in something, you get the net change in that thing. So if we accumulate these changes in velocity, we just get the net change in velocity. Now, acceleration is the rate of change of velocity, and if we accumulate or integrate a rate of change, what we get is net change. So this integral is just the change in velocity of the car from t equals 0 to t equals 30. And there that answer is written out. This integral is the car's change in velocity. We want to make sure we use units, that's velocity in feet per second, from t equals 0 to t equals 30. All right, the other part of the question was asking for the exact value of this integral. Now, we can just use the fundamental theorem of calculus here. The integral of acceleration from 0 to 30 is just going to be the velocity evaluated at 30 minus the velocity evaluated at 0, because velocity is the antiderivative of acceleration. All right, and now we can just refer to the table. V of 30 is negative 14. V of 0 is negative 20. So negative 14 minus negative 20, that's negative 14 plus 20, which is 6. And our units are feet per second. So the change in velocity was 6 feet per second from t equals 0 to t equals 30. On to part C. For t between 0 and 60, must there be a time t when the velocity is equal to negative 5? And of course, justify our answer. So this is an intermediate value theorem problem. Must there be a place on this interval where the velocity is equal to negative 5? Well, the velocity, as we're told, is a continuous function, and the velocity does pass negative 5 at some point. It has to, because we see right here from 35 to 50, the velocity goes from negative 10 to 0. So yes, it must have passed negative 5 at some point. So this is our answer for part C, because v of 35, which is negative 10, is less than negative 5, which is less than 0, which is v of 50. Negative 5 is between the velocity at 35 and the velocity at 50, and the velocity is continuous. So by the intermediate value theorem, there must be some value of t in this interval between 35 and 50, which is also in the interval between 0 and 60, such that the velocity is equal to negative 5. Moving on to part D. For t between 0 and 60, must there be a time t when the acceleration equals 0, and justify our answer? We could use the intermediate value theorem here on the acceleration function, or we could use the mean value theorem on the velocity function. If we come up to the table, we do not see the acceleration function ever pass 0. We never see it go from positive to negative, but we only have a selection of the values. So just because the table of acceleration values doesn't make it clear that it hit 0, doesn't mean that it never hit 0. Let's consider using the mean value theorem applied to the velocity function. Is there any interval over which the average rate of change of the velocity is 0? The answer is yes, because we see at t equals 0, the velocity is negative 20, and at t equals 25, the velocity is also negative 20. Over this interval, the average rate of change of the velocity was 0, because it went from negative 20 to negative 20. And since that's the case, there must have been some point where the instantaneous rate of change of the velocity, thus the acceleration, was 0. That's the mean value theorem. There's our answer for part D. Because v of 0 equals v of 25, they were both negative 20, the average rate of change is 0 over that interval, and so the mean value theorem guarantees a t in that interval from 0 to 25, so that the derivative of the velocity function, the instantaneous rate of change, which is the acceleration, is equal to 0. I'll also point out that according to the College Board scoring guidelines for this question, you could mention the hypotheses of these theorems, or you could mention the theorems. You don't have to do both. I could say, by the mean value theorem, all of this is true, or I could say, because the functions are continuous and differentiable on the interval, all of this stuff is true. That completes our solution to free response question 6 from the 2006 AP Calc AB Form B exam. This is free response question 1 from the 2011 AP Calc AB exam. This is part of the graphing calculator section. We will use a calculator throughout this problem. A cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. The can is initially empty, and rain enters the can during a 60-day period. The height of water in the can is modeled by the function s, where s of t is measured in millimeters, and t is measured in days from 0 to 60. The rate at which the height of the water is rising in the can is given by s prime of t equals 2 sine of 0.03t plus 1.5. All right, part A. According to the model, what is the height of the water in the can at the end of the 60-day period? We know the can was initially empty, so at the start, the 0th day, t equals 0, the height of water in the can is 0. Then all we have to do is accumulate the rate of change of the height of the water in the can, so integrate s prime, from 0 to 60. That's just like accumulating all of the rainfall. So the answer to our question, s of 60, the height of the water in the can on the end of the 60th day, is going to be the integral from 0 to 60 of s prime. S prime, of course, is 2 multiplied by sine of 0.03t, and plus 1.5. And we are integrating with respect to t, and we'll just go ahead and calculate this on a calculator. On the calculator, I'll press the math button, and then option 9 to access the integration function. We are integrating from 0 to 60. The function we're integrating is 2 sine of 0.03t, but we'll use the variable x on the calculator, plus 1.5. And we're integrating with respect to x, and it's about 171.81 millimeters. All right, on to part B. Part B says, according to the model, what is the average rate of change in the height of water in the can over the 60-day period? And show the computations that lead to our answer and indicate the units of measure. Now, we are given the function for the rate of change in the height of the water at any moment, that is s prime of t. So to find the average rate of change in the height of water in the can over the entire 60-day period, all we have to do is add up the rates of change over the entire interval, which is actually this integral that we just calculated, and then divide by the amount of time that passed, divide by the interval width. So the average value is going to be the integral from 0 to 60 s prime of t dt, just like in the previous part. And then we need to divide this by the interval width, divide by 60, which is the same as multiplying by 1 over 60. So in fact, all we have to do is divide 171.81 millimeters by 60 days. And this will be about 2.863 millimeters per day. The average rate of change in the height of the water is about 2.863 millimeters per day. Moving on to part C. Assuming no evaporation occurs, at what rate is the volume of water in the can changing at time t equals 7, and indicate units of measure? To answer this question, let's start off by writing a function for the volume of water in the can. The volume of water in the can, since it's a cylinder, is going to be the area of the circular base multiplied by the height. The area of the circular base is pi r squared, and r, we know, is 10 millimeters. The radius is 10 millimeters. So pi times r squared is pi times 100. That's the area of the circular base, and then for volume, we need to multiply by the height, which is the s of t function. So this is a function for volume. It is, of course, a function of t, and for part C, we are asked at what rate the volume of water in the can is changing at time t equals 7. So all we have to do is take the derivative of this function and plug in 7. V prime of 7 is going to be, well, it's just going to be 100 pi multiplied by s prime of 7. And we can just consult the calculator to calculate this. So on the calculator, I'll type 100 pi, and then we have to multiply by s prime of 7. Now, we don't have to use the calculator's derivative function because s prime is actually what the question gives us. The question gives us s prime. So that's going to be multiplied by 2 times sine of 0.03 times 7, because the question is about t equals 7. And we want to make sure that we put this whole derivative in parentheses. So let me put a parenthesis in front there. And at the end, we have plus 1.5. And this is about 602.218. Since the height is measured in millimeters, the volume is measured in millimeters cubed. And since t is measured in days, this rate of change of the volume is cubic millimeters per day. So on the 7th day, the volume of water in the can is increasing by about 602.218 cubic millimeters per day. Finally, part D. During the same 60-day period we've been discussing, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. The height of the water in the can on Monsoon Mountain is modeled by the function m, where m equals this. The height, m of t, is measured in millimeters, and t is measured in days between 0 and 60. Let d of t equal m prime of t minus s prime of t, where s prime, of course, is the s prime that we've been considering this whole time. We want to apply the intermediate value theorem to the function d on the interval from 0 to 60 to justify that there exists a time from 0 to 60 at which the heights of the water in the two cans are changing at the same rate. Now, all of our functions are continuous. It's clear that s prime is continuous, and m is a polynomial, so it's continuous, and so is its derivative, m prime. So our difference function, d of t, is also continuous, so it's possible that we could apply the intermediate value theorem. The way that we'll do that is plug in 0 to d of t, and then also plug in 60 to d of t. Hopefully, they have opposite signs, and in order for that to be the case, since d of t is continuous, it must pass through 0, which means there must be some time at which the difference in these rates of change is 0. So for part D, we will look at d of 0, plugging 0 into our difference function, which is m prime of 0 minus s prime of 0. And then we will also plug in 60, the final time in our interval. D of 60, of course, is equal to m prime of 60 minus s prime of 60. Now, a little bit of this will be easier to do without the calculator. I don't really feel like typing all of this into the calculator. It's fairly easy to just find the derivative, and then we'll just plug 60 into that on the calculator. Let's write the derivative right up here where we have a little bit of room, m prime of t. That's going to be 1 over 400 multiplied by, just using the power rule, 9t squared minus 60t plus 330. All right, so we will just plug 60 and 0 into this for our calculator. Although plugging in 0 is really easy because this goes away and this goes away. And so if we plug in 0, all we're going to get is 330 over 400, which is just 33 over 40. So when we plug in 0, we're going to have 33 over 40. That's m prime of 0. And then going to look at s prime. Plugging 0 into s prime will produce 2 times sine of 0, which is 0, plus 1.5. So that's actually just 1.5, or 3 halves, so minus 3 halves. This is clearly negative because 33 over 40 is less than 1, and we're subtracting 3 halves, which is greater than 1. All right, now let's consider the second part where we plug in 60, and hopefully this will be positive. Thus, the intermediate value theorem will apply to show us that d, the function d, must have passed 0 at some point, since it went from negative to positive. But let's do the calculation and see. Here on the calculator, I'll start off with m prime of 60. I already know what m prime is. It is up here, so now I'll just plug 60 into this. I'll save the division by 400 for the end. So we have 9 times 60 squared minus 60 times 60 plus 330. And then divide this whole thing by 400. This turns out to be 72.825. Then we will want to find s prime of 60. S prime, we know, is 2 times sine of blah, 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 blah. Let's plug 60 into that. 2 times sine of 0.03 times 60, and then plus 1.5. This is about 3.447. And this is clearly positive. So yes, we can use the IVT. Since d of t is continuous and d of 0 is negative, while d of 60 is positive, the intermediate value theorem guarantees that there must be some time in the interval where d of t takes on that intermediate value of 0. It starts off less than 0, it finishes above 0, so it must have passed 0 at some time in the interval. And that completes our solution to free response question 1 from the 2011 AP Calc AB exam. This is problem 3 from the 2013 AP Calc AB exam. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t from 0 to 6 is given by differentiable function c, where t is measured in minutes. Selected values of c of t, measured in ounces, are given in the table above, which we see here. Part A asks us to use the data in the table to approximate c prime of 3.5 and show the computations that lead to our answer and indicate units of measure. Since the function c is the ounces of coffee that are in the cup, c prime is going to be the change in ounces per unit of time, which is minutes, so ounces per minute. Now, of course, we don't know what c of t is explicitly, so we can't find a function for the derivative, but we can approximate the value of the derivative at 3.5 by looking at what the average rate of change of the function c of t is from 3 to 4, because 3.5 is in the middle of that interval. So if we look at the average rate of change from 3 to 4, we should get a decent approximation of c prime of 3.5. So for part A, we are trying to find c prime of 3.5, and we know that it should be approximately the change in the ounces of coffee from time t equals 3 to time t equals 4. So c of 4 minus c of 3. Divided by the length of that interval, which is just 4 minus 3. Now let's refer to the table. C of 4 is 12.8, and C of 3 is 11.2. So their difference is 1.6. The denominator, 4 minus 3, is obviously 1, and so this is just 1.6, and like we said, this is going to be in ounces per minute. Moving on then to part B. Is there a time t from 2 to 4 at which c prime of t is equal to 2? And we must justify our answer. For this, we are using the mean value theorem. C of t, we know, is a differentiable and thus continuous function, so we can use the mean value theorem as long as we find the pieces necessary in the table. In order to use the mean value theorem to conclude that the derivative is equal to 2 at some time, we need to find some interval in the table such that the average rate of change over that interval is equal to 2. So for some examples, if we look at the interval of time from 2 to 3, the change in ounces looks to be 2.4, but the change in minutes is just 1, so the average rate of change would be 2.4. That's not equal to 2, so that's not going to work. We are not restricted to looking at intervals of length only 1, however. If we look at an interval like this with length 2, the average rate of change over this interval is 12.8 minus 8.8, that's 4, divided by 4 minus 2. That's 4 divided by 2, which is 2, which is exactly what we're looking for. We have an interval over which the average rate of change is 2. Thus, at some point in that interval, the mean value theorem would guarantee that the derivative is equal to 2. The interval we were just looking at was from 2 to 4. So c of 4 minus c of 2 divided by 4 minus 2. We found that this actually equals 4 over 2, which equals 2. So we have an interval over which the average rate of change is 2. We can apply the mean value theorem. Since we were told that c is differentiable and thus continuous, we can use the mean value theorem to conclude there must have been a time t from 2 to 4, so between these two values, for which c prime of t was equal to that average rate of change of 2. Moving on to part C. Use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the average number of ounces of coffee in the cup. That's what this is. It's adding up the ounces of coffee in the cup, C of t, and then dividing by the interval length. So this is over that whole time from 0 to 6. Using correct units, explain the meaning of this integral, which is what I just said. It is the average amount of coffee in the cup, because it's the sum of all the amounts of coffee in the cup divided by the time, right? Divided by 6 minutes in this case. Now let's use the table to help organize our information that we'll use for the midpoint sum. The interval length is 6, that's the length of this entire interval, and we're splitting it up into 3 subintervals. So each subinterval should have a length of 2. Thus, one rectangle will go from 0 to 2 with the height as determined by the midpoint, which is the height at t equals 1, which is 5.3. The next rectangle will go from 2 to 4 and have the height as determined by the c value at the midpoint, which is 11.2. And then the next rectangle will go from 4 to 6, with its height again determined by the c value at the midpoint, which is 5, and the height is 13.8. So our approximation for this integral is going to be 1/6 multiplied by the sum of the areas of these rectangles. Their areas are just base times height, and each one has a base of 2. So let's suppose we just pull that factor of 2 out. So it's 1/6 times 2 multiplied by, now we just have to worry about the heights, which we've jotted down, 5.3, 11.2, and 13.8. This is equal to 1/6 times 2 is 1/3, and then adding up everything in brackets, that's going to be, let's see, 16, 29, and then 30, and then 30.3. So multiplied by 30.3, and 1/3 of 30.3 is 10.1. And again, this is in ounces. It's the average number of ounces of coffee in the cup over the time interval. And of course, the problem also asked us to explain the meaning of this integral, and so there we go. Our approximation for its value was 10.1 ounces using the indicated midpoint sum, and then this is the explanation of what it means, the average amount of coffee in the cup in ounces over the time interval. Finally, part D. The amount of coffee in the cup in ounces is modeled by this function. Using this model, we are asked to find the rate at which the amount of coffee in the cup is changing when t equals 5. This is an easy part to finish with. I'll try to squeeze it in right here, part D. We just have to take the derivative and then plug in t equals 5. So let's see, what is b prime of t? Well, the derivative of 16 will just be 0, and then taking the derivative of negative 16 e to the negative 0.4t, we will have just negative 16 multiplied by e to the negative 0.4t, because the exponential function is its own derivative, but then we have to multiply by the derivative of the inside function. The derivative of negative 0.4t is just negative 0.4. So all that's left for us to do now is simplify this derivative a little bit, and then plug in t equals 5. Negative 16 multiplied by negative 0.4 is just positive 6.4. So this is 6.4 times e to the negative 0.4t. And I'd say that's a good point to plug in t equals 5. B prime of 5 is going to be 6.4 multiplied by e to the negative 0.4 times 5, that's just e to the negative 2, and so we might want to finish by just rewriting this with positive exponents. So 6.4 over e squared. And that's at the perfect time because it sounds like my laundry is done. Let's just make sure that we get our units in here. This is ounces per minute because it is a derivative of this function, which was giving us the number of ounces of coffee in the cup as a function of the minutes. So if we take its derivative, we'll get the rate of change of ounces as the minutes pass. So ounces per minute. And that will complete our solution to free response question 3 from the 2013 AP Calc AB exam. Next up are the linear motion problems. For these problems, recall that we are talking about motion on a line. So a negative velocity indicates leftwards motion on the line, whereas positive velocity indicates rightwards motion. Also recall that in order to determine if the speed of a particle is increasing at a point in time, you have to check if the velocity and acceleration have the same sign. I think of acceleration as pulling on velocity. So if they have the same sign, the acceleration is pulling in the same direction that the velocity is going, and so the particle is speeding up. If that doesn't make much sense, hopefully it'll make sense when you see the problems. Good luck. This is free response question 1 from the 2011 AP Calc AB exam. This is part of the calculator section. We will have to bust out our calculator a few times for this question. Let's read it. For t between 0 and 6, a particle is moving along the x-axis. The particle's position, x of t, is not explicitly given. The velocity of the particle is given by v of t equals 2 sine of e to the t over 4 plus 1. The acceleration is a of t equals half e to the t over 4 cosine e to the t over 4, and we also know that x of 0, the initial position of the particle, is 2. All right, that's a whole lot of information. Part A. Is the speed of the particle increasing or decreasing at time t equals 5.5, and give a reason for your answer. Remember that speed is the absolute value of velocity. So if the velocity is getting more extreme, either more positive or more negative, then the speed is increasing. To figure out if that's happening, we need to assess both the velocity and the acceleration. If they have the same sign, then yes, the speed is increasing. If the velocity is positive and the acceleration is positive, that would mean the particle is moving to the right, and it's doing so at a faster pace because the acceleration is positive and the velocity is positive. If the velocity is negative, that would mean the particle is moving to the left, and if the acceleration is also negative, that would mean that the particle is speeding up with that leftward motion. So if the velocity and acceleration have the same sign, then the particle is speeding up. Now I've opened up our graphing calculator. Again, for part A, we're going to look at the velocity at the time of interest, which is 5.5, and the acceleration at 5.5. If they have the same sign, then indeed the particle is speeding up. So let's start with the velocity. Here is our velocity function, and we need to plug in 5.5. So let's type that into our calculator very carefully. It's going to be 2 times sine of e to the t over 4, but we're plugging in 5.5 for t, so 5.5 over 4. and then plus 1. We see that's about negative 0.453. Before we write that down, let's just also check the acceleration. That's right here. Okay, so we'll plug this in. We have 1/2, so 1 over 2. And maybe we'll put that in parentheses just to make sure we're being careful with the calculator. 1/2 multiplied by e to the t over 4. Again, t is 5.5, so we're plugging in 5.5. Multiplied by cosine of e to the 5.5 over 4. And that's it. Press enter. Okay, so we see both the velocity, which is about negative 0.453, and the acceleration, which is about negative 1.359, both of these are negative. So indeed, at t equals 5.5, the speed of the particle is increasing. It is moving to the left because the velocity is negative, and it's doing so at a faster rate as time goes on because the acceleration is also negative. And there is our reasoning written out. Moving on to part B. Find the average velocity of the particle for the time period between 0 and 6. The average value of a function is found by just integrating the function across the interval in question. So to find average velocity, we'll integrate velocity from 0 to 6, and then just divide by the interval length. So we will divide it by 6. It's kind of like adding up all the values in a data set and then dividing by the total number of values in that data set. All right, so we'll write this down. The average velocity, whoops, don't need two b's there. The average velocity is what? Well, it's 1/6, because again, we have to divide by the interval length, which is 6. 1/6 times the integral from 0 to 6 of velocity. The velocity function, of course, is given. We'll go ahead and plug this into the calculator. All right, again, we'll plug this in very carefully. We have 1 divided by 6 multiplied by, I'll press the math button to access all my functions and choose option 9, the integration function. We are integrating from 0 to 6. And now I have to put in the velocity function, which I know is 2 sine of e to the t over 4. So 2 multiplied by sine of e to the, I'm just going to use x as the variable, divided by 4, and also plus 1. And we're integrating with respect to x. Again, I'm just replacing t with x. Doesn't really matter. We did also multiply by the 1/6 at the front. We'll just press enter, and there it is. I just changed the mode of my calculator to decimals so I could get a decimal answer. Exactly how you would do that on your calculator, if it was reporting fractions, may vary. A lot of calculators will have a secondary approximately option on their enter key, so you could press second enter and you would get an approximation instead of an exact value, but it depends on your calculator. So for me, I've got this decimal approximation. It is about 1.949. That is the average velocity of the particle on the interval from 0 to 6. Again, all we did was integrate the velocity over that interval and divide by the interval length. Moving on to part C. Find the total distance traveled by the particle from time t equals 0 to t equals 6. This is pretty similar to the previous problem. We will again need an integral that we will use our calculator for in order to calculate distance. Now, how do you calculate the distance traveled when you have the functions that we've got in this situation? Well, you don't want to integrate velocity because some velocities may be positive, some may be negative, and that could cancel some of the distance out. Remember, we are trying to calculate distance, so we don't care if the particle goes 100 feet one way and then 100 feet back and its displacement would be 0. We would want to count that distance as 200. Now, in order to represent that in an integral, we actually have to integrate the speed, which has no regard for sign because it's the absolute value of the velocity function. So what is the distance? Well, we have to integrate from 0 to 6 again, the speed. And the speed, like I said, is the absolute value of the velocity. Of course, having a calculator for this makes it a breeze. So coming back to the calculator, I'll press the math button to access my functions, and press number 9, the integration function. Again, we're integrating from 0 to 6, and what we're integrating is the absolute value. So I will press math, and then go to the num tab, and then press the absolute value function. This is the absolute value of velocity. So now I have to type in the velocity function, which is 2 sine of e to the t, we're just going to replace t with x, divided by 4, and then plus 1. I have to correct this, I accidentally put times 4, this is divided by 4. And then plus 1 outside of the sine function, but still in the absolute value bars. And we're integrating this with respect to x. So this is the integral of the speed, which is the absolute value of velocity, from 0 to 6. We see it's about 12.57. So there we go. The distance traveled over this interval is about 12.573. We don't integrate velocity because some of the velocities could cancel each other out since they could be positive or negative. We just want to count all the distance traveled, no matter the direction, so we integrate speed. All right, moving on to part D. For t between 0 and 6, the particle changes direction exactly once. We need to find the position of the particle at that time. All right, there are a couple steps to this problem. If we want to find the position of the particle at the time when it changes direction, we first need to figure out when it changes direction. Now, a change in direction will be marked by a change in the sign of velocity. If we go from positive to negative velocity, or vice versa, that means that the direction has changed from right to left or from left to right. So let's open up our graphing calculator and see where the velocity on this interval from 0 to 6 passes 0, where the velocity changes sign. Going back to my calculator, I'll press y equals so I can enter in the velocity function and then look at its graph. The velocity function is 2 sine of e to the x divided by 4 and plus 1. Now I can press the graph button to get a look at the graph, and we want to look at the interval between 0 and 6 and see where this velocity function passes 0 and changes sign. And we see it appears to be right there. The velocity goes from positive to negative at t equals 5.158. It also passes 0 and changes sign to the right over here around 7, but that's outside of the interval we're interested in. So where does it hit 0? Well, in the interval of interest that we have, the velocity hits 0 at about 5.1955. And with that information, we can find the position of the particle at the time when it changes direction. It changes direction at t equals 5.1955. So what is the position at that time? Well, it's going to be the initial position plus the accumulation or integral of the velocities from 0 to the time in question. This is like taking that starting position, which we know, that's why we're starting there, and then adding up all the change from that position we know, from t equals 0 to the time we want, t equals 5.1955. Now, of course, the position at time equals 0 is 2, so this is 2, x of 0 is 2, plus this integral of velocity from 0 to 5.1955. When it comes to finding position, we do want to integrate velocity because whether the velocity is positive or negative is very important to the position. And this final thing, of course, we will deal with on our calculator. We need 2 plus the integral, so I'll press the math button and then function 9, the integration function, the integral from 0 to 5.1955, that time at which the particle changes direction. And then we're integrating the velocity function, which we've entered a million times by now. It's 2 sine of e to the x divided by 4 plus 1 outside of the sine function. And we're integrating with respect to x. Press enter. Thankfully, we're in decimal mode, so we get our decimal approximation. This is about 14.135. 5. So at the time when the particle changes direction, which is at t equals 5.1955, the position of the particle is about 14.135. We're able to figure out quite a bit of information, even though we don't know the position function explicitly. And that completes our solution to free response question 1 from the 2011 AP Calc AB exam. This is free response question 2 from the 2013 AP Calc AB exam. A particle moves along a straight line. For t between 0 and 5, the velocity of the particle is given by this equation, and the position of the particle is given by s of t. It's known that the initial position, s of 0, is 10. Part A asks us to find all values of t in the interval from 2 to 4, for which the speed of the particle is 2. The speed of the particle is the absolute value of the velocity function. So, using a calculator, we can just find the intersections of the abs val of the velocity function and y equals 2. Heading on to the calculator, I'll press the math button and then go to the number section to access the absolute value function. Now I'll enter in the velocity, which is -2 plus, in parentheses, t squared, but we're using the variable x on the calculator, plus 3x to the power of 6 over 5. 6 over 5 is just 1.2, and then minus x cubed. I'll also graph y equals 2, and then I want to see where these things intersect. Now I'll go ahead and press the graph button and find the intersections on the interval in question, which is between 2 and 4. How you find the intersections, of course, will depend on your calculator. I'm just going to zoom in and locate them. So the intersections between 2 and 4 are these two intersections over here. One of them is at t equals 3.127. So when t equals 3.127, and the other intersection up here is when t equals 3.473. Moving on to part B. Write an expression involving an integral that gives the position s of t. Use this expression to find the position of the particle at time t equals 5. Now we'll be able to find the position by just integrating the velocity and using what we know about the initial position. So what position does the particle have at any given time t? Well, it starts off with a position of 10. So we would have 10, and then plus the integral from 0 to t of the rate of change of its position, which is the velocity. Now we're integrating the velocity, but velocity is given as a function of t. T is in the bounds of our integral, so we'll have to use a different variable. Often we would pick something like s, but we don't want to use s because s is reserved for the position function. So let's just say v of u. V of u du. This is an integral expression for the position function s of t. Then we can use the calculator and our function to find the position at time t equals 5. So what is s of 5? Well, we will consult with the calculator. It's going to be 10, the initial position, plus the integral of the velocity from 0 to the time in question, which is 5. So I'll press the math button, and then option 9 for the integration function. We are integrating from 0 to 5, and the function we are integrating is this big velocity function. I've entered it into the integral, and of course I'm using x rather than t on the calculator, and we get about -9.207. -9.207, that's the position of the particle at time 5. Moving on to part C. Find all times t in the interval from 0 to 5 at which the particle changes direction. In order for the particle to change direction, the velocity must pass 0, changing from positive to negative. It's not sufficient to just hit 0. The velocity could come down to 0, but then go back up. Still, the whole time, it's not negative. We need the velocity to go from positive to negative, like this, positive to negative, or negative to positive. That would mean that the particle has changed direction. So here on the calculator, I've entered in the velocity function, no absolute value bars this time, and we consult the graph. Remember, we're focused on the interval from 0 to 5, so let's see. Where does the velocity pass from positive to negative? or negative to positive? Well, it would appear right here at t equals 0.536. It goes from negative to positive. So yes, that is a change in direction, from moving to the left to moving to the right, because it's negative to positive. And then here, when t is about 3.318, the sign of the velocity goes from positive to negative. So it was moving to the right, but then it started moving to the left. And here that answer is written out. We see when the velocity equals 0 at these two times in the interval, and at both of these times there is a change in sign. And so it is at those two times that our particle changes direction. Finally, part D. Is the speed of the particle increasing or decreasing at time t equals 4? And we need to give a reason for our answer. The speed, again, is the absolute value of the velocity. That's going to be increasing if the acceleration has the same sign as the velocity. If the velocity were positive, but the acceleration were negative, that would mean our particle is moving to the right, but the negative acceleration means that it's doing so more slowly, so it would be slowing down. But if our velocity is positive and our acceleration is positive, then not only is the particle moving to the right, but it's also getting faster with that rightward motion. So in order to determine if the speed of the particle is increasing or decreasing at time t equals 4, we need to see if the velocity and acceleration have the same sign or opposite signs. Back on our calculator, we can just look at our graph and see that when t equals 4, it's clear the velocity is negative. V of 4 is less than 0. Now, what about the acceleration? Well, we could try to figure that out from the graph, since that is the derivative of velocity, but we might as well just use the calculator's built-in derivative function to get a precise answer. So I'll press the math button, option 8 for the derivative function. We are taking the derivative with respect to x, and then just plug in the velocity function, but in terms of x. So -2 plus parentheses x squared plus 3x to the power of 6/5, which is 1.2, minus x to the power of 3, and we are evaluating this at x equals 4. And we see that the acceleration, is also negative. So v of 4 is negative, and the acceleration, a of 4, is about negative 22.3, which is also negative. Since the velocity and acceleration have the same sign, the particle is speeding up when t equals 4. And there that answer is written out. Not only is the particle moving to the left at this time, but it's doing so more quickly because of that negative acceleration. And that will complete our solution to free response question 2 from the 2013 AP Calculus AB exam. This is free response question 2 from the 2021 AP Calc AB exam. This was part of the calculator section. We will use our calculator a good amount throughout this problem. A particle P is moving along the x-axis. The velocity of particle P at time t is given by this sine function for t between 0 and pi. At time t equals 0, the initial position of particle P is x equals 5. A second particle, Q, also moves along the x-axis. The velocity of particle Q at time t is given by this function here for t between 0 and pi. Its initial position at t equals 0 is x equals 10. Part A is to find the positions of particles P and Q at time t equals 1. So for part A, we're going to have to take the initial position of each particle and then integrate or add up the rates of change, or the velocities, from t equals 0 to t equals 1. So first, let's find the position of particle P at time t equals 1. We'll denote that xp of 1. And again, this is going to be the initial position of particle P, which was given to us as 5. And then we need to add the integral from t equals 0 to t equals 1. And what we have to integrate is the velocity. If we add up all of those rates of change, we'll get the total change in position from t equals 0 to t equals 1. And when we add that to the initial position, we'll get the actual position at t equals 1. Now, what was the velocity function, which we need to integrate? Well, for particle p, the velocity function is this, sine of t to the 1.5. So we are integrating sine of t to the 1.5, and this integral is taken with respect to t, and we'll open up the calculator to figure this out. I also set up the integral here for the position of particle q at time t equals 1. Same idea, the initial position, which was given to us, is 10, plus the integral of the velocity function from t equals 0 to t equals 1. So coming over to the calculator, I'm going to press the math button, and then press number 9, the integration function. Starting with the position of particle p, we are integrating from 0 to 1. The function we're integrating is sine of, we'll use x instead of t for convenience. This is x to the power of 1.5, and this integral is taken with respect to x. This is about 0.3707. Let's not forget to add 5 to it. We have to get that 5, that initial position. And okay, so we see this is about 5.3706. I'll round that to 5.3707. All right, as for particle q, we have to do 10, the initial position, plus, I press the math button, number 9, the integration function. We're integrating from 0 to 1. This function is x minus 1.8. Again, we're using x instead of t for convenience in our calculator, multiplied by 1.25 to the power of x. And this integral is taken with respect to x. This gives us an answer of about 8.5644. And there's our conclusion. At time t equals 1, p has this position, and particle q has this position. All right, moving on to part B. Are particles p and q moving toward each other or away from each other at time t equals 1? And we need to explain our reasoning. Now, looking back at our answer for part A, we see that particle q is to the right of particle p, because particle p is at about x equals 5, particle q is at about x equals 8.5, so q is to the right of p. If we sketch that out real quick, maybe particle p is right here and particle q is right here. The important part is that q is to the right of p. So if they're moving towards each other, then particle p should have a positive velocity, and particle q should have a negative velocity. It's moving to the left. For them to be moving away from each other, particle p should have a negative velocity, it's moving to the left, and particle q should have a positive velocity, it's moving to the right. It is also possible that they could be moving the same direction, and yet they could be getting closer together or further apart, but let's first see what their velocities are, and we can talk about that situation if necessary. We'll begin with the velocity of particle p, and the time we're interested at, again, is time t equals 1. So what's the velocity of particle p at time t equals 1? Well, we know what the function for the velocity of particle p is. That is sine of t to the 1.5. So this would be sine of 1 to the 1.5. If you plug this into your calculator, you'll get about 0.841. So the velocity of particle p is positive. So maybe I'll sketch that on our number line. It's looking something like that. As for the velocity of particle q at time t equals 1, remember that the velocity of particle q is t minus 1.8 times 1.25 to the t. So at t equals 1, this would be 1 minus 1.8 multiplied by 1.25 to the 1, which of course is just 1.25. And this is just negative 1. So we see the velocity of particle p is positive, whereas the velocity of particle q is negative. It's less than 0. So indeed, these particles are getting closer to each other. They're moving towards each other. And there's our logic written out. Since the position of particle p at time t equals 1 is to the left of particle q, and the velocity of p is positive, meaning it's moving to the right, whereas the velocity of q is negative, meaning it's moving to the left, p and q are moving toward each other at the time t equals 1. Let me add that. This is at the time t equals 1. All right, let's move on then to part C. Find the acceleration of particle q at time t equals 1. Is the speed of particle q increasing or decreasing at time t equals 1? And explain our reasoning. To determine if the speed of the particle is increasing or decreasing, we need to compare the sign of the acceleration to the sign of the velocity. Since we're talking about a one-dimensional situation, we have a particle moving on a number line, its direction is indicated by the sign of the velocity. So its speed will be increasing if its acceleration has the same sign as the velocity. If the velocity and the acceleration are both negative, the particle is moving to the left and it's speeding up with that leftward motion. If the velocity and acceleration are both positive, then the particle is moving to the right, and it's speeding up in that rightward motion. So let's see what the acceleration is, and then we'll compare the sign of that to the signs of the velocities. I said velocities, it's really just velocity, because we're only asked about particle q in this case. All right, in order to find the acceleration of particle q, the acceleration of particle q at time t equals 1, we're going to have to take the derivative of the velocity function for particle q and evaluate that at time t equals 1. Now we can do that on our calculator. So on the calculator, I'll press the math button and then number 8, the derivative function. We're taking the derivative with respect to time, but we'll use x in place of t. Now the velocity function for particle q, which is what we're taking the derivative of, is t, or in our case x, minus 1.8 multiplied by 1.25 to the power of x. And we're evaluating this when x equals 1. This gives us the acceleration of particle q at time t equals 1. And we see it's positive. It's about 1.02685. So the acceleration at this time is positive. Remember, we already assessed the velocity at time t equals 1. We already know the velocity of particle q at time t equals 1 is -1, which is obviously less than 0. So since the sign of the acceleration is opposite the sign of the velocity, the particle is actually slowing down. The velocity is negative, so it's moving to the left, but the acceleration is positive, which means it's actually moving to the left, but it's slowing down. And remember, that's because for a negative velocity, a positive acceleration means that the velocity is getting closer to 0. Closer to 0 means the speed is going down. So the speed of particle q is decreasing at time t equals 1 because the velocity and acceleration have opposite signs. All right, moving on to part D. Find the total distance traveled by particle p over the time interval from 0 to pi. To find the total distance traveled, all we have to do is integrate the speed function from t equals 0 to t equals pi. You don't want to integrate velocity because some of the velocities may be positive and some may be negative, which would cancel out. If you integrate velocity, you get displacement, which is useful, but it's not useful for this. If you just want to find how much distance was traveled, you don't want to think about whether it's left motion or right motion. You're just trying to add up all the distance traveled. So you need to integrate the speed function. Speed is the absolute value of velocity. So here for part D, we are going to integrate from time t equals 0 to t equals pi the absolute value of the velocity function of particle p. This integral, of course, is taken with respect to time. And we can do this on a calculator. Press the math button. We'll press number 9 for the integration function. We're integrating from 0 to pi. And what we're integrating is the speed, which is the absolute value of the velocity. So again, I press the math button, I go to the num tab, and function 1 is the absolute value function. Inside of this, I put the velocity, which is sine of t, or in our case x, to the 1.5. All right, we've got the velocity function in the absolute value. We're taking the integral with respect to x, and there we go. The total distance traveled from t equals 0 to t equals pi is about 1.931. Finally, there is our conclusion. Over the time interval from 0 to pi, the total distance traveled by particle p is about 1.931. And that completes our solution to free response question 2 from the 2021 AP Calc AB exam. This is free response question 6 from the 2022 AP Calc AB exam. This is part of the no calculator section. Particle p moves along the x-axis such that for time t greater than 0, Its position is given by this function, xp of t. Particle q moves along the y-axis such that for time t greater than 0, its velocity is given by this function, vq of t. At time t equals 1, the position of particle q is yq of 1 equals 2. Remember, it's moving along the y-axis. So for the time t equals 1, the position on the y-axis of particle q is 2. Part A asks us to find Vp of t, the velocity of particle p at time t. That's pretty easy because we are given the position function of particle p. This is the position function, so to find the velocity function, all we're going to have to do is take the derivative of the position function. So we will write this, Vp of t, the velocity of particle p at time t, is equal to xp prime of t. That's just the derivative of the position function. Here's xp of t, and we just need to take its derivative. The derivative of 6 is 0, and the derivative of negative 4 e to the negative t is positive 4 e to the negative t. The e to the negative t doesn't change, but you have to multiply by the derivative of the exponent. The derivative of the exponent is negative 1, which is why the negative in front of the 4 gets canceled out. And that is part A. Moving on to part B. Part B asks us to find aq of t, the acceleration of particle q at time t, and then find all times t for t greater than 0 when the speed of particle q is decreasing, and justify our answer. All right, let's start off by finding the acceleration. To do that, we just need to take the derivative of the velocity function. So aq of t, we will write, equals vq prime of t. Just take the derivative of the velocity function. The velocity function is given to us here, 1 over t squared, which is the same as t to the negative 2. So taking the derivative of that is just applying the power rule, negative 2t to the negative 3. That is the acceleration of particle q at time t. Now, the other part of the problem asks us to find when the speed of the particle is decreasing. The speed is the absolute value of the velocity, so the speed is going to be decreasing when the sign of the velocity and acceleration are opposites. So if this is particle q moving along the y-axis, if its velocity is positive, then it's moving in the positive direction. But if its acceleration is negative, then it's moving in the positive direction increasingly slowly because that negative acceleration is kind of pulling it back. On the other hand, if the velocity were negative, it would be moving down the y-axis. But if its acceleration is positive, then its speed would be decreasing because the acceleration being positive would mean that q is kind of being pulled back up, even though it is moving down. So again, we need the velocity and acceleration to have negative signs in order for the speed to be decreasing. So the speed of particle q is decreasing when the velocity and acceleration have opposite signs. It's pretty easy to see that this is when t is positive, because the acceleration will clearly be negative. T to the negative 3 is just positive, but it's getting hit with that negative 2. So acceleration will be negative, but the velocity up here is 1 over t squared. That's always going to be positive. So when t is positive, the acceleration and velocity will have opposite signs, and thus the speed will be decreasing. And we were only looking for positive times when this is happening, so this would be our answer, t greater than 0. The velocity of particle q is negative, which means that it is moving down the y-axis, but the acceleration is positive, which means that negative velocity is actually getting smaller in magnitude. On to part C. We are asked to find yq of t, the position of particle q at time t. Now, we are given the velocity of particle q, so in order to find the position of particle q, we're going to have to integrate the velocity function. So let's start this process for part C. We are looking for yq of t, the position function of particle q. That's going to be the integral. What we can do is say we're integrating from 1 to t, and then the position of particle q at time 1, we can add that at the start. So yq of 1, we know what that is, plus, and then we can integrate the velocity from 1 to t. The velocity we know is given by this function here, 1 over t squared, and I'll just write that as t to the negative 2. Although we can't use t because t is in the bound of the integral, so let's use s to the negative 2 ds. All right, yq of 1 was given in the problem as 2. That was the position at time t equals 1. So this is going to be 2 plus the integral of s to the negative 2 evaluated from 1 to t. The integral of s to the negative 2 is negative s to the negative 1. That's just using the reverse power rule. This is from 1 to t. So finally, finishing up the evaluation here, we have 2 plus, plugging in t gives us negative t to the negative 1, and then subtract, plugging in the lower bound, which is going to be negative 1 to the negative 1. Finally, we can simplify this a little bit. Let's write this as, well, what do we have? 2 minus negative 1, so 2 plus 1, so 3. And then minus t to the negative 1. So that is the position of particle q at time t. It'll even work for t's that are less than 1, because it would be like we're starting with the given position, but if you plug in a t less than 1, this integral is actually going to undo some of the distance traveled based on the velocity function, and still will give a correct position. Moving on then finally to part D. As t goes to infinity, which particle will eventually be further from the origin, and give a reason for our answer. So we'll have to look at the limits of the positions of the two particles as t goes to infinity, see which limit is greater. Let's first look at particle p. So we are taking the limit as t goes to infinity of the position of particle p. The position of particle p is given to us as 6 minus 4e to the negative t. So 6 minus 4e to the negative t. Now as t goes to infinity, this exponent, negative t, is going to get very, very negative. So this term is actually going to be going to 0. It'll be 4e to some massive negative power, which is like 4 divided by e to a massive power. So that thing is going to 0, thus this limit is going to be 6. So in the long run, particle p is going to be about 6 units away from the origin on the x-axis. On the other hand, let's look at particle q. So for particle q, we're taking the limit as t goes to infinity of the position function of particle q, which we just found, 3 minus t to the negative 1. And a very similar thing will be happening here. T to the negative 1, it might be more helpful in this case to write that as 1 over t. Clearly, as t goes to infinity then, this expression will just be approaching 3, because 1 over t will be approaching 0. So in the long run, particle q is going to be about 3 units away from the origin on the y-axis. Clearly then, since 6 is greater than 3, particle p will be further away from the origin. And there that conclusion is, and this completes our solution to free response question 6 from the 2022 AP Calc AB exam. Next up are a few implicit differentiation problems. For these problems, just recall that you have to keep your eye out for derivative rules that might sneak under your nose. If we have something like x times sine of y equals 5, then you have to recall that for x times sine of y, the product rule is necessary because we have a product of two functions, but also the chain rule is necessary because y is taken to implicitly be a function of x, so the derivative of sine of y, for example, is cosine of y times dy dx. Good luck. This is free response question 6 from the 1999 AP Calc AB exam. In the figure above, line L is tangent to the graph of y equals 1 over x squared at point P, with coordinates w, 1 over w squared, where w is greater than 0. So P is just some point of tangency with a positive x-coordinate. Point Q has coordinates w, 0. This is just the point of tangency projected down to the x-axis. And we'll say the tangent line L crosses the x-axis at a point we'll call R, which has coordinates k, 0. Part A asks us to find the value of k when w equals 3. So for the line tangent to this curve at an x-coordinate of 3, where does that line intersect the x-axis? To figure that out, we'll write an equation of the tangent line and then see what x value will cause y to be 0. To write the equation of the tangent line, we will use point-slope form, which begins with y minus the y-coordinate. Now if w equals 3, well, the y-coordinate will be 1 over 3 squared, so 1 over 9. So y minus 1 over 9. This equals the slope, which we'll put there in parentheses, multiplied by x minus the x-coordinate. The x-coordinate is 3, so all that remains is to find the slope of the tangent line. To find that, we need to take the derivative. Y equals 1 over x squared, then y prime is negative 2 over x cubed. That is just the power rule. So the slope of this tangent line at x equals 3 will have a slope of negative 2 over 3 cubed, so negative 2 over 27. And thus we have our complete tangent line equation at x equals 3. Then we can replace y with 0 and solve for x. Although rather than writing it as x, we were told that the line intersects the x-axis at a point we're going to say has coordinates k0. So the x-coordinate we're calling k. So let's just replace x with k, and we will solve for that. All right, on the left we have 0 minus 1/9, which of course is just minus 1/9. On the right, we have negative 2 over 27k. We are distributing this. And then negative 2 over 27 times negative 3, which is plus 6 over 27. Now 6 over 27, we can reduce that fraction to 2 over 9. And now we can subtract 2/9 from both sides of this equation. Thus, on the left, we have negative 3/9, which is the same as negative 1/3. And this equals negative 2 over 27k. To finish solving for k, we just multiply both sides by negative 27 over 2. So on the left, we will have positive 27. The two negatives cancel out. And in the denominator, we'll have 3 times 2, which is 6. And this equals k. Now we can just finish up by reducing the fraction, and we have that k equals 9 over 2. 3 goes into 27 9 times, and it goes into 6 twice. Thus, k equals 9/2. Moving on then to part B. For all w greater than 0, find k in terms of w. So do what we just did, but instead of plugging in w equals 3, like we did here to find the value of the derivative and whatnot, we just need to keep w arbitrary. So again, we will begin with our tangent line, y minus the y-coordinate. If we're keeping w arbitrary, then the y-coordinate will be 1 over w squared. This is the y-coordinate of the point of tangency. So y minus 1 over w squared. And then we need a slope, which is the derivative, which, as we said before, is negative 2 over w cubed. And then this needs to get multiplied by x minus the x-coordinate. We're letting w be the x-coordinate of the point of tangency. Now again, we will replace y with 0, and we will replace x with k. So 0 minus 1 over w squared equals negative 2 over w cubed multiplied by, if y is 0, we're saying that the x-coordinate is k minus w, and now we just have to solve for k in terms of w. To do that, we will begin by, again, distributing on the right side of the equation. So negative 2 over w cubed times k, that's going to give us negative 2k over w cubed. And then negative 2 over w cubed times negative w, that's going to be plus 2 over w squared, because one factor of w would cancel out. Now let's put this k expression on the left, so we will have negative 2k over w cubed. And then let's subtract 2 over w squared from both sides. So on the other side of the equation, we would have negative 1 over w squared minus 2 over w squared. So in total, minus 3 over w squared. Finally, we can finish solving for k by multiplying both sides by negative w cubed over 2. That's the reciprocal of k's coefficient, so to speak. So doing that, we have k equals negative 3 over w squared, and then we are multiplying this by negative w cubed over 2. And now we just simplify. W cubed over w squared is just going to leave w. And then negative 3 over negative 2 is just positive 3/2. So final answer, k equals 3/2 w. So if you look at a line tangent to this curve, 1 over x squared, if the x-coordinate of the point of tangency is positive, and we call it w, then that tangent line would intersect the x-axis at x equals 3/2 w. Moving on then to part C. Suppose that w is increasing at the constant rate of 7 units per second. So our tangent line, which has an x-coordinate of w, is moving forward on the curve. So w is increasing at the constant rate of 7 units per second. When w equals 5, what is the rate of change of k with respect to time? So this is a related rates problem, and we're going to have to use the equation we just found. K equals 3/2 w. In the problem, we are given the rate of change of w. It is a constant 7, so we could write dw, let me write that w again, dw dt, we know, to equal 7. We are looking for dk dt. We want to know what that is when w equals 5, right? That's what the problem asked us. It asks, when w equals 5, what's the rate of change of k with respect to time? So what we'll do is take the equation we found in the previous problem, k equals 3/2 w, and then differentiate the left and the right sides with respect to time. On the left, that's going to give us dk dt, and on the right, that's going to give us 3/2 dw dt. But dw dt we know to be constant of 7. So this, in fact, is equal to 3/2 times 7, which is 21 over 2. And so that is our answer. When w equals 5, the rate at which k is changing is 21 over 2. Its rate of change, as we see, actually does not depend on w. So 21 over 2, that's our answer. All right, moving on to part D. Suppose that w is increasing at the constant rate of 7 units per second. When w equals 5, what's the rate of change of the area of triangle PQR? I'm not sure what this symbol is. That's a rendering error. That's supposed to be triangle PQR with respect to time. Determine whether the area is increasing or decreasing at this instant. So let's look at our picture. We're talking right now about this triangle PQR, and we're wondering how its area is changing based on the rate of change of w, which we know to be 7. So let's do part D up here by our handy-dandy picture. We'll begin by writing an equation for the area. Since we need to figure out how the area is changing, we're going to need to begin with an equation for area. The area of a triangle is 1/2 base times height. So in this case, that's going to be 1/2. The height is very easy because the height is just that length there, which is the y-coordinate of 1 over w squared. Now the base length of the triangle, this part here, that's going to be the change in x-coordinates from Q to R. We know that Q has coordinates w, 0. It's just the projection of point P onto the x-axis. And point R, we previously said had coordinates k0. It's just wherever the tangent line intersects the x-axis. But earlier in the problem, we figured out that k is actually just 3/2 w. So then, the base length is 3/2 w minus w. That's the change in x. And that is just 1/2 w, or w over 2. Thus, the equation for area we can simplify to 1 over 4w. Now that we have our equation for area, we can differentiate the left and right sides. On the left, we have the derivative of the area with respect to time. That must equal, on the right, the derivative of this guy with respect to time. So let's think about this as two separate pieces. It's 1 over 4 multiplied by w to the negative 1. So the derivative of that is just going to be 1 over 4 multiplied by negative w to the negative 2 multiplied by dw dt. And now, to finish up our answer, we just have to plug in w equals 5, because we want to know how the area is changing when w equals 5, and replace dw dt with 7, and then determine whether the area is increasing or decreasing based on the sign of whatever number we get. So coming back up here, we are evaluating dA dt at the moment when w equals 5. So this is going to be 1/4 multiplied by negative w to the negative 2. Since w equals 5, that's going to be negative 1 over 5 squared, or 25. And then dw dt we know to equal 7. And then this is just negative 7 over 100. So negative 7/100ths, or negative 0.07. That's how the area is changing. Thus, since it's negative, the area is decreasing. And that completes our solution to free response question 6 from the 1999 AP Calc AB exam. This is problem 5 from the 2000 AB exam. Let's read it. Consider the curve given by xy squared minus x cubed y equals 6. The first part of the question is to show that dy dx equals this fraction. So we're just going to have to do some implicit differentiation and make sure that our result matches the answer given there. This is a no calculator question, so we won't be graphing this or anything like that, but I went ahead and graphed it anyway, and I'll show you what that looks like just because it's interesting. We will, of course, not appeal to this graph during our solution, since that's not allowed, but that's what it looks like in case you were curious. Pretty cool. All right, so let's go ahead with our implicit differentiation. I will just rewrite the equation here. We have xy squared minus x cubed y equals 6. And what we're going to do is take the derivative with respect to x on the left side of the equation and on the right side of the equation. On the right side of the equation, of course, the derivative, I'll put that this is part A as well, the derivative of a constant, the derivative of 6, is just 0. On the left, we'll have a little bit more going on. We're going to need to apply the product rule, in fact, because this first term is x times y squared, and this second term is x cubed times y. So let's start with xy squared. If we call x our f and we call y squared our g, then the product rule, of course, here is f prime g plus g prime f. F prime is just the derivative of x, which is 1, so f prime g is just y squared. And then we need to add g prime f. G prime, the derivative of y squared, is going to be 2y, that's like the derivative of the outside function, 2y, but then y is itself a function, so we need to also use the chain rule here, and that's where the signature dy dx of implicit differentiation comes from. It's like the derivative of an inside function. So that is our g prime. Let's not forget that we have to multiply that by f, which in this case is x. Let's move this equals 0 over to the right because we're going to need a little bit more room. Now we have to take the derivative of x cubed y, and this whole thing is getting subtracted. So we will subtract this derivative. Now again, we're applying the product rule. F is, I should probably put this a little bit differently so you can see the exponent there. F is x cubed, right? So f prime is going to be 3x squared. And so f prime g is 3x squared times y. Remember, the dy dx terms only show up when we take the derivative of y. So it's going to show up in this next part where we have g prime f. G is y, so g prime is literally just dy dx. And then we have to multiply this by f, which is x cubed, and close the parenthesis. Remember, we're subtracting this whole thing. And this is equal to 0. Now we just have to solve for dy dx. Solving for dy dx is super easy. You can do it step by step if you need to, but I think it's really easy to just do this in one fell swoop. I'll show you how I think about it. So I'm going to write dy dx equals, what does it equal? Well, the first thing I would do is move all the non-dy dx terms to the right side of the equation. For example, y squared needs to get subtracted from both sides. So there's going to be a minus y squared over here. What else do we have without a dy dx? The only other thing is minus 3x squared y. So we would have to add 3x squared y to both sides. After we move everything without a dy dx term over, we have to divide by everything that's with a dy dx term. Really, what we do is gather those terms together, factor out the dy dx, and then divide by everything else. So in this case, that's going to be a 2yx that we see with a dy dx. That would get divided, so 2yx. And then we also have a minus x cubed getting multiplied by dy dx. So we'd also have minus x cubed in the denominator. And that's how we solve for dy dx. Now we just need to make sure that this matches the answer that was part of the question. And if we scroll up, we see we're supposed to have 3x squared y, yes, minus y squared, yes, divided by 2xy, yes, we have that, minus x cubed. So there we go. I will take one last step of just rewriting this exactly as it appeared in the question. All right, let's move on to part B. We are supposed to find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line at each of these points. So we'll take the original equation, defining the curve, and replace x with 1, and then find all the possible y values. Those will tell us the full sets of points where the x-coordinate is 1 on this curve. I'm switching to purple here just for kicks, so let's rewrite this equation, but replacing the x's with 1s. So that's going to give us y squared minus y equals 6. And now we just have to solve this quadratic for y. Let's subtract 6 from both sides, so y squared minus y minus 6 equals 0. And then we can factor this into y minus 3 times y plus 2 equals 0. We know this factorization works because minus 3 times plus 2 is minus 6, and minus 3 plus 2 is minus 1. So we see this is a correct factorization. And this gives us the possibilities that y equals 3 or y equals negative 2. That, of course, is just the zero product property. So now let's come over here and write our tangent lines. We will do the tangent to the point 1, 3. Remember, this came from x equaling 1, so that's the x-coordinate. And then we'll also find the tangent line at the point 1, negative 2. Now, at the point 1, 3, using point-slope form, we, of course, would have y minus 3 equals the slope, which we'll have to find, multiplied by x minus 1. Now, to find this slope, we're just going to plug this point into the derivative dy dx that we found in part A. And I'll put that in red right down here. So what we're doing is taking dy dx, and we're plugging in x equals 1, y equals 3 to find the slope at this point. And remember, dy dx is right up there. So that's what we're plugging this stuff into. So what is this equal to? Well, x squared, if x is 1, that's just 1. So this is just 3 times y, and if y is 3, then 3 times y is 9. And then we subtract y squared. Y squared, of course, is 9. In the denominator, we have 2xy, which would just be 6, minus x cubed, which would just be 1, and so this is 0 over 5, which of course is 0. So we can throw a 0 in here as our slope. Turns out this equation would actually just be y equals 3 then. And we can put this in a box and move on to the next tangent line. The next tangent line is at the point 1, negative 2. Again, we can start with point-slope form. Y minus the y-coordinate, that's y minus negative 2, which is just y plus 2. This has to equal the slope, which we'll find in a minute, multiplied by x minus 1. To find the slope, of course, we'll just plug this point, 1, negative 2, into the derivative, just like we did before. So we are now plugging in x equals 1 and y equals negative 2. What is this going to equal? Well, the derivative says we have 3x squared y first. X is 1, so x squared is 1. Y is negative 2, so 3y is negative 6. And then subtract y squared, so in this case, that's minus 4. In the denominator, we have 2xy, which is just going to be negative 4, and then subtract x cubed, thus we'll subtract 1. Negative 6 minus 4 is negative 10, and the denominator is negative 5. So this is negative 10 divided by negative 5, and so the slope is positive 2. And so we can replace our box with the slope. Turns out it is 2, and so this is the tangent line. Y plus 2 equals 2 times x minus 1. And we can leave it in point slope form. All right, it is on to part C. Find the x-coordinate of each point on the curve where the tangent line is vertical. That means the slope is infinite, so to speak. So to find where that happens, where the tangent line is vertical, we're going to need to see where the denominator of the derivative is equal to 0. That's what will make it infinite if the denominator is 0. Then we just have to check that where the denominator is 0, the numerator is not also 0. As long as the numerator is anything else, we'll be fine. So let's begin by setting the denominator equal to 0. The denominator of our derivative is 2xy minus x cubed, so we have that 2xy minus x cubed is equal to 0, and thus 2xy equals x cubed. We can actually just divide both sides of the equation here by x, because if we come up to the definition of our curve, it's given by this equation, and if x was equal to 0, this equation would never be true because 0 minus 0 does not equal 6. So x cannot be equal to 0. Thus, it's totally fine to divide both sides of this equation by 0. Thus, we have 2y equals x squared. Again, this is the denominator of our derivative, which only applies on the curve. And on the curve, x is not equal to 0. From here, we can divide both sides by 2 and find that y equals 1/2 x squared. So where is the tangent line vertical? Well, it's vertical on the curve where y equals 1/2 x squared. So let's go back to our original equation and replace y with 1/2 x squared and see what x values come out of that. One more time, what we did was set the denominator of the derivative equal to 0. That led us to this, y equals 1/2 x squared, but we're only interested in points that are actually on the curve. So we're going to plug this into the curve and see what x values will satisfy this. This is the original equation. Let's go ahead and replace the y's with 1/2 x squared. So first, we're going to have x times 1/2 x squared squared, which is 1/4 x to the 4th. And then we're going to subtract x cubed multiplied by 1/2 x squared. I'll put that in parentheses. This, of course, equals 6 on the right side of the equation. X times 1/4 x to the 4th is 1/4 x to the 5th. And then minus x cubed times 1/2 x squared is minus 2/4 x to the 5th. I'm just rewriting 1/2 as 2/4 because I want common denominators. And this equals 6 on the right side of the equation. Now we can go ahead and combine these on the left to get minus 1/4 x to the power of 5 equals 6. Multiply both sides by -4, and we have that x to the 5 equals -24, and thus x is the 5th root of -24. We can't take the square root of a negative, but we can take an odd root of a negative. So this is defined. This is a real number. So it appears we have a vertical tangent where x equals the 5th root of -24. However, we do need to verify that the numerator of our derivative is non-zero here to confirm that we actually have a vertical tangent. We need to make sure the numerator of the derivative is non-zero. We know that x is the fifth root of negative 24, and we can plug that into this equation for y in order to find the appropriate y coordinate. Remember, we assumed this equation for y was true and plugged it into the original equation for the curve to get this x value. So to get the y value, just plug this x into this equation for y. Then we'll plug the x and y into the numerator of the derivative. The numerator of the derivative, for your reference, is 3x squared y minus y squared. When we plug this value for x into this equation for y, this is what we get. 1/2 x squared, so the fifth root of 24 becomes 24 to the 2/5. The negative goes away because of the squaring when we plug in for y. So you square that, negative goes away, and it's just 24 to the 2/5 with that 1/2 out front. Then we plug this value for x and this value for y into the numerator of the derivative. That gives us 3 times x squared. Squaring x again gets rid of the negative, so we just have this, multiplied by y, which we see here. And then we subtract y squared, which we see here. Squaring y turns the half to a fourth, and the 24 to the 2/5 becomes 24 to the 4/5. Now this is clearly non-zero because it's clearly a positive number. Because what we have on the left is 3 halves, 24 to the 4/5, if you were to combine those, 3 halves, 24 to the 4/5, and we're subtracting a smaller number, 1/4, 24 to the 4/5. So we've got 3 halves, 24 to the 4/5, minus the smaller number, a fourth, 24 to the 4/5. So clearly this is positive, and more importantly, that means it's non-zero. So indeed, x equals the fifth root of negative 24 is the x-coordinate of a vertical tangent. And that completes our solution to problem 5 of the 2000 AP Calc AB exam. This is free response question 6 from the 2001 AP Calc AB exam. This is part of the no calculator section. The function f is differentiable for all real numbers. That's nice. The point 3/1/4 is on the graph of y equals f of x, and the slope at each point, xy, on the graph is given by this equation. Part A asks us to find the second derivative of y with respect to x and evaluate it at the point 3/1/4. So we will start with part A right down here. Will be pretty straightforward. We just need to take the derivative of both sides of this equation. So on the left, we'll have the second derivative of y with respect to x. And on the right, we're going to have to deal with a little bit of implicit differentiation because we have that y there. So the second derivative of y with respect to x is the derivative of dy dx, which is given to us as y squared times 6 minus 2x. Now, to take the derivative of this, we are going to have to be careful and make sure we use the product rule. We have this function, y squared, which we could call f, and this function here, which we could call g. So in the context of the product rule, we've got to do f prime g plus g prime f. Beginning with f prime, we're going to have 2y, don't forget the dy dx, this is implicit differentiation, and then multiply by g, so f prime g. G is 6 minus 2x. Then we add g prime f. The derivative of g is just negative 2, so this is plus negative 2 multiplied by f, which is just y squared, so negative 2y squared. Now, we could simplify this a little bit because we know what dy dx is, so we could replace it with this expression. But we're just asked to evaluate the second derivative at this point, 3/1/4. So let's just do the evaluation. There's no need to mess with this expression a bunch. Since dy dx is part of this expression, though, let's start by evaluating what dy dx is at the point in question, 3/1/4. So we're plugging in x equals 3 and y equals 1/4 into this expression. If we just focus on the 6 minus 2x for a second, if x equals 3, 6 minus 2x is 0. And so, in fact, dy dx is actually 0 at this point in question. And so this whole term in the second derivative would get canceled out because the dy dx factor is 0. So all we have to evaluate is actually that right there. So we are looking for the second derivative of y with respect to x evaluated at the point 3 1/4. This first part of the second derivative is just going to be 0, and then we have to plug in y equals 1/4 to negative 2y squared. So that's going to be negative 2 times a fourth squared. A fourth squared is 1/16. And so our final answer for part A is negative 1/8. Moving on to part B. Part B asks us to find y equals f of x by solving the given differential equation with this given initial condition. In order to do this, we're going to use separation of variables. So we'll divide both sides of this equation by y squared, so the y's are all together on the left side. And then we'll multiply both sides by dx, so the x's are together on the right side. Then we can integrate both sides of the equation and use the given initial condition to solve for the arbitrary constant. So we'll put part B down here, and I will just rewrite the given differential equation. dy dx equals y squared multiplied by 6 minus 2x. Like I said, we're going to divide both sides by y squared. So on the left, we're going to have y to the negative 2. And we're going to multiply both sides by dx. So there's no dx on the left anymore. And on the right, we have 6 minus 2x dx. Now we can integrate both sides of this equation because we've separated the variables. On the left, the integral of y to the negative 2 dy is going to be negative y to the negative 1. In theory, we also have the addition of an arbitrary constant, but let's imagine that we collect all of our arbitrary constants on the right side of this equation, so we won't worry about it on the left side. On the right, the integral of 6 minus 2x is 6x minus x squared, and then we'll put the arbitrary constant over here. Now, we're going to need to solve for y, but it's going to be easier if we solve for c first. Let's solve for the arbitrary constant given our initial condition. The initial condition was that when x equals 3, y equals 1/4. So x equals 3, y equals 1/4. We can plug this information in and solve for the arbitrary constant. Plugging in 1/4 to negative y to the negative 1 gives us negative 4 equals, plug x equals 3 in on the right. That's going to be 6 times 3, which is 18, minus 3 squared, which is 9, plus c. 18 minus 9 is 9. Subtract 9 from both sides, and we have that negative 13 equals c. Now that we know what the arbitrary constant is, we can finish this up by solving for y. So I'll just put that off to the side there. Coming back to the equation in blue, let's multiply both sides by negative 1 to get rid of that negative there. So we're going to have y to the negative 1 equals, let's put the x squared first, which is now positive, and then minus 6x, and then minus c because we're multiplying by negative 1, but c is negative 13. So minus negative 13, which is the same as plus 13. Finally, we can invert both sides of this equation to finish getting y by itself. Thus, on the left, we'll have y, and on the right, we're just going to have 1 over x squared minus 6x plus 13. That's the answer, and that completes our solution to free response question 6 from the 2001 AP Calc AB exam. Up next are some related rates problems. When solving related rates problems, make sure not to plug in any known quantities for things that change before taking the derivative. When you plug in a known quantity for something that changes over time, you are fixing yourself at a moment in time, and thus taking the derivative with respect to time would not make any sense. So don't be too hasty when plugging in known values. Good luck. This is free response question 6 from the 2002 AP Calc AB Form B exam. Got a very nice picture for this one. Ship A, seen here, is traveling due west toward Lighthouse Rock at a speed of 15 kilometers per hour. Ship B, seen here, is traveling due north away from Lighthouse Rock at a speed of 10 kilometers per hour. Note that means x is decreasing because ship A is traveling this way, whereas y is increasing because ship B is traveling this way. All right, let x be the distance between ship A and Lighthouse Rock at time t, and let y be the distance between ship B and Lighthouse Rock at time t, as shown in the figure above. Very nice. Part A. Find the distance in kilometers between ship A and ship B when x equals 4 and y equals 3. So x is equal to 4, y is equal to 3. We just need to find this segment here. That's just Pythagorean theorem, and if you know your Pythagorean triples, you already know the answer is 5. If we were to call the distance between them, let's not use d because we're going to take some derivatives later. Let's use r. We would have that r squared equals 3 squared plus 4 squared by the Pythagorean theorem. 3 squared is 9, 4 squared is 16, so that would be 25. So r would equal the square root of 25. Of course, that is where we get our answer of 5, and the units here are kilometers. Moving on to part B. Find the rate of change in kilometers per hour of the distance between the two ships when x equals 4 and y equals 3. So for this, we are again going to use the Pythagorean theorem, but we can't plug in 3 and 4 immediately, because y is only equal to 3 and x equal to 4 for a moment. Generally speaking, these quantities are changing. So the relationship we need is r squared equals x squared plus y squared. Now we can take the derivative of both sides of this equation in order to relate the rates. On the left, we apply the power rule to get 2r, but then remember we also have implicit differentiation going on because r changes with respect to time. So we have dr dt. And then same thing on the right, 2x multiplied by dx dt plus 2y multiplied by dy dt. Now we can start to plug in known information. We're focused on the moment when x is 4 and y is 3. So we can replace x with 4 and y with 3. But we also know when x is 4 and y is 3, we figured out that r has to be 5. That was part A. So on the left, we have 2 times 5, which is 10, multiplied by dr dt. On the right, we have 2 times x, but x we know is 4, so that's 8. dx dt we also know, because it says in the problem how ship A is moving. It says ship A is traveling toward Lighthouse Rock at a speed of 15 kilometers per hour. So dx dt is negative 15. This segment, this distance, is being reduced by 15 kilometers per hour. So negative 15. And then we have plus 2y, but we know that y is 3, so 2y is 6, and dy dt is going to be 10, because ship B is moving away from the rock at 10 kilometers per hour. So 6 multiplied by 10. All right, everything's in place. We just have to solve for dr dt. On the right side, we have 8 times negative 15, which is negative 120, plus 60, so negative 60 is the sum. And then divide by 10, so negative 6. And this is a rate of change of a distance. It is kilometers per hour. Finally, part C. Let theta be the angle shown in the figure. So that's this angle here. And we want to find the rate of change of theta in radians per hour, again when x is 4 and y is 3. So we want to relate this angle theta to these sides, x and y. We can do that not using sine, because sine of theta would be y over the hypotenuse. Not using cosine, which would be x over the hypotenuse. We need to relate these sides using tangent. Tangent of theta is opposite, y, over adjacent, x. So this is just like part B, but we are using a different equation because we're concerned with a different quantity. This time we're concerned with the angle. Tangent of theta, like we said, is opposite, y, over adjacent, which is x. Now we can take the derivative of both sides of this equation and eventually solve for d theta dt. On the left, the derivative of tangent is secant squared theta, and then we are multiplying by d theta dt because the angle changes as time passes. And then on the right, we are unfortunately going to need the quotient rule. First, we'll have the derivative of the numerator, which is dy dt, and I suppose we're going to have a little bit more room to work with here, so let me move this down. So first, the derivative of the numerator, so dy dt multiplied by the denominator, which is x, and then minus the derivative of the denominator, dx dt, multiplied by the numerator, which is y. And then all of this gets divided by the denominator squared. Now we can plug in the known pieces. Secant squared of theta we can figure out by looking at the triangle. We know that x is 4 and y is 3. Remember that secant is the reciprocal of cosine, and cosine is adjacent over hypotenuse. So if cosine of theta is equal to adjacent x over hypotenuse, which we know to be 5 in this case, cosine of theta is 4 over 5. So secant is 5 over 4. So secant squared is 25 over 16. So we have 25 over 16 d theta dt. Now let's worry about the right side. On the right, it's very much like the previous problem. dy dt we know is positive 10. X was given to us as 4. dx dt we know is negative 15, so minus negative 15. Y we know is 3, so negative 15 times 3. And then again, x is 4, so the denominator will be 4 squared, or 16. Now let's just simplify this side a little bit. 10 times 4 is 40, and then 15 times 3 is 45. So this is 40 plus 45, which is 85, and then this is getting divided by 16. Now we'll multiply both sides by 16 over 25 to get d theta dt by itself. So on the left, we'll have d theta dt. And now we're multiplying 85 over 16 by 16 over 25. This, of course, produces 85 over 25, which we can simplify. 5 goes into 85 17 times, and 5 goes into 25 5 times. So final answer is 3.4. And let's not forget our units. This is an angle, and so the rate of change is radians per hour. It is the angle's rate of change. And that is our solution to free response question 6 from the 2002 AP Calc AB Form B exam. This is problem 5 from the 2003 AP Calc AB exam. Let's read it. A coffee pot has the shape of a cylinder with radius 5 inches, which we see here. Let h be the depth of the coffee in the pot, which is also measured in inches. H is a function of time measured in seconds. The volume, V, of coffee in the pot is changing at the rate of negative 5 pi root h cubic inches per second. So the volume of coffee in the pot is decreasing. Coffee is leaving the pot, and thus the height of the coffee is going to be decreasing as well. Part A is to show that the height of the coffee is changing with respect to time in this way, negative root h over 5. So we just need to find dh dt. We can do that using the volume of a cylinder equation, which is given to us. V equals pi r squared h. The cylinder we're thinking about is this cylinder of coffee inside the cylindrical coffee pot. If we take the derivative of the left side of the volume equation with respect to t, we're going to get dv dt, which is going to work out just great because dv dt was given to us. We know that dv dt equals negative 5 pi root h. So let's go ahead and write that. dv dt, we know, is negative 5 pi root h. All right, now I'm going to rewrite the volume equation. Volume equals pi r squared h, and we can go ahead and take the derivative of both sides. Remember that on the right, the only function is h. Pi is a constant, and r is a constant as well. The radius of the body of coffee is going to be 5 inches, the radius of the containing cylinder. Even as coffee leaves the pot, that radius is not going to change. All right, so taking the derivative on the left with respect to time, we get dv dt. On the right, r squared is 5 squared because the radius is fixed at 5. So this is just going to be 25 pi multiplied by, taking the derivative, dh h dt. Now we're trying to solve for dh dt. We know what dv dt is, so let's replace dv dt with its given value, which is negative 5 pi root h. Now we'll just divide both sides of this equation by 25 pi in order to solve for dh dt. And I'm going to write dh dt on the left. So this will be equal to this divided by 25 pi. And when we divide by 25 pi, 5 over 25 just leaves a factor of 5 in the denominator. The pi's cancel out, and of course we still have that negative. And thus we see that dh dt equals negative root h over 5, just as desired. So we can move on to part B. Given that h equals 17 at time t equals 0, we want to solve this differential equation for h as a function of t. So this is actually a separation of variables differential equation question. We need to separate the h's, we'll move the h's to the left, and separate the t's, get those to the right. Then integrate both sides of that equation and use this initial condition in order to solve for the arbitrary constant. So let's start setting this up, and I'll write it in red. We're going to take this equation, divide both sides by root h, and multiply both sides by dt. Thus, we're going to have 1 over root h dh on the left, and on the right, we're going to have negative 1/5 dt. Now, 1 over root h is the same as h to the negative half, so I'm just going to write it like that because that's easier to integrate. Now we integrate the left side, and we integrate the right side. On the left, using the reverse power rule to integrate this function, we increase the power of negative half by 1. Thus, it becomes a power of positive half. And then we divide by this new power. Dividing by a half is the same as multiplying by 2. In theory, we also have to add an arbitrary constant, but that's going to happen on the right side as well. So let's just gather the arbitrary constants on the right side. This is going to equal the integral of negative 1/5, which with respect to t, which is just negative 1/5 t. And then we have all our arbitrary constants. We'll just call that a plus c. So how do we find h as a function of t? Well, first, let's use our initial condition in order to solve for c, the arbitrary constant. The initial condition is that when t equals 0, h is 17. So let's plug that in. We have 2 multiplied by 17 to the 1/2, which is the square root of 17, equals negative 1/5 times t, but we're plugging in 0 for t. So that's just 0, and this equals c. So there we go. That's the arbitrary constant. It's 2 times the square root of 17. So I guess we'll just go ahead and replace that c right now. Let's write this as plus 2 times the square root of 17. And then I'll move this equation off to the side. We don't really need that anymore. Now all that's left for us to do is to solve for h. To do that, we'll divide both sides of this equation by 2 and then square both sides of the equation. Dividing both sides by 2 turns negative 1/5 t into negative 1/10 t. And 2 root 17 becomes just root 17. And then we would square both sides to get rid of that exponent of 1/2. And thus, we have our function for h in terms of t. H equals negative 1/10 t plus the square root of 17, all squared. And we're in luck because we can very easily use our solution to part B to answer part C. Part C asks, at what time t is the coffee pot empty? Well, the coffee pot would be empty when the height reaches 0. That would mean that the coffee is all the way at the bottom. There is no coffee. When the height is 0, that's when there's no coffee. So we need to come to this equation and plug in 0 for h and then solve for t. Now, if we plug in 0 for h, I'll write that this is part C. If we plug in 0 for h, we have that 0 equals this thing squared. But if 0 equals something squared, then 0 must just equal that something. So 0 equals negative 1/10 t plus the square root of 17. Again, we need this to be 0 because we need the height to be 0, because that represents there being no coffee in the pot. And then we just solve this equation for t. So we'll subtract root 17 from both sides. So we have negative root 17 equals negative 1/10 t. And then multiply both sides by negative 10 to finish getting t by itself. Thus, we have that t equals 10 times the square root of 17. And that is when the coffee pot is empty, after about 10 times the square root of 17 seconds. And that completes our solution to problem 5 from the 2003 AP Calc AB exam. This is free response question 5 from the 2005 AP Calc AB Form B exam. Consider the curve given by y squared equals 2 plus xy. Part A asks us to show that the derivative of y with respect to x is y over 2y minus x. So this is just a simple implicit differentiation problem. For part A, we are going to have to take this equation and we can differentiate the left side and the right side and then solve for dy dx. If we take the derivative of the left side, we get 2y, but then we have to apply the chain rule. This is the key step of implicit differentiation. We got to multiply by dy dx because y also changes with respect to x. This equals taking the derivative on the right side. The derivative of 2 is 0, so we don't have to write that. For the derivative of xy, we are going to need the product rule. If we call x f and y g, then the product rule is f prime g plus g prime f. F prime would just be 1, and g would be y. And then we'd have to add g prime f. G prime is dy dx, and f is just x. And again, that's just applying the product rule. All right, all that remains is to solve for dy dx. Let's subtract x dy dx from both sides so that the dy dx terms are together on the left. Then we will have 2y dy dx minus x dy dx equals y. And you can see how this is going to lead to the expected result. On the left, we'll factor dy dx out of both terms. So we have dy dx multiplied by 2y minus x equals y. And then finally divide both sides by 2y minus x to finish solving for dy dx. And we get exactly what we expected. Dy dx equals y divided by 2y minus x. And going back to part A, you can see that is the answer we were supposed to get. We don't even have to do any weird simplification. All right, part B. Find all points, xy, on the curve where the line tangent to the curve has slope 1/2. We know the slope is the derivative, which is given by this expression here, y over 2y minus x. So we just need this expression, the derivative, to equal 1/2. So here that is. I've set the derivative equal to 1/2. Let's multiply both sides by 2 and multiply both sides by 2y minus x to get rid of the fractions. Then on the left, we're going to have 2y. And on the right, we multiplied both sides by 2, so the 1/2 is gone, and it's just going to be 2y minus x on the right side. Then we can subtract 2y from both sides, and we find that 0 equals negative x, which of course is the same as saying x equals 0. If x equals 0, then what is y? Well, we can refer back to the equation of the curve. Y squared equals 2 plus xy. If x is 0, this xy term just goes away, and so we have y squared equals 2. And if y squared equals 2, then y must be plus or minus root 2. Thus, there are 2 points where the slope of the tangent to the curve is 1/2. There is the point 0, root 2, and the point 0, negative root 2. All right, let's go ahead and move on to part C. Show that there are no points, x, y, on the curve where the line tangent to the curve is horizontal. A horizontal tangent means that the slope, or the derivative at that point, is 0. So this is like part B, except we need to take that derivative and set it equal to 0. Now, the only way that this derivative is going to be 0 is if the numerator, which is y, is equal to 0. However, that just can't ever be the case, because if we look at the equation of the curve, if y is 0, then 0 squared equals 2 plus x times 0. Clearly, this has no solutions. So if the derivative is 0, which we need for a horizontal tangent, that means y must be 0 because y is the numerator of the derivative. And so based on the equation of the curve, we would need 0 squared to equal 2 plus x times 0, which would mean we need 0 to equal 2. That obviously is not possible. Thus, there are no points on the curve where the tangent has a slope of 0. We see that assuming there is such a point results in a contradiction. Moving on to part D. Let x and y be functions of time t that are related by this equation we've been working with. At time t equals 5, the value of y is 3 and dy dt is 6. We want to find the value of dx dt at time t equals 5. So this is like a related rates problem. Now this is our expression for dy dx, but now we're thinking about derivatives with respect to time. So what is dy dt? Well, it's still the case that y changes with respect to x, but now they're also both changing with respect to time. So dy dt would be dy dx, because again, y does change as x changes, but because x changes with respect to time, it's the chain rule here, we also have to multiply by dx dt. So dy dt is just dy dx, but multiplied by the change in x with respect to time. Now we can use the known information to figure out what dx dt is at t equals 5. We were told that at t equals 5, y is equal to 3 and dy dt is equal to 6. If y equals 3, we can use the given equation of the curve to solve for x. The equation of the curve was y squared equals 2 plus xy, so plugging in y equals 3, we have 9 equals 2 plus 3x. Subtracting 2 from both sides gives us 7 equals 3x. And so x equals 7 over 3. Now let's start to plug in our known information. At t equals 5, dy dt is 6. So on the left, we have 6. And then on the right, y in the numerator is 3. In the denominator, we have 2 times 3 minus 7 over 3, multiplied by dx dt, which is what we are trying to solve for. Now, 6 is the same as 18 thirds. So this is 18 thirds minus 7 thirds, but that's the same as 11 thirds. So let's just write that as 11 thirds. But then 3 over 11 thirds is the same as 3 times 3 over 11, which is just 9 over 11. So now we can multiply both sides by 11 over 9 in order to solve for dx dt. So dx dt must equal 6 times 11 over 9, which is 66 over 9, which, reducing by a factor of 3, is 22 over 3. And perhaps we should specify with notation that this is the value of dx dt when t equals 5. And that is our answer, 22 thirds. And that completes our solution to free response question 5 from the 2005 AP Calc AB Form B exam. Next up are problems on extreme values and concavity. For these problems, recall that it often comes down to finding critical points, which is where the derivative equals 0 or doesn't exist. But a critical point is not necessarily the location of an extreme value. If x equals c is a critical point, we have to check if the derivative changes sign at that point in order to determine if it's an extreme value or not. If a derivative goes from positive to negative, the function goes from increasing to decreasing, and thus that critical point would be a maximum. On the other hand, if the derivative goes from negative to positive, the function goes from decreasing to increasing, and thus that point is a minimum. You can also use the second derivative and assess concavity to classify critical points. Good luck. This is free response question 2 from the 1998 AP Calc AB exam. Let's read it. Let f be the function given by f of x equals 2x times e to the 2x. Part A asks us to find the limit of f of x as x goes to negative infinity and the limit as x goes to positive infinity. So let's put part A down here, and we will start by evaluating the limit of our function as x goes to negative infinity. If x is going to negative infinity, then 2x is also going to negative infinity, which means this 2x in the exponent of e is going to negative infinity. So we are in fact dividing this 2x by increasingly large powers of e, because e has a negative exponent, so really it's in the denominator. And we could write it that way, perhaps to make this a little more clear. This is the same as the limit as x goes to negative infinity of 2x in the numerator, divided by e to the absolute value of 2x in the denominator. Again, the power of e is negative because x is going to negative infinity, but we can make that power positive by moving the e to the denominator. At this point, it's pretty clear that the limit equals 0. Sure, the numerator and denominator are both going to infinity or negative infinity. It's the numerator going to negative infinity and the denominator going to positive infinity. But hopefully you know exponential growth, e to the 2x, in the denominator far outpaces the linear growth of 2x in the numerator. You could use L'Hopital's rule to formalize this, but regardless, the denominator is going to infinity far quicker than the numerator is, and so this limit is 0. For part B, the limit as x goes to positive infinity, or excuse me, this isn't part B, this is the second part of part A. For x going to positive infinity, this is quite obviously going to positive infinity. You just have 2x, which is getting really big, and e to the 2x, which is getting really big. So you could say this limit is infinity, or it doesn't exist. Remember that a limit diverging to infinity is just a particular type of non-existence. Let's move on then to the actual part B of this problem. Find the absolute minimum value of the function f and justify that our answer is an absolute minimum. To investigate extreme values, we of course need to find critical points. So for part B, we will begin by taking the derivative, finding f prime, and then setting that equal to 0. Now f is a product of functions. You might call 2xu and e to the 2x v. Then, to take the derivative, we need to use the product rule, u prime v plus v prime u. U prime would just be 2, so u prime v is 2e to the 2x. If v is e to the 2x, then v prime is e to the 2x times 2, because 2 is the derivative of the inside function, 2x. So v prime is e to the 2x times 2, which I'll write as 2 times e to the 2x. And then you have to multiply that by u, which is 2x. Finally, we'll set this equal to 0 and solve for x to find critical points. As we go ahead and set this equal to 0, I'm going to factor 2e to the 2x out of both terms. So we have 2e to the 2x multiplied by 1 plus 2x, and we're setting this equal to 0. Note also that this derivative clearly exists everywhere, so the only critical points will be where the derivative equals 0. Now, 2e to the 2x is never 0, So the only time the derivative equals 0 is when 1 plus 2x equals 0, which only happens when x is negative 1/2. Thus, we have our critical point. Now, whether or not an absolute minimum occurs at this critical point is going to depend on the behavior of the derivative to the left and to the right of the critical point. For x equals negative 1/2 to be the location of an absolute minimum, it must be the case that the function is decreasing to the left of negative 1/2 and then increasing afterwards. So decreasing and then increasing. To see if that's the case, we can take a sample point from the left of negative 1/2 and plug it into the derivative and see if it's positive or negative, and then take a sample point from the right of negative 1/2 and plug it in the derivative and see if it's positive or negative. So to the left of negative 1/2, let's choose a simple point like, say, negative 1. What is f prime of negative 1? Plugging negative 1 into the derivative gives us 2e to the negative 2. I'm plugging it in here. And then 2 times 2 times negative 1 is negative 4. So minus 4 times e to the negative 2. And clearly, this is less than 0 because we have 2e to the negative 2, which is positive, but then we're subtracting a bigger positive number. We're subtracting 4e to the negative 2. This clearly is negative, which means to the left of negative 1/2, f prime must be less than 0. To the right of negative 1/2, let's plug in a sample point like 0. 0 is a very easy option. So f prime of 0, what is that? Well, that's going to be 2 times e to the 0. And then this second term in the derivative is just zeroed out. And so this is f prime of 0, which is clearly positive because it's just equal to 2 times 1. So to the right of negative 1/2, f prime is positive. Thus, x equals negative 1/2 is the location of an absolute minimum. But remember, part B asked us to find the absolute minimum, not just the location of it. The x-coordinate is the location, but we need to actually plug the x-coordinate in to our function in order to find what the absolute minimum actually is. So let's plug negative 1/2 into our function f. Now, f of x is 2x e to the 2x. So we're going to have 2x, which is negative 1/2, times e to the 2x. So e to the 2 times negative 1/2. What is this? Well, 2 times negative 1/2 is negative 1. And then that's getting multiplied by e to the 2 times negative 1/2. So that's e to the negative 1. This clearly is negative 1 over e. Thus, we have our conclusion. Because the derivative is negative for x less than negative 1/2, and the derivative is positive for x greater than negative 1/2, the function is decreasing and then increasing. It switches right at negative 1/2. And so f of negative 1/2, which is negative 1 over e, must be the absolute minimum of the function. On to part C. What is the range of f? Well, we just figured out that the minimum value f takes on is negative 1 over e. And we know from part A that the function goes to positive infinity as x goes to positive infinity. So there is no upper bound on this function. We clearly know the lower bound is negative 1 over e, and so its range is everything from negative 1 over e to positive infinity. So for part C, we can say that the range is everything from negative 1 over e, which is included. The function does actually attain that minimum value. And then there is no upper bound. So everything up to positive infinity, not including positive infinity because positive infinity is not a number. Finally, let's take care of part D. Part D says consider the family of functions defined by y equals bx e to the bx, where b is a non-zero constant. We've been working with the particular function where b is 2x e to the 2x. So, considering this more general family, we want to show that the absolute minimum value of bx e to the bx is the same for all non-zero values of b. So, the absolute minimum should not depend on b. the absolute minimum should be the same. We just found the absolute minimum of 2x e to the 2x was negative 1 over e, so then it should be the case that the absolute minimum of any function, bx e to the bx, is negative 1 over e, provided that b is non-zero. So let's try to prove that. We're considering y equals bx e to the bx. To determine anything about the absolute minimum of such a function, we'll need to take the derivative and find the critical points. Y prime is, well, again, it's just product rule. We have b multiplied by e to the bx, that's like u prime v, and then we're going to have b squared x e to the bx. That's like v prime u. Now, this derivative is defined everywhere, so in investigating critical points, all that remains is to set it equal to 0. As we do that, we'll factor b e to the bx out of both terms. So we have b e to the bx multiplied by 1 plus bx, and we're setting this equal to 0. Assuming that b is non-zero, b e to the bx is also non-zero. So the only critical point occurs when 1 plus bx equals 0. 1 plus bx only equals 0 when x is negative 1 over b. Just like in the previous part of this problem, we had x equals negative 1 over 2. So if this function has an absolute minimum, it must occur at x equals negative 1 over b. So let's try evaluating the function at x equals negative 1 over b. At x equals negative 1 over b, we have that y would equal b multiplied by negative 1 over b multiplied by e to the b multiplied by negative 1 over b. Simplifying, b times negative 1 over b is negative 1, and e to the b times negative 1 over b is e to the negative 1. This, as expected, is negative 1 over e. Now, how do we actually know that each one of these functions, y equals bx e to the bx, has a minimum? We know that if it has a minimum, then it occurs at negative 1 over b, and this is what the minimum is. But how do we know they're all minimums? How do we know that there's not one of these that's actually a maximum for a certain value of b? Well, to proceed with this investigation, we can assume that b is positive. If you consider a positive case, like y equals 2x e to the 2x, what's the difference if we make that negative, like y equals negative 2x e to the negative 2x? It's going to be the same, except the y values are going to occur at the opposite x values. It's as if we didn't change 2 to negative 2, and instead changed the x's to negative x. And when you make a change like this, what amounts to just changing x to negative x, that just causes a reflection across the y-axis, something like this to something like this. It's just a reflection across the y-axis, which does not change the minimum value. So we can assume that b is greater than 0. The minimum values will be the same for the negative b's. In that case, we can again consider a sign chart. Here's negative 1 over b, and since b is positive, this is a negative number. So to the right of negative 1 over b is the point 0, and f prime of 0 is clearly positive. If we plug 0 in here, this term goes away, and this is just b times 1. Again, we're assuming b is positive, so in the case where x is 0, the derivative is positive, and so the function is increasing to the right of negative 1 over b. On the other hand, to the left of negative 1 over b would be a number like negative 2 over b. And if we plug negative 2 over b into f prime, this is what we get. To make the notation more clear, let me specify that right now I'm considering f of x to be the general function bx e to the bx. So f prime just looks like this. And if we plug in negative 2 over b, this is what we get, which is clearly negative, because it's a positive number, b e to the negative 2, minus a bigger positive number, minus 2b e to the negative 2. So clearly that guy is negative. So the function will go from decreasing to increasing in all cases. And so we can state our conclusion for part D that any function like this, any function y, will have an absolute minimum of negative 1 over e. And this applies for all non-zero values of b. And that completes our solution to free response question 2 from the 1998 AP Calc AB exam. This is problem 4 from the 1999 AB exam. Let's read through it. Suppose that the function f has a continuous second derivative for all x, and that f of 0 equals 2, f prime of 0 is negative 3, f double prime of 0 is 0. We'll let g be a function whose derivative is given by the following equation involving f and f prime. Part A is to write an equation of the line that's tangent to the graph of f at the point where x equals 0. So we'll use point-slope form for this. Remember, the point-slope form of a line is y minus the y-coordinate. What's our y-coordinate? Well, we want the line to be tangent to f where x is 0. And we know that when x equals 0, f is 2. So the y-coordinate is that output of the function, which is 2. So we'll have y minus 2 equals the slope. What's the slope? Well, f prime of 0 is given to us. It's negative 3. That's the slope of a tangent line at x equals negative 3 on this function. So the slope is negative 3, and then x, of course, minus the x-coordinate, which is 0, and we don't even have to write that. So if we want to put this into slope-intercept form, which we don't have to do, but this is a really simple line, so perhaps we might as well, we get y equals negative 3x plus 2. So that is our tangent line. Let's move on to part B. Is there sufficient information to determine whether or not the graph of f has a point of inflection when x equals 0? We have to recall that a point of inflection is a point where the graph changes concavity, where the second derivative goes from negative to positive or from positive to negative. In this case, there is not sufficient information. The only thing we know about the second derivative is that it is continuous, and when x equals 0, the second derivative is also 0. But we don't know the values of the second derivative to the left or to the right of 0. So we can't say if it switches sign, and thus we can't say if in fact x equals 0 is a point of inflection. Moving on then to part C. Given that g of 0 equals 4, write an equation of the line tangent to the graph of g at the point where x equals 0. So this will be a lot like part A. We'll use the point-slope form of a line in order to get our tangent line. Point-slope form is y minus the y-coordinate. We want this line to be tangent to the graph of g, so the y-coordinate is the output of g when x is 0, and we're given that is 4, so we have y minus 4. This has to equal the slope of the tangent line at x equals 0, multiplied by x, of course, minus the x-coordinate, which is 0. We don't have to write minus 0. So now let's just focus on this slope. This slope is g prime of 0, so we just need to figure out what that is. We're given that g prime is this big, long expression. So let's just plug x equals 0 into that. G prime of 0 is going to be e to the negative 2 times 0, multiplied by 3 times f of 0, plus 2 times f prime of 0. And now we can plug in the known pieces of information here. E to the negative 2 times 0 is just e to the 0, which is 1. So this part doesn't really matter. 3 times f of 0, what is that? Well, looking at the question, f of 0, remember, is 2. So 3 times f of 0 is 6. Then we must add 2 times f prime of 0. F prime of 0 is negative 3. So 2 times f prime of 0 is negative 6. Thus, the derivative of g at x equals 0 is 6 plus negative 6, which is 0. And so we can plug 0 into that box. Thus, the right side of this equation is actually just 0. And so we can add 4 to both sides and find that the equation of the tangent line is just y equals 4, a horizontal line. Finally, let's move on to part D. Part D says, show that g double prime of x, the second derivative of g, equals this big long expression. And then we want to say, does g have a local maximum at x equals 0 or not? And we need to justify our answer. Okay, so this works out pretty nicely because once we take the second derivative, we'll find that it equals this, and then we can just plug x equals 0 into that second derivative. That will give us the concavity. If the concavity is downwards, so the second derivative takes on a negative value, well, that will tell us that in fact we have a maximum. And if when we plug x equals 0 into the second derivative, we get a positive number, that tells us it's concave up and we have a minimum. So let's go ahead and take the derivative of g. Remember that g prime was given to us as this expression, e to the negative 2x times all this stuff. So I'm going to go ahead and shrink our work for parts A through C, just so I can scroll up a little bit and we can see the whole problem while we work through part D. So to find g double prime of x, we'll just go ahead and take the derivative of both sides of this equation. That, of course, gives us g double prime on the left. And on the right, we'll need some derivative rules. First, notice that it's a product of functions, an exponential function times this sum of functions. So the product rule says the derivative of this will be u prime v plus v prime u. The derivative of the first function times the second function, so we'll start with that. The derivative of the first function is negative 2 e to the negative 2x, using a little bit of chain rule there. And then we have to multiply by the second function, which is just 3 f of x plus 2 f prime of x. So that is our u prime v from the product rule. Now we need to add v prime u. I'll do that on a second line so that I don't run out of room here. So let's think about the derivative of 3f of x plus 2f prime of x. That's our second function, which we need the derivative of here. And that's pretty straightforward. That's just going to be 3f prime of x and then plus 2f double prime of x. And this needs to get multiplied by the first function, which is e to the negative 2x. Now we can factor out an e to the negative 2x from both of these terms. We can also then distribute the negative 2 through these parentheses and do some simplification. So here we are after factoring out the e to the negative 2x. We have e to the negative 2x, that's getting multiplied by everything. Here in parentheses, we have negative 2 times 3f of x, and negative 2 times 2f prime of x, and we have 3f prime of x, and we have 2f double prime of x. So now let's just go ahead and combine like terms. We can combine these f primes, and it looks like that's it. Negative 4f prime of x plus 3f prime of x is negative 1 f prime of x. And so now we can see that indeed this second derivative of g matches what we were supposed to get in the question. E to the negative 2x times negative 6f of x minus f prime of x plus 2f double prime of x. Now, to determine if g has a local maximum at x equals 0, we will determine its concavity by plugging x equals 0 into this second derivative. What is g double prime of 0? Well, when we plug 0 into the exponential, that's just going to give us 1, so let's not worry about that. F of 0, we know, is equal to 2, so negative 6 times f of 0 is going to be negative 12. Then we have to subtract f prime of 0. F prime of 0 is negative 3, so if we subtract that, we are adding 3. Finally, we have to add 2f double prime of 0. F double prime of 0 is 0, so 2f double prime of 0 is just 0. So this is negative 12 plus 3, which is negative 9. Thus, we have a concave down function here at x equals 0, and so indeed we have a
maximum. And there is my written out conclusion, and that completes our solution to problem 4 from the 1999 exam.
This is problem 6 from the 2008 AP Calc AB exam. So this would have been the final question, part of the no calculator section. Let's read it. Let f be the function given by f of x equals ln x over x for all x greater than 0. It's nice enough to just give us the derivative here, so we don't even have to use the quotient rule to find that. And part A is this. Write an equation for the line tangent to the graph of f at x equals e squared. So, pretty straightforward to write the equation of a tangent line. Easiest way to do it is usually point-slope form. And we do that like this. Y minus the y-coordinate. The y-coordinate is found by just plugging the x-coordinate into the function. So we'll just plug e squared, because remember, that's the x-coordinate. We'll plug that into the function. And this equals the slope, which we'll find by plugging e squared into the derivative, multiplied by x minus the x-coordinate. All right, let's just evaluate these pieces, and we will be done. F of e squared, what is that? Well, we just plug e squared into our function. So it's ln of e squared divided by e squared. Natural log of e squared is just 2 because ln and e cancel out. So this is just 2 over e squared. As for the derivative, f prime of e squared, which is going to give us our slope, we've got to plug e squared into this. Now, same thing, ln of e squared is just 2, so this is going to be 1 minus 2 in the numerator, which is negative 1, divided by e squared squared, which is e to the 4 in the denominator. So this is negative 1 over e to the 4. All right, now having evaluated the pieces, our tangent line equation in point-slope form is y minus the y-coordinate, which we found to be 2 over e squared, equals the slope, which we found to be negative 1 over e to the 4, multiplied by x minus the x-coordinate. The x-coordinate, of course, is e squared. And that is part A. Moving on then to part B. Find the x-coordinate of the critical point of f. So the wording suggests there is one critical point, and we have to find its x-coordinate. Determine whether this point is a relative minimum, a relative maximum, or neither for the function, and justify our answer. We can determine if the critical point is the location of a maximum or minimum by seeing if the derivative switches sign, and if so, how it switches sign. So let's get into this. This is part B. The first part of the question is to find the x-coordinate of the critical point of the function. The critical point of a function is where the derivative either doesn't exist or is equal to 0. At this point, we would use the quotient rule to find the derivative if it hadn't already been given to us. The question already told us the derivative is 1 minus ln x over x squared. Now, you may think x equals 0 here would be a critical point because the derivative would not exist at x equals 0. But in fact, that's not a critical point because x equals 0 isn't even in the domain of the function. The function isn't defined at x equals 0, so this would not be a critical point. So then, what is a critical point of this function? Well, we've got to see where the derivative equals 0. The derivative is going to equal 0 when 1 minus ln x is equal to 0. This, of course, means that 1 equals ln x, and the natural log of what is equal to 1? Well, that, of course, is just e. This means that e must equal x. Then the question is this the location, this critical point, is this the location of a maximum or a minimum or neither? We have to think about what happens to our derivative as we pass from x being less than e to being greater than e. Well, let's think about this. When x is less than e, we know that the natural log of x has to be less than 1. The natural log is going to be less than 1 because you need to raise e to fractional powers to get something that's less than e. And if ln x is less than 1 in this case, then 1 minus ln x is positive. So we could say to the left of e, the derivative is positive. Now what happens to the right of e when x is greater than e? When x is greater than e, of course, ln x is greater than 1, because e needs to be raised to powers bigger than 1 to get something bigger than e. And if ln x is greater than 1, then 1 minus ln x is going to be less than 0. I should point out we're only discussing the numerator because x squared is always positive, so will have no effect on the sign of the derivative. So yes, the derivative does switch signs when x equals e. How does it switch signs? Well, to the left of e, the derivative is positive, so our function is increasing. And then to the right of e, the derivative is negative. It is decreasing. Thus, at x equals e, we have a maximum. The derivative goes from positive, so an increasing function, to negative, so the function is decreasing. Sorry, I just hit the mic. And there our reasoning is written out. F of x has a relative maximum at x equals e, the critical point, because f prime of x, the derivative, switches from positive to negative at that point. Let's move on then to part C. The graph of the function f has exactly one point of inflection. Find the x-coordinate of this point. A point of inflection, you should recall, is a point where a function changes concavity, which means its second derivative switches signs. So for part C, we are going to have to find the second derivative, and perhaps this is why they gave us the first derivative. There's no need to test our knowledge of the quotient rule twice. We'll have to use the quotient rule once in order to get the derivative of the derivative, so we can find the second derivative and see if there are any points of inflection. Or in fact, we know there is a point of inflection, we just have to find it. Because we're looking for where this second derivative switches signs, and in order for it to switch signs, it's gonna have to pass 0. So this is a lot like finding critical points and using that first derivative. Okay. Since the first derivative we know is 1 minus ln x over x squared, it's pretty straightforward to apply the quotient rule to find the second derivative. You have to start with u prime v, the derivative of the numerator times the denominator. The derivative of the numerator is just minus 1 over x. So we'll have minus 1 over x. That's the derivative of the numerator. And then we have to multiply by the denominator. So multiply by x squared. And then subtract v prime u, the derivative of the denominator, multiplied by the numerator. The derivative of the denominator is 2x, and the numerator is 1 minus ln x. All right, so that is the numerator based on the quotient rule. And of course, all of this is over v squared, the denominator squared. And x squared squared is x to the 4. So that is our second derivative. And then we're just doing some simplification. Negative 2x times negative ln x is positive 2x ln x. So move that to the front. Then we have minus 2x right here. And over here, a factor of x cancels out. This is actually just minus x. So between the minus 2x and the minus x, we have minus 3x. And of course, x to the 4 is still in the denominator. Now, everything here has a factor of x, so we can actually cancel an x out of everything. And so this simplifies to 2 ln x minus 3 divided by x cubed, and that's not so bad. Necessarily, at a point of inflection, the second derivative has to change signs, and thus it's got to hit 0. So we'll set the numerator equal to 0, because that's the only way the second derivative can equal 0, is if the numerator equals 0. So 2 ln x minus 3 equals 0, and then we just have to solve this. Add 3 to both sides, so 2 ln x equals 3. Divide both sides by 2, so ln x equals 3 halves. And then exponentiate both sides, right? Put it all in a power of e. E and ln cancel out, and we just have x equals e to the 3 halves. And yes, indeed, this is a point of inflection, because when x is less than e to the 3 halves, ln x is going to be less than 3 halves, and thus 2 ln x is going to be less than 3, so this will be negative. But once x passes e to the 3 halves, this is going to be positive because this term is going to be bigger than 3. Of course, the x cubed here doesn't affect anything because when x is close to e to the 3 halves, x is positive, and so x cubed is also positive. This is the location of our one point of inflection where the concavity switches. Finally, on to part D, we are asked to find the limit of f of x, the limit of this function, as x approaches 0 from the right. We, of course, can't approach 0 from the left because the natural log is not defined for negative values. We'll also not be able to just plug 0 in because log's not defined at x equals 0, and we can't divide by 0 either. And maybe we can sneak part D in right here. Here's part D, the limit as x approaches 0 from the right of our function, and our function is ln x over x. This is actually pretty straightforward. Let's just think about what happens here. If we approach 0 from the right on the natural log of x, the natural log, you could sketch it real quick, it veers off to negative infinity as x approaches 0 from the right. And x, of course, is just a line. It's looking like that as we approach 0 from the right. So we're dividing by these small positive numbers, and the numerator is massive negative numbers. So this is definitely negative infinity. Again, that's because as we approach 0 from the right on the natural log, we get really big negative numbers. You need to raise e to really big negative powers in order to get really small positive numbers, those numbers that are close to 0. Meanwhile, we're dividing these massive negative numbers by very small positive numbers in the denominator, which only makes them bigger, but doesn't change their sign. So the limit is negative infinity, and according to the AP College Board scoring guidelines for this question, you could also simply say that the limit does not exist, because going to negative infinity is just a special type of not existing. And that completes our solution to the final question from the 2008 AP Calc AB exam. This is free response question 5 from the 2008 AP Calc AB Form B exam. Let's read it. Let g be a continuous function with g of 2 equal to 5. The graph of the piecewise linear function g prime, the derivative of g, is shown here from x equals negative 3 up to x equals 7. Part A says find the x-coordinate of all points of inflection of the graph of g of x for x between negative 3 and 7, and justify our answer. A point of inflection is somewhere the second derivative switches signs, which means it's somewhere the first derivative goes from increasing to decreasing. Looking at the graph, we see the first derivative, remember that's what the graph is, it's g prime. The graph goes from increasing to decreasing right here at x equals 1, and it goes from decreasing to increasing right here at x equals 4. At both of those places, the second derivative must change sign because the first derivative has a change in increasing, decreasing behavior. So there is our answer for part A. G prime changes from increasing to decreasing at x equals 1, and from decreasing to increasing at x equals 4. So those are the 2 points of inflection. Moving on to part B. Part B says find the absolute maximum value of g on the interval from negative 3 to 7 and justify our answer. To have an absolute maximum, the function must go from increasing to decreasing, which means the derivative must go from positive to negative. We see the derivative goes from positive to negative at the point x equals 2, and that is it. However, looking for extreme values, we do also need to check the endpoints at x equals negative 3 and at x equals 7. Now this is just the graph of the derivative, so how are we going to use this to find values of the function to see which one of these candidates actually is the location of the absolute max? Well, we'll be able to do that by using integrals. We can integrate the derivative, and we also have this known point for the function g. We know that g of 2 is 5, so we can integrate from there and find more values of g. So here are our candidates, the endpoints of the interval -3 and 7, and that one point where g prime changes from positive to negative at x equals 2. So let's assess the values of g at these points, beginning with g of -3. We'll be able to see which one's the maximum once we check all of these values. To find g of -3, we'll take the value of g we know, that's g of 2, and then just accumulate g's rates of change, so the derivative g prime of x, from that known point of 2 backwards to the desired point of -3. We can compute this integral, of course, using area calculations and the provided graph. G of 2, to begin with, we know is 5, so this is going to be 5 plus, let's go ahead and calculate this integral. The integral of g prime from 2 to -3 is the area under the curve from here to here. So that's all of this area. And also, we need all of this area. So this is just a couple triangle area calculations. Now remember, we're moving backwards, right? We're going from 2 to -3. So this area that looks positive because it's above the x-axis, we actually need to count as negative because we're moving backwards. And this area that looks negative because it's below the x-axis, we actually need to count as a positive, again, because we're moving backwards. All right, so what are the areas of these triangles? Well, it's just 1/2 base times height. So beginning with this one, which will make negative, it's -1/2. The base goes from -1 to 2. So that is a base of 3. And the height, well, it just goes up to 1. So the height is 1. And then we need to add, we're going to make this area positive. That's going to be 1/2 times the base. The base goes from -1 to -3. So it's a base of 2. And then multiply by the height, which is -4. But again, we want this area to be positive, so we're going to multiply by a height of +4. Another way to think about this is that the base is actually -2 because we're moving back 2, and the height is actually -4 because it's down 4. And so you can see those negatives cancel out, and it just remains positive. So here's the value of our integral with those areas of the triangles we just calculated. Let's go ahead and simplify this. This is 5, which is the same as 10 halves. And then here we have -3 halves. And then here we have +8 halves. So in total, this is 15 halves, or 7.5. All right, now as for g of 2, that is given to us. We know that g of 2 equals 5. So the only thing left to check is g of 7, which we can find just like we found g of -3. We will find it by beginning g of 2 and then integrating the rates of change, so g prime of x, from x equals 2 to the desired point at x equals 7. So let's head back up to our graph and find this integral using some geometry. We need the area under the curve from 2 to 7, so that area there, as well as this area. Now we are moving forward, so the areas should be positive and negative in the ways that we would expect. This first area, underneath the x-axis, will be counted as negative. What is its area? Well, it's 1/2 times the base. The base is 1, 2, 3, 4, multiplied by the height, which is -2. And then we need to add the area of this little triangle here. It's 1/2 multiplied by the base of 1 multiplied by the height of 1. Now we can go ahead and just simplify this real quick before we finish up the integral. 1/2 times 4 times -2 is -4. And then 1/2 times 1 times 1 is just +1/2. So this is -3.5. So back down here with our integral, g of 2 we know is 5. The integral we just found is -3.5. So in total, g of 7 is positive 1.5. Now remember, the question for part B was to find the absolute maximum. After having checked all the candidates, we see the absolute maximum is 7.5, which occurs at x equals -3. So I'll just write that, a max of 7.5, which occurs at x equals -3. Moving on then to part C. Part C says, find the average rate of change of g of x on the interval from -3 to +7. The average rate of change of g of x can be found by looking at the slope of the secant line through the endpoints. Thankfully, we just found all the information we need in order to figure this out. So let's put part C down here, and we will refer back to our work in part B. The average rate of change of g from -3 to +7 is g of 7 minus g of -3, that's the change in g over this interval, divided by the amount of distance that is passed. So 7 minus -3. That's just the width of the interval. G of 7 we figured out is 1.5. So we'll have 1.5 minus g of -3 we figured out is 7.5. So 7.5. And then divide by 7 minus -3 is 10. That's the interval width. 1.5 minus 7.5 is -6. So this is -6 over 10, which equals -3/5, or -0.6. And that is the average rate of change of g over the interval in question. Finally, part D. Find the average rate of change of g prime of x. So we just found an average rate of change of g, but part D is asking for the average rate of change of g prime on this interval from -3 to 7. And then we need to answer this. Does the mean value theorem applied on the interval from -3 to 7 guarantee a value of c between -3 and 7 such that the derivative of the derivative, g double prime of c, is equal to this average rate of change? Why or why not? Let's just start with the average rate of change of g prime. The average rate of change of g prime, just like with g, is just going to be the values of g prime at the end minus the beginning divided by the interval width. So we need to calculate g prime of 7 minus g prime of -3, that's going to be the change in g prime, and then divide by the interval width. 7 minus -3, of course, we already know that's 10. Now these values, g prime of 7 and g prime of -3, we can just grab from the graph. G prime of 7 is 1, and g prime of -3 is -4. So we have 1 minus -4 over 10. 1 minus -4 over 10. This is 5 over 10, which is 1/2. Now, does the mean value theorem guarantee that the second derivative takes on this average rate of change of the first derivative, this value of 1/2, at some point? The answer is no, because the mean value theorem only applies to differentiable functions. We see that the derivative, g prime, is not differentiable on the entire interval in question. For example, we have a corner right here where the slope of g prime suddenly changes. That means right here is a point of non-differentiability. G prime is not differentiable on this whole interval. It has several sudden changes in its slope. So the mean value theorem does not apply. It may be the case that the second derivative takes on a value of 1/2 at some point, but the mean value theorem certainly does not guarantee it. And there is our statement for that. The mean value theorem does not guarantee the existence of a value c so that g double prime of c equals the average rate of change, which we found to be 1/2, because g prime is not differentiable on the entire interval. There are several points where it fails to be differentiable. And that completes our solution to free response question 5 from the 2008 exam. Next are problems involving tables and Riemann sums. For these problems, make sure you read those tables very carefully so that you understand exactly what information is being presented to you. You might also find it helpful to sketch a rough picture of a function that agrees with the information in the table. In this way, you encode the table information in a picture which can be easier to read than looking at a table. Good luck. This is free response question 3 from the 1998 AP Calc AB exam. You can see we are given a graph which is showing us the velocity of a car with respect to time. We also have a table telling us exactly what some of the velocity values are at given times. Let's read the question. The graph of the velocity, v of t, in feet per second of a car traveling on a straight road for t between 0 and 50 is shown above. A table of values for v of t at 5-second intervals of time t is shown to the right of the graph. Part A says, during what intervals of time is the acceleration of the car positive? The acceleration being positive means that the velocity should be increasing. We need to give a reason, of course, for our answer. So this is the graph of the velocity. We need to ask, when is this increasing? That's going to be when the acceleration is positive, because acceleration is the derivative of velocity. So looking at the velocity, we see that it is actually increasing quite a bit. It's increasing all the way up to here, where t equals 35. That whole time, the velocity is increasing. And then it's also increasing, it appears, from 45 to 50. It is only here, between 35 and 45, where the acceleration is negative because the velocity is decreasing. All right, so let's write our answer for part A. So here is our answer for part A. Acceleration is positive on the interval from 0 to 35 and from 45 to 50, because this is where v of t, the velocity, is increasing. Whether or not you chose to include the endpoints in these intervals would not affect how your answer is scored for this question. Now, part B. Find the average acceleration of the car in feet per second squared over the interval from 0 to 50. The average acceleration is the average rate of change of the velocity. So we need to find the average rate of change of the velocity, which is like the slope of a secant line. In particular, it's the slope of the secant line from t equals 0 to t equals 50. So that line would look something like this, and we're looking for the slope of this line. That will tell us the average rate of change of the velocity over this interval, which is the average acceleration, because acceleration is change in velocity. So for part B, like we said, average acceleration that we're looking for is the average rate of change of velocity. So how do we find it? Well, we need to take the velocity at t equals 50. That's the terminal velocity, or I should say the velocity at the end of the interval in question. And then subtract the initial velocity, v of 0. Then just divide by the change in time over this interval, so 50 minus 0. Now v of 50, we can see from the table, is 72. V of 0 is 0. So this is just 72 minus 0 over 50 minus 0. 50 minus 0, of course, is 50, and 72 minus 0 is 72, so this is 72 divided by 50. And you could use a calculator to find that this is about 1.44 feet per second squared. Now on to part C. Part C says find one approximation for the acceleration of the car in feet per second squared at t equals 40, and show the computations we use to arrive at our answer. Given the information we have, there are several different approximations we could use for the acceleration at t equals 40. Remember, acceleration is the change in velocity. So to approximate acceleration, we need to look at an average rate of change in velocity on an interval that contains t equals 40. So the options we could use are from 35 to 40, or we could use from 40 to 45, or we could actually have 40 be the middle of the interval and go from 35 to 45. Any of those would be valid answers. We could use t equals 40 as an endpoint, or we could use it as a midpoint. For our solution, let's use an approximation going from 35 to 40. So the acceleration at t equals 40, well, it should be about the average rate of change of the velocity from t equals 35 to t equals 40. If we had the information to get a closer approximation that was a little bit more narrowed in on t equals 40, we would. And we could use the graph, perhaps, to get a closer approximation. But we're going to use the table. That is what the College Board answer key expects you to do. So let's go ahead and do that. For t equals 35, the velocity is 81. And for t equals 40, the velocity is 75. So we have 75 minus 81, that's the change in velocity, divided by the change in time, so 40 minus 35. That's a 5-second interval. This turns out to be negative 6 over 5, which is negative 1.2 feet per second squared. Again, this is an approximation of acceleration at t equals 40. So we use the information that we have, getting us as close to t equals 40 as possible, and looking at what the rate of change in the velocity was, because that is acceleration. Let's move on to part D. Approximate the integral from 0 to 50 of the velocity function with a Riemann sum using the midpoints of 5 subintervals of equal length. So we're going from 0 to 50, and we're using 5 subintervals, so they'll each have to have a length of 10. Then, using correct units, explain the meaning of the integral. So we are looking for the integral from 0 to 50 of the velocity function v of t dt, and we are going to approximate this using a Riemann sum, and we have to use a midpoint Riemann sum specifically, and we're using 5 subintervals of equal length, of course. So let's use our table to break this down. We're going from 0 to 50, and we need to use 5 subintervals, so each subinterval should have a length of 10, since they all need to be equal. So we can go from 0 to 10, and then we can go from, let me write that differently, 0 to 10, and then we can go from 10 to 20, and then we can go from 20 to 30, and then from 30 to 40, and then from 40 to 50. And you can see what our midpoints will be, the points that we use to determine the heights of the rectangles. We have 5 as the midpoint, 15 is the midpoint, 25, 35, and 45. So the heights of our rectangles are 12, 30, 70, 81, and 60. So the areas of all these rectangles will be base times height. The base of each one is 10. Each rectangle will have a base of 10 because these intervals all have lengths of 10. And then the heights are the highlighted numbers. So let's just jot this information down, and instead of multiplying each one individually by 10, let's imagine we factor the 10 out. So we just have 10 multiplied by the sum of the heights. 12 plus 30 plus 70 plus 81 plus 60. Here that information is back with our integral, and if you do this addition and multiplication, this equals 2,530, and the units are feet because we are accumulating a change in feet because the velocity is in feet per second. If you accumulate feet per second over a span of seconds, you get accumulated feet. More specifically, in this case, these feet are describing the change in the car's position. From t equals 0 to t equals 50, the change in the car's position is about 2,530 feet. This is displacement. When you accumulate velocity, you get displacement. In this case, 2,530 feet is actually how far the car traveled as well. It's not just the change in position, it's actually the total distance traveled. That's only the case here because the velocity is never negative. If the velocity were negative, then when we integrate it, we wouldn't necessarily get the total distance traveled, we would just get the change in position. But in this case, because the velocity is positive the whole time, we get the change in position, which is equal to the distance traveled. And that completes our solution to free response question 3 from the 1998 AB exam. This is problem 3 from the 2005 AP Calc AB exam. It is part of the graphing calculator section. Let's read it. A metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature, T of x, in degrees Celsius of the wire x centimeters from the heated end. So for example, 5 centimeters from the heated end, the wire has a temperature of 70 degrees Celsius. The function t is decreasing, which we see in the table, and it is twice differentiable, which means its derivative is differentiable, and thus its derivative is also continuous. Let's read part A. Estimate t prime of 7. Show the work that leads to your answer and indicate units of measure. So t, remember, is the temperature of the wire, x centimeters from the heated end. So t prime is going to be the rate of change of the temperature. And here we are asked to estimate it. Estimate t prime of 7. We can do that with a secant line, or more precisely, the slope of a secant line.
In other words, we need to find the slope between these 2 points because x equals 7 is between x equals 6 and x equals 8. So the best approximation we're going to be able to get with this data, the best approximation of the rate of change of t at x equals 7 will be the rate of change in this space near x equals 7, the rate of change from x equals 6 to x equals 8. To calculate that average rate of change over that interval from 6 to 8, we just need to take the change in the temperature and divide by the change in distance. So we have that t prime of 7 is approximately the average rate of change from x equals 6 to x equals 8, and that is 55 minus 62, that's the change in temperature, and divide by 8 minus 6, the change in distance. This is equal to -7/2. But remember, we also need to indicate units of measure. In this case, this is how the temperature, degrees Celsius, is changing as we travel more centimeters across the wire. So this is -7/2 degrees Celsius per centimeter. When x equals 7, the temperature of the wire is changing by about -7/2 degrees Celsius per centimeter. As we go forward another centimeter, we're dropping about -7/2 degrees. Moving on to part B. Write an integral expression in terms of t of x for the average temperature of the wire. For a continuous function like t of x, to find the average, we just need to add up all the values from 0 to 8, which we do with an integral, and then divide by the length of that interval, which is 8. Then we need to estimate the average temperature of the wire using a trapezoidal sum with the 4 subintervals indicated by the data in the table. So the interval from 0 to 1, from 1 to 5, 5 to 6, and 6 to 8. So we'll have 4 trapezoids for that. And again, we'll need to indicate units of measure. All right, let's start with the integral expression for the average temperature of the wire, and we'll do that down here. This is just a basic definition you should know. In order to find the average temperature of the wire, we need to integrate the temperature over the applicable interval, which is from 0 to 8, from the heated end to the other end. We need to add up all those temperatures, and then we have to divide that by the interval length. So we'll just put a 1 over 8 in front. That's dividing by 8. And that is an integral expression in terms of t of x for the average temperature of the wire. All right, now we're going to estimate this using a trapezoidal sum. So I've just copied the integral representing the average temperature of the wire, and this is approximately 1/8 times our approximation for this integral. We're going to approximate that integral using a trapezoidal sum. So let's come up to this data and recall the area of a trapezoid and how it applies in this situation. I'll just do a little sketch representing this situation. The first interval is from 0 to 1, so we can kind of sketch this base that has a length of 1. On the left, the trapezoid goes up to a height of 100, and on the right, it goes up to a height of 93. Since this function is just decreasing, let me make this highest value of 100 a little bit bigger. All right, and then this other side goes up to about 93. Okay, so we have a trapezoid that looks something like that. The next trapezoid goes from 1 to 5. I'll do that in a different color, say blue. So maybe we go from 1 to 5, and this thus would have a length of 4. Going from 1 to 5 means this base length is 4. On the left, again, it's going up to 93. And on the right, it's going up to 70. So maybe right there. It's not perfectly to scale, but it's a decent sketch. And we have that trapezoid. The next trapezoid goes from 5 to 6, and the right side goes up to 62. And so on. I'll sketch the rest of this. So that's just a rough sketch of our situation. Remember, each of these numbers on the bottom is representing the length of these intervals. In the context of trapezoids, these interval lengths are actually the heights of the trapezoids. The bases of the trapezoids are these vertical sides, 100 and 93, 93 and 70. 70 and 62. Those are the parallel sides of the trapezoids, and that, by definition, is the base of the trapezoid, or the two bases. To find the area of a trapezoid, we just need to take the average of the bases, b1 plus b2, take the average, so divide that by 2, and multiply that by the height. So we need to find the areas of all these trapezoids using that formula and add them all together. For example, the area of this red trapezoid is the average of the bases, so 100 plus 93, those parallel sides are the bases. Take the average, so divide it by 2, and then multiply by the height, which is the interval length, which is 1. This blue trapezoid we calculate the area of similarly. Average the bases, so 93 plus 70, divide by 2, because we're taking the average, and multiply by the height, which is 4, the interval length. And we can proceed with the rest of these areas in a similar manner. All right, there it is after writing all of the areas out. And there's another look at the sketch and the table, just so you can make sure you understand where everything is coming from here. Now, this here is our approximation for this integral using a trapezoidal sum. So when we multiply that by 1/8, we're going to get an approximation for the average temperature of the wire. And this turns out to be about 75.6888 degrees Celsius. And that completes part B. Let's move on to part C. Find the integral of t prime of x dx from 0 to 8 and indicate the units of measure. Then we need to explain the meaning of this in terms of the temperature of the wire. At a glance, we can say, well, this is the integral of the rates of change of the temperature. When we accumulate or integrate the rates of change of the temperature, we're going to get the total change from 0 to 8. But before we write that interpretation out, let's actually find this integral. The integral of t prime of x from 0 to 8 is very straightforward. If we integrate t prime, we are just going to get the original function t of x, and we're evaluating this from 0 to 8. So the value of the integral is t of 8 minus t of 0, and we can find those values by consulting the table. T of 8, we see, is 55, and t of 0 is 100. So the value of this integral is 55 minus 100, which is negative 45. We should specify this is degrees Celsius, so that is our value of the integral. And then here is our interpretation of what this means. This means that the temperature of the wire drops 45 degrees Celsius from the heated end at x equals 0 to the other end at x equals 8. That's because this is the accumulation of all the rates of change, so we get the total change. Let's move on to part D. Are the data in the table consistent with the assertion that the second derivative of t is positive for every x in the interval from 0 to 8? And of course, we should explain our answer. So for the second derivative to be positive means that this whole time, the first derivative, t prime, should be increasing. Now, we know the derivative t prime is negative. The temperature t is decreasing, so the derivative is negative. So for the derivative to be increasing, it should be getting less negative, which means that even though the temperature is decreasing, it should decrease by less and less as x goes on, and that should always be true. That's what it would mean for the second derivative to be positive. The first derivative is increasing, the first derivative happens to be negative, so it should be getting less negative, and the amount that our function is decreasing should be getting less extreme, because the first derivative is getting less negative. This is rather tricky, because we don't actually know any values of the second derivative, or any values of the first derivative. So how can we say that the second derivative is always positive, or that the first derivative is always increasing? Actually, we can use the mean value theorem to get a definitive answer to this question. Our function t is continuous and differentiable on this interval from 0 to 8. So the mean value theorem tells us that whatever the average rate of change is over some interval, that must be the same as the instantaneous rate of change at some point in that interval. If we look at the average rate of change from 1 to 5, the instantaneous rate of change must equal that average rate of change at some point in the interval. Using this, we'll be able to find 2 points that must exist where the derivative actually has decreased. And that's going to show that the second derivative can't always be positive. So let's check this out. What's the average rate of change from 0 to 1? Well, that would be 93 minus 100, which is negative 7, divided by 1 minus 0. So it would be negative 7. So the average rate of change from 0 to 1 is negative 7. Since that's the average rate of change, there must be some point from 0 to 1 where the actual derivative equals negative 7. Now let's look at this interval from 5 to 6. What's the average rate of change there? Well, let's write it down. T of 6 minus T of 5 divided by 6 minus 5, the average rate of change over this interval, is going to be 62 minus 70 divided by 1, the interval length. 62 minus 70 is negative 8. So this is just negative 8. So we can see the derivative has actually gone down. By the mean value theorem, there has to be some point in this interval from 5 to 6 where the derivative actually does equal that average rate of change, negative 8. So at some point, the derivative is negative 7, and at some other point in this interval, the derivative is negative 8. So at some point, it must decrease, which means it isn't always increasing, which means the second derivative isn't always positive. So no, the data in the table is not consistent with this assertion that the second derivative is always positive. And there is our reasoning written out. By the mean value theorem, there must be some point C1 from 0 to 1 such that the derivative at C1 is negative 7, and similarly a point C2 in the interval from 5 to 6 where the derivative is negative 8. And since our original function t is twice differentiable, we know that the first derivative must be continuous. Thus, it couldn't have just jumped from negative 7 to negative 8. It actually had to decrease somewhere. And so t double prime isn't positive for every x in that interval from 0 to 8. And that completes our solution to free response question 3 from the 2005 AP Calc AB exam. This is problem 3 from the 2007 AP Calc AB exam. This is part of the calculator section, so we may need our calculator for this problem. Let's read it. The functions f and g are differentiable for all real numbers, and g is strictly increasing. So it's not just that it doesn't go down, but it only ever goes up. The table above gives values of the functions and their first derivatives. You can see some f's, some f primes, some g's, some g primes, at selected values of x, 1, 2, 3, and 4. The function h is given by h of x equals f of g of x, a composite function, minus 6. Part A is to explain why there must be a value r between 1 and 3, such that h, this function, of r equals negative 5. This is a fairly straightforward question. We just need to use the intermediate value theorem, or IVT. I'll leave a link in the description to my lesson on the intermediate value theorem if you need to review that. The idea, though, is that h is a continuous function. Because f and g are continuous functions, we know that because they're differentiable, and differentiability implies continuity. So f and g are continuous, the composition of continuous functions is continuous, and subtracting a constant from a continuous function, well, you'll still have a continuous function if you do that. Okay, so h is continuous, which means what we need to do is look at h of 1, because remember, we're concerned about what happens between 1 and 3. We want to show that h must equal negative 5 at some point between 1 and 3. So we're going to look at h of 1, and we're going to look at h of 3. if we evaluate these correctly, what we're going to see is that one of these values will be less than -5, and one will be greater than -5. So -5 is an intermediate value, which must have been taken on at some point in the interval because h is continuous. It can't just skip over something. It has to hit all of those intermediate values. So let's evaluate h of 1 and h of 3 using the definition of h and our table of values. H of 1, by definition of h, is f of g of 1 minus 6. Looking at the table, we can see that g of 1 is 2. Then we need to plug that into the function f. So we're plugging 2 into f. F of 2, we see, is 9. So this should be 9 minus 6, which is positive 3. And then we'll do a similar process to evaluate h of 3. By definition, h of 3 is f of g of 3. Looking at the table, we see that g of 3 is 4. And then we need to plug that into f. And we see that f of 4 is -1. Thus, this is going to be -1 minus 6. Sorry, I forgot to write the minus 6 a minute ago. So this is -1, and then subtract 6. That's going to be -7. And so there is our conclusion. Since h is continuous, and h of 3 we found was -7, is less than -5, which is less than h of 1, we found to be 3. By the intermediate value theorem, there must exist, sorry I wrote the exists, there exists, a number r between 1 and 3, so that h of r is equal to -5. The function h must have passed -5 at some point, because between 1 and 3, it is less than -5, and then it becomes greater than -5. So it must have passed -5 at some number r between 1 and 3. Moving on to part B. Explain why there must be a value c between 1 and 3, such that h prime of c equals -5. In this case, we're trying to show that the derivative takes on a certain value, so for this, we're going to use the mean value theorem. The mean value theorem tells us that since h is a differentiable function, since it's a composition of differentiable functions, whatever the average rate of change is of h on an interval, in particular, right now we're interested in the interval between 1 and 3, whatever the average rate of change of h is on that interval, the derivative must equal that average rate of change at some point in the interval. So we need to calculate the average rate of change on the interval. To find the average rate of change of a function over an interval, we just need to take the change in the function, so h of 3 minus h of 1, how much did h change from 1 to 3, and subtract by the length of the interval, so 3 minus 1. Now, h of 3 we already found is -7, so we have -7 minus h of 1 we already found, that's 3. Divided by 3 minus 1 is, of course, a division by 2. So this is -7 minus 3, which is -10, divided by 2, which is -5. Look at that. And there is our conclusion. Since h is continuous and differentiable, we can use the mean value theorem, the MVT, which tells us since the average rate of change of h over this interval from 1 to 3 is -5, that means that there must exist a point c between 1 and 3 where the derivative of h at c is exactly -5. The instantaneous rate of change at some point must equal the average rate of change over the interval. All right, moving on to part C. Part C says let w be the function given by w of x equals the integral from 1 to g of x f of t dt. And we want to find the value of w prime of 3. So this might look kind of intimidating, but all we actually have to do here is use the fundamental theorem of calculus and the chain rule. Those things together tell us how to take the derivative of an integral function like this, which has a function in the bounds. So let's take the derivative, and then we'll plug 3 into the derivative to find w prime of 3. W prime of x equals The derivative essentially undoes the integration, but how it works is this. The upper bound needs to get plugged in, this upper bound, which is a function. So it's f of g of x. But then by the chain rule, we need to multiply by the derivative of that function. So we have to multiply by g prime of x. Then, to find w prime of 3, we can just plug that in and use our table. We know that g of 3 from the table is equal to, let's see here, g of 3 right there. It's 4. So this is going to be f of 4. And what is f of 4? F of 4 is negative 1. Okay, so this part here is negative 1. But remember, it's also getting multiplied by g prime of 3, which from the table we see is positive 2. All right, so that right there is positive 2. So w prime of 3 is negative 2, their product. Remember that the lower bound of this integral would just yield a constant, which is why taking the derivative makes that part totally go away, but this function in the upper bound does have an impact on the rate of change. So that's part C. Finally, the final part is part D. If g inverse is the inverse function of g, write an equation for the line tangent to the graph of y equals g inverse of x at x equals 2. Okay, to write the equation of a tangent line, we need a couple things, right? We need a point for starters. So let's jot down our point. We're going to need a point and a slope, of course. The point has an x-coordinate of 2, so let's put that there. What is the y-coordinate? Well, we want a line that's tangent to g inverse. So the y-coordinate should be g inverse of the x-coordinate, 2. Now, if we look at our table, we see that g has an output of 2 when x equals 1. G of 1 equals 2. By definition of an inverse function, since g of 1 equals 2, that means that g inverse of 2 equals 1. So to evaluate g inverse of 2, all I had to do was look at what input makes g give an output of 2. Then I know g inverse of 2 gives an output of 1. And so that's going to be my y-coordinate. Thus, I've got my point. Now I just need my slope. So I need to find the slope of g prime at this point. All right, now to find the slope, we're going to have to take the derivative of g inverse. It'd be helpful if you knew the formula for the derivative of an inverse function, but it's not the end of the world if you don't have that memorized. We can figure it out from scratch pretty easily. By definition of an inverse function, we know that g of g inverse of x equals x, because inverse functions cancel each other out. What we're going to do next is take the derivative on the left with respect to x, and the derivative on the right with respect to x. To take the derivative on the left, we have to use the chain rule. The outside function is g, so we have to start with g prime and leave the inside function g inverse unchanged. But then we need to multiply this by the derivative of the inside function. The inside function is g inverse of x, so we have g inverse of x prime, the derivative of the inside function. On the right, the derivative of x is just 1, and then remember, we're trying to find a formula for g inverse prime, so let's solve for g inverse prime by dividing both sides by g prime of g inverse of x. Again, ideally, you have this formula we're going to get memorized, but this is how you can figure it out if you don't have it memorized. All right, there's our formula for the derivative of g inverse, so we can use that now to find the slope of g inverse at this point. Let me write this part in orange. So now we are looking for g inverse of 2 prime, right? We want the slope where x equals 2. And we know that this is equal to 1 over g prime of g inverse of 2. And let's see, what is g inverse of 2? Well, we already figured that out. G inverse of 2 is 1, because g of 1 is 2. Okay, so coming back down here, g inverse of 2 is 1. So this is going to be 1 over g prime of 1. And what is g prime of 1? Going back to the table, we see that g prime of 1 is 5. So this should be 1 over 5. I'm going to have to move everything to the left a little bit so I have room for this. This is 1 over 5. And that inverse derivative formula really comes in handy. All right, so finishing the tangent line, we have a point, 2, 1. We just figured out the slope, 1 over 5. So we can go ahead and write the equation of the tangent line using point-slope form. Y minus the y-coordinate equals the slope multiplied by x minus the x-coordinate. And there you go. That is our answer to part D. And that completes our solution to free response question 3 from the 2007 AP Calc AB exam. This is free response question 5 from the 2014 AP Calc AB exam. Let's read it. The twice differentiable functions f and g are defined for all real numbers x. Values of f, f prime, g, and g prime for various values of x are given in the table above. So here we have a big table giving us some information about f, f prime, g, and g prime. We can see, for example, that the derivative of f evaluated at x equals -1 is 0. We also have some information about their signs on various intervals. We can see, for example, that g prime is positive between -1 and +1, which means that g is increasing on that interval. These sorts of table problems often involve a little bit more abstraction than usual. Really got to know your stuff. Let's read part A. Find the x-coordinate of each relative minimum of f on the interval from -2 to 3 and justify our answer. Now, if we're going to have a relative minimum on this interval, we're going to have to look at the critical points where the derivative is 0. We know the derivative isn't undefined anywhere in this interval because we're told that f and g are twice differentiable. So we can take the derivative. We got to see where's the derivative 0. And again, we're talking about f. Well, by looking at the table, we can see that the derivative is 0 when x is -1, and the derivative is 0 when x is +1. So how do we determine if these critical points are the locations of minimums or maximums or neither? Well, we have to think about the sign of the derivative. We see that the derivative goes from negative to the left of x equals -1 to still negative to the right of x equals -1. So the function is decreasing and decreasing, and then it flattens out a little, and then it continues decreasing. So this would not be the location then of a minimum or a maximum. Remember that we're looking for minimums. This would look something like this. The function's decreasing, flattens out, and then just keeps decreasing. On the other hand, this other critical point, to the left, the derivative is negative. The function is decreasing. And then to the right, the derivative is positive. The function starts increasing. So certainly at this critical point, where x is 1, we will have a relative minimum. F has a relative minimum at x equals +1, and that is the only one. So there's our answer. F has a relative minimum at x equals 1 because this is the only critical point where the derivative, f prime, changes from negative to positive. Let's move on then to part B. Explain why there must be a value c between -1 and +1 such that the second derivative of c, f double prime of c, equals 0. Now, we don't have information in our table about the second derivative, so we're not going to be able to use, say, the intermediate value theorem to say that the second derivative goes from negative to positive, so it must cross 0 at some point. We can't do that. But we do have information about the first derivative, f prime. We have some values of f prime. So what we're actually going to use is the mean value theorem. We know that f is twice differentiable, which means that its derivative, f prime, is also differentiable, and so it's also continuous. We can use the mean value theorem. Because we know that f prime is continuous on this closed interval, and also that it's differentiable, we can apply the mean value theorem to say that whatever the average rate of change of f prime is on this interval, its derivative, f double prime, must equal that average rate of change at some point on the interval. So what is the average rate of change of f prime on this interval? Well, what we have to do to find that is take f prime of the ending point on the interval, so f prime of 1, and then subtract f prime of the beginning point, negative 1. This tells us how much f prime changed on the interval, and then we have to divide by the interval length, which is 2, 1 minus negative 1. That's the interval length. That's going to tell us the average rate of change. Now, f prime of 1 and f prime of negative 1, we can check our table to see what those values are. F prime of 1, we know is, let's see, where is it? Right there. It is 0. And f prime of negative 1, we see, is also 0. Okay, so coming back down to our average rate of change calculation, we have 2 in the denominator, and in the numerator, we just have 0 minus 0. Of course, then this average rate of change is 0, just like we wanted, because remember, part B is to show that there's some value C where f double prime of C is 0. There must be, by the mean value theorem, some point C where this instantaneous rate of change equals the average rate of change. And there's our conclusion. By the mean value theorem, there has to be at least one value C on this interval where f double prime of C equals 0, because we see the average rate of change of f prime on this interval is 0, so there must be a point where the instantaneous rate of change of f prime, which is f double prime, is also 0. Moving on then to part C. The function h is defined by h of x equals the natural log of f of x. We want to find h prime of 3 and show the computations that lead to our answer. So this is just going to be a little bit of chain rule. Let's put part C over here. If h of x is ln of f of x, then let's just quickly find h prime. We have to use the chain rule, which begins with the derivative of the outside function. The outside function in this case is ln. The derivative of that is 1 over the input. We don't want to change the inside function, f of x, right? Leave that inside function alone. And then multiply by the derivative of the inside function. So in this case, that's f prime of x. That is h prime, which makes it fairly straightforward then to evaluate h prime of 3. H prime of 3 is going to be 1 over f of 3 multiplied by f prime of 3. Now, hopefully, all of these numbers are in our table. If we go up to the table, what is f of 3? F of 3, we see, is 7. That's over here. And the other value we needed was f prime of 3. And f prime of 3 is 1/2. So this calculation is simply 1 over f of 3, so 1 over 7, times f prime of 3, so times 1/2. So 1/7 times 1/2, which is 1/14. That's h prime of 3. Moving on to our final problem, part D. Evaluate the integral of f prime of g of x, g prime of x dx from -2 to 3. Now, if you don't really understand U substitution, this might look kind of intimidating. If you do understand U substitution well, this should look pretty trivial, because when you're trying to do a U substitution integral, what you're looking for is an inside function, like g of x, it's inside f prime in this case. You're looking for an inside function whose derivative is represented outside, like elsewhere in the integral. These are the sorts of situations where you want to use U substitution. In this one, we see ln x, and the derivative of ln x is this other thing, 1 over x. So this is a prime candidate for U substitution. This integral, we have sine of x squared. The derivative of x squared is 2x, which is just a multiple of 3x, which we see out here. Also a perfect candidate for U substitution. When you have an inside function and its derivative elsewhere in the integral, that's when you should be thinking U sub. And that's all this is. So here's the integral for part D rewritten. Let's proceed with the U substitution. We're going to let U, as usual, be the inside function, in this case g of x. And then we have that du equals g prime of x dx. And we see how nicely that substitution is going to work. What is this integral equal to then? Well, we have the integral of, let's worry about the bounds in a minute. This is the integral of f prime of g of x, but g of x is u, and g prime of x dx is du. So it's f prime of u du. Now, what about the bounds? Well, the bounds should be, let's see, u equals g of x. So if we're integrating with respect to u, the lower bound should be g of negative 2, and the upper bound should be g of positive 3. Before, it was x going from negative 2 to positive 3, but when x goes from negative 2 to positive 3, u goes from g of negative 2 to g of positive 3. So these are our bounds since we're rewriting this in terms of u. And we can evaluate these using the table. Let's go look at the table. G of negative 2 is, let's see, right here. G of negative 2 is negative 1. And g of positive 3 is right here. It's positive 1. So the lower bound is negative 1. The upper bound is positive 1. That works out pretty nicely. Here's our integral from negative 1 to positive 1, f prime of u du. And now the integral of f prime from negative 1 to 1 is just f of u evaluated from negative 1 to 1. The integral undoes the derivative. So this is going to equal f of 1 minus f of negative 1. And of course, we can consult the table to find these values. Going back to the table, f of 1 we see is 2 right there, and f of negative 1 is 8 right there. So this is going to be 2 minus 8. So with a little bit of u substitution, a little bit of fundamental theorem of calculus, we get the answer is negative 6. Pretty cool little u sub problem. And that completes our solution to free response question 5 from the 2014 AP Calc AB exam. Next up are problems on rates and accumulation. For these problems, recall that integrating a rate of change produces a net change. If we integrate velocity, we get the net change in position. Also, keep your eye out for units. A lot of these problems, or I should say most of them, request that you include units with many of your answers. Good luck. This is free response question 1 from the 2013 AP Calc AB exam. This is part of the calculator section. We will have to consult our graphing calculator a couple times throughout this problem. Let's read it. On a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by g of t equals 90 plus 45 cosine of t squared over 18, where t is measured in hours between 0 and 8. At the beginning of the workday, which is t equals 0, so that's not midnight necessarily, it's just the beginning of the workday, the plant has 500 tons of unprocessed gravel. That's like our initial condition for the amount of unprocessed gravel. During the hours of operation, so from t equals 0 to t equals 8, the plant processes gravel at a constant rate of 100 tons per hour. And remember, that function g of t is telling us the rate at which unprocessed gravel arrives. Now, part A is to find g prime of 5, the derivative of g evaluated at t equals 5. Using correct units, we should interpret our answer in the context of the problem. So it's really important to note here that g is already a rate. G is already the rate in tons per hour at which unprocessed gravel arrives at the gravel processing plant. So when we take the derivative of this to find g prime here for part A, that's going to be the rate of change of the rate of change. It would be straightforward enough to find the derivative of g on our own, but since we can use the calculator and we're going to have to evaluate the derivative anyways, let's just use the calculator to evaluate the derivative at 5, and then we'll worry about the interpretation. So over on my calculator, I'm going to press the math button, and then I'm going to press number 8. This is the derivative function. I'm taking the derivative with respect to x. What function am I differentiating? Well, I'm differentiating g, which is 90 plus 45 times cosine of t squared, but I'm just going to use x as a variable, divided by 18. And that is our function. Then at the end, we put where we want this derivative evaluated. We want it evaluated at 5. And we get our answer. It's about negative 24.588, we could say. Now, to interpret this, what does it mean that g prime of 5 is negative 24.588? Well, remember, g is the rate at which unprocessed gravel is arriving. So g prime is the rate at which the rate the gravel is arriving is changing. So this means the rate at which gravel is arriving is decreasing, because this is a rate of change of the rate of change. So how fast the gravel is arriving, that's decreasing 5 hours into the workday, and it is decreasing by about 24.588 tons per hour. And there is the interpretation written out. We have our units, tons per hour. We have the negative covered by the word decreasing, which is why you don't see a negative here. And we also have our interpretation of this being at t equals 5. That means we are 5 hours into the workday when this sentence applies, when the rate at which gravel is arriving is decreasing by 24.588 tons per hour. All right, let's move on to part B. Find the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. The workday goes from t equals 0 to t equals 8. This function g of t tells us the rate at which unprocessed gravel is arriving. So to find the total amount of unprocessed gravel that arrives during the workday, we're just going to have to integrate g of t from 0 to 8. That's like accumulating all of the rates of change of unprocessed gravel. So for part B, we just add up all of the rates of gravel arriving over the entire workday from t equals 0 to t equals 8. So that will give us our answer, and we'll go ahead and use the calculator to evaluate this integral. So again, I'll press the math button, and then this time press function 9, the integration function. Now we are integrating from t equals 0 to t equals 8. Or in this case, we'll use the variable x, so from x equals 0 to x equals 8. And now I just have to put in my function, which of course is g of t, so we'll type that into the calculator. That is 90 plus 45 times cosine of x squared divided by 18. And of course, we are integrating with respect to x. And we find this is about 825.551 tons of unprocessed gravel that arrive during the workday. Now, part C. Is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5 hours? And we need to show the work that leads to our answer. Now, of course, we know that unprocessed gravel is arriving at the plant during the entire workday, and we have the function that describes that. But we also know that gravel is being processed at a rate of 100 tons per hour. So to answer this question of whether or not the amount of unprocessed gravel is increasing or decreasing at time t equals 5, let's write a function for the amount of gravel at the plant and consider its derivative. So here for part C, I said we would write a function for the amount of gravel. I should have just said name a function. Say we call it A. The amount of unprocessed gravel at the processing plant is A. So then what is A prime, the change in the amount of unprocessed gravel? Well, certainly it would have to be G of T, the amount of unprocessed gravel that is arriving at the plant, but then minus 100, which is the amount of gravel being processed each hour. Then to answer part C, we have to figure out what A prime of 5 is. If this is positive, that means the amount of unprocessed gravel at the plant is increasing. If it's negative, then the amount of unprocessed gravel is decreasing. A prime of 5, of course, is going to be G prime of 5 minus 0. So all that we really have to determine is if the derivative of g is positive or negative at t equals 5. I'll just go ahead and erase the minus 0. We don't really need that. Let's open up the calculator. So to answer part C, we will plug t equals 5 into a prime. This, of course, is going to be g of 5 minus 100. Is this positive or is it negative? Well, let's open up the calculator and get a value for g of 5. So here again, I'll just type in our function, but plug in 5. So 90 plus 45 times cosine of 5 squared, so 25, divided by 18. And this is about 98.141. So A prime of 5 is going to be about 98.141 minus 100. This number, of course, is negative. It is less than 0. And this means that the amount of unprocessed gravel at the plant is decreasing 5 hours into the workday. And again, that's because we know that the derivative of the amount of unprocessed gravel at the plant is the rate at which unprocessed gravel arrives minus the rate at which it is processed. And when we plug in 5, we get a negative. So the amount of unprocessed gravel is decreasing at this time. Moving on to part D, the final part. What is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? And we need to justify our answer. Now, since we're talking about this workday, T is between 0 and 8, so we basically will have to conduct a candidates test. We'll have to plug in 0, plug in 8, and then use our derivative to find critical points, and if there are any critical points, we'll have to plug those in as well and see where the function is maximized. At what time is the amount of unprocessed gravel the highest? Now for part D, we will actually need to figure out what our function a of t, the amount of unprocessed gravel at time t, is. And that's pretty straightforward. The amount of unprocessed gravel at the plant at time t is 500, which is the starting amount of unprocessed gravel. That was given to us in the question that, what do we have right here? At the beginning of the workday, t equals 0, the plant has 500 tons of unprocessed gravel. So it's 500, that initial value, plus the integral of g of s minus 100, so that's the rate at which the amount of unprocessed gravel changes. We have to integrate that amount from 0 to t. That way we get the starting amount, 500, plus whatever the accumulated changes from 0 to t. That will tell us what the actual amount of unprocessed gravel is at time t. Take that starting amount and accumulate the change up to time t. Although again, this only applies on this closed interval from 0 to 8. Now we already know the derivative, a prime of t, is g of t minus 100, and we need to set this equal to 0 to find critical points. There are no critical points where the derivative doesn't exist because g of t exists for all values of t on this closed interval. There's no forbidden value that we can't plug into cosine. So to find the critical points where this derivative equals 0, we will plug it into our calculator. So I just pressed y equals to get here where I can put in a function, and then we can graph it and see where it hits 0 in the interval that we're interested in. So we've got 90 plus 45 times cosine of x squared, again we're just using x instead of t for convenience, divided by 18. That is g of t, but remember we also have to subtract 100. That's the rate at which gravel is being processed. All right, now let's press the graph button and take a look at the graph. I'll have to zoom out to make sure we can get a good view here, and let's scroll over to the positive x values, and here we can see is where it passes 0 on the interval we're actually interested in. It passes 0 again over here, but that's after t equals 8. That's after the end of the workday. That is not important for us. It's only this 0 that's important for us, where t is about 4.923. All right, now we have all of our candidates, the endpoints of the interval 0 and 8, and the one critical point we just found. We need to evaluate the a function, the amount of unprocessed gravel, at each of these times and see which one is maximum. A of 0, we already know that was given to us as 500. As for the other two, A of the critical point and A of 8, we are going to need our definition of A using the integral here in order to figure those out, and so we'll have to consult the calculator once more. All right, I did this calculation once, but forgot to subtract the 100. Now you can see in my calculator, I got the minus 100 in the integral, and our answer for the amount of unprocessed gravel at this critical point time is about 635.376 tons. And I can just press second entry in order to get this integral again and just go edit the upper bound. The upper bound now we need to change to 8 to find the amount of unprocessed gravel at t equals 8. And we get about 525.551 tons. So again, all of this was found using the function we wrote for the amount of unprocessed gravel at the plant at time t, and the logic behind this is that we're taking that initial amount of unprocessed gravel, 500 at t equals 0, and then adding the accumulation of the rate of change of unprocessed gravel from 0 to t, the time that we are interested in. All right, now we have evaluated our function a at all of the candidates. And thus we can make our conclusion. We see the maximum amount was 635.376. So our conclusion is that the maximum amount of unprocessed gravel at the plant during this workday was 635.376 tons, which occurred about 4.92348 hours into the workday. And that completes our solution for free response question 1 from the 2013 AP Calculus AB exam. This is free response question 1 from the 2016 AP Calc AB exam. This is part of the graphing calculator section. We will use a calculator a couple times throughout this video. Water is pumped into a tank at a rate modeled by W of t equals 2000 e to the negative t squared divided by 20 liters per hour for t between 0 and 8, and t is measured in hours. Water is removed from the tank at a rate modeled by R of t liters per hour, where R is differentiable and decreasing from t equals 0 to t equals 8. Selected values of the function r of t are shown in this table, and at time t equals 0, there are 50,000 liters of water in the tank. All right, part A is to estimate r prime of 2 and to show the work that leads to our answer and to indicate units of measure. Remember that r is the rate in liters per hour at which water is being removed from the tank. So in estimating r prime of 2, we're estimating how fast that removal rate is changing at t equals 2. Now, all we have are a few values of r of t. So in order to estimate r prime of 2, we're going to have to estimate the rate of change near t equals 2. The closest we can really get to that is looking at how r of t changes from t equals 1 to t equals 3. If we find the average rate of change from t equals 1 to t equals 3, that will give us the best approximation we could get for r prime of 2. Let's go ahead and put part A down here. We are trying to estimate r prime of 2. And we know that r prime of 2 is about, we need to do some division here, it's about the change in r from t equals 1 to t equals 3. So r of 3 minus r of 1, that's going to tell us how much r changed on that interval. And then divide by the width or length of the interval, so 3 minus 1. This tells us the average rate of change on the interval. The interval contains 2, so it's a rough approximation of the rate of change at t equals 2. R of 3 we know is 950, and R of 1 is 1190. So our numerator is 950 minus 1190. The denominator, of course, 3 minus 1, the interval length, is just 2. And this is negative 120. Don't forget, we also need units of measure. R, the original function R, was in liters per hour, so negative 120 liters per hour. But this is an estimation of the rate of change of R. So this is actually liters per hour. You could also write this as liters per hour squared. This is how fast the rate of change, that rate of removal, how fast that rate of removal is changing. All right, moving on to part B. Use a left Riemann sum with the 4 subintervals indicated by the table, so 0 to 1, 1 to 3, 3 to 6, 6 to 8, those 4 subintervals. Use this to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or an underestimate of the total amount of water removed? And give a reason for your answer. Okay, so if we look at the table up here, again, this is giving us values of R of t, a few values for how fast water is being removed at different times. If we were to integrate this function, R of t, from 0 to 8, that would accumulate all of those removal rates, and thus tell us how much water is removed in total. Now, we don't know what R of t is as a function exactly, so we can't actually do that. But we can approximate that integral using a left Riemann sum. And again, what we're approximating is the integral from t equals 0 to t equals 8 of our function r of t. So this is the integral of r of t dt from 0 to 8, and we're going to approximate it using a left Riemann sum. A left Riemann sum means that we're adding up rectangles whose heights are determined by the left endpoints of our intervals. So if this was an x-axis, for example, our first rectangle, starting at t equals 0, would have a height determined by this left endpoint. So it would be a height of 1340. So it would go up here to 1340, and it'd have a width of 1, because we're going from 0 to 1. So let's maybe draw it a little bit less wide. It has a width of 1, and it has a height determined by the left endpoint, so 1340. The next rectangle in our Riemann sum would be going from t equals 1 to t equals 3, and its height is determined by the left endpoint, 1190. The height of this rectangle is 1190, but the width is 2, because this interval width from 1 to 3 is 2. So that rectangle might look something like this. It's a little bit lower because its height is 1190, but it's twice as wide. So I'll put a 2 down there and an 1190 there. The third rectangle, I'll write in orange, is over this interval from t equals 3 to t equals 6. Its height is determined by the left endpoint because we're doing a left Riemann sum, so it goes down some, starting there maybe. And the width of this rectangle is 3 because it goes from 3 to 6. So let me sketch this. It starts at about 950. Its width is about 3. So maybe it looks something like that. Again, the height is determined by the left endpoint. And there's the last rectangle with a width of 2 from t equals 6 to t equals 8. Its height determined by the left endpoint of 740. So to find the approximation of the integral, we just have to add up the areas of all of these rectangles. The area of a rectangle is base times height. So that would be 1 times 1340 plus 2 times 1190 plus 3 times 950, and so on. Those are the areas of the rectangles, and these add up to 8,050 liters. So we would approximate that about 8,050 liters of water were removed from the tank from t equals 0 to t equals 8. But remember, we are not done, because part B also asks us to determine if this approximation is an overestimate or an underestimate of the actual total amount of water removed. And we're able to determine the answer to this question based on knowing that R of t is decreasing. So R of t, if we were to sketch it in, say, this reddish color on this same graph where we sketched the rectangles, because R of t is decreasing, it might look something like this. And so you can see that all of the rectangles are overestimates because they lie above the curve. Because it's decreasing, we know that this left Riemann sum is an over approximation. All right, moving on to part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So we need to consider how much water was in the tank to begin with, 50,000 liters, add in the amount that is pumped. Remember that W of t, this function's telling us how much water is pumped into the tank over this interval of time. And then we need to subtract the amount which is removed. And we know a rough approximation for that. That came from part B. About 8,050 liters are removed. So our answer for part C is going to be 50,000, the amount that was there to begin with, plus the accumulation of all the water that's pumped in from t equals 0 to t equals 8, minus the approximate amount that is removed. Again, this is just an approximation of the total amount of water at t equals 8. Now, to integrate W of t, this function here, from t equals 0 to t equals 8, we will crack open the calculator. So I'll press the math button to access my functions, press 9 for the integration function. We are integrating from 0 to 8. The function that we are integrating is W of t, which is 2,000 times e to the negative. We'll use x as our variable for convenience, so negative x squared divided by 20. And this integral is taken with respect to x, and this is about 7,836.195. That's how much water is pumped into the tank during this time. So we have 50,000 plus this integral was about 7,836.195 minus that water that's removed, 8,050. This turns out to be about 49,786 liters of water in the tank at time t equals 8. All right, moving on to part D. For t between 0 and 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So to answer this question, we have to consider the amount of water being pumped into the tank, W of t, minus the amount of water that is being removed, which is R of t. That difference should be 0 at some point between t equals 0 and t equals 8 in order for the functions to be equal. In order for the rate at which water is being pumped in and removed to be the same, their difference needs to be 0. Now, the difference of those functions is continuous and differentiable because we know that both w is differentiable. We can look at it. We know that's a differentiable function. And r of t is differentiable because we're told as much. So we can apply the intermediate value theorem. And here is all of that logic written out. W of 0 minus R of 0, the initial difference in the pumping and removing function, is 2000 minus 1340, which is positive. We know this because if we just plug 0 into W of t, we're going to get 2000 times 1. So that's 2000. And we're also given that R of 0 is 1340. So that's where those numbers come from. We see the initial value of this difference is positive. The ending value, though, W of 8 minus R of 8, is negative. We know that because we can just plug 8 into W of t. Just do that on the calculator. You get about 81.5. And then subtract 700, that was given to us. R of 8 is given as 700. Clearly, this is negative. So this difference between W and R, the pumping in rate and the removal rate, was initially negative. But at the end, it was initially positive. But at the end, it was negative. Because this difference is continuous on the interval, we know that the intermediate value theorem guarantees at least one time t between 0 and 8 for which the difference of the functions had to equal 0. It was positive, then it was negative, so it must have crossed 0 at some point, and at that point in time, W of t, the pumping in rate, was the same as R of t, the removal rate. So at this time t, the rate at which water is pumped into the tank equals the rate at which water is removed from the tank. That's how you solve this part using the intermediate value theorem. And that completes our solution to free response question 1 from the 2016 AP Calc AB exam. This is free response question 1 from the 2022 AP Calc AB exam. It is part of the graphing calculator section. Let's read it. From 5 a.m. to 10 a.m., the rate at which vehicles arrive at a certain toll plaza is given by this function, a of t, where t is the number of hours after 5 a.m., so t equals 0 is 5 a.m. A of t is measured in vehicles per hour, that's the rate at which the vehicles are arriving. Traffic is flowing smoothly at 5 a.m. with no vehicles waiting in line. Part A says, write, but do not evaluate, an integral expression that gives the total number of vehicles that arrive at the toll plaza from 6 a.m. to 10 a.m. And it even gives us the appropriate t values there from t equals 1 hour after 5 a.m., that's 6 a.m., to t equals 5 hours after 5 a.m., which is 10 a.m. Now, an expression for the total number of vehicles that arrive in this time is going to require us to accumulate the rates at which the vehicles arrive. We just have to integrate that rate of arrival from t equals 1 to t equals 5. So for part A, the integral expression we're looking for is just the integral of the rate at which vehicles are arriving from t equals 1 to t equals 5. If we want to, we could rewrite this to be a little more specific by just replacing a of t with what the function actually is, since it's given to us, as 450 times the square root of, let's just double check, square root of sine of 0.62t. So sine of 0.62t, integrating, of course, with respect to t. So this integral, if we were to calculate it, would give us the number of vehicles that arrived at the toll plaza between t equals 1 and t equals 5, which is from 6 a.m. to 10 a.m. And we don't have to evaluate this. That is it for Part A. Part B says, find the average value of the rate in vehicles per hour at which vehicles arrive at the toll plaza from 6 a.m. to 10 a.m. So we're concerned with that same window from t equals 1 to t equals 5. This is just asking for the average of the rate of arrival. So we just have to add up the rates of arrival, like we did in part A, and then just divide it by the time that passes. The amount of time that has passed from t equals 1 to t equals 5 is 4 hours. So we just need this integral expression again, but divide it by 4 to find the average rate. Again, it's just adding up all the rates from 1 to 5 and then dividing by the interval width, dividing by 5 minus 1. We'll consult the calculator for this, but let's write out the expression first. Here's the appropriate integral, and then we just have to divide it by 4, which is the same as multiplying by 1 over 4. So this would be the average value of the rate of arrival. And we'll bring up the calculator to find this. So on the calculator, I'll type 1/4 or 0.25 multiplied by math button, option 9, the integration function. We're integrating from 1 to 5. The function we're integrating is 450 multiplied by the square root of sine of 0.62t, but it's more convenient to use x on the calculator. There we go. This is about 375.54. I'll use 3 decimal places, so 375.537. And remember what this actually is. This is the average value of the rate of arrival during this time from t equals 1 to t equals 5. So the units here would be vehicles per hour. This is the average of that rate. The rate at which vehicles are arriving obviously changes as time passes, but on average, between 6 a.m. and 10 a.m., vehicles are arriving at about this rate. On to part C. Is the rate at which vehicles arrive, which again is A of t, is that rate at 6 a.m. increasing or decreasing? That's a really easy question. We just have to find the derivative of A of t. That will tell us how the rate is changing. If the derivative at t equals 1 is positive, then the rate is increasing, and otherwise the rate would be decreasing. So we will write part C over here. We'll again use the calculator to evaluate this derivative. So what we're looking for is the derivative with respect to time of A of t, and we are evaluating this at t equals 1. All right, so the derivative of A of t at t equals 1 is about, let's consult the calculator. I'll press the math button. Option 8 for the derivative function. We will use x as our variable, and we are taking the derivative of A of t. So here's A of t, which we will type into the calculator. 450 multiplied by the square root of sine of 0.62 times x. And we are evaluating this derivative at x equals 1. The question tells us that, right? X, or in this case, t equals 1. This is about 148.95. So we'll write that here, 148.95. Since this is positive, the derivative of the rate is positive, that means that the rate at which the cars are arriving is actually increasing. And there our explanation is written out. Because the derivative of A at t equals 1 is positive, the rate at which vehicles arrive at the toll plaza is increasing at this time. Finally, part D. A line forms whenever A of t is at least 400. The number of vehicles in line at time t, for t between A and 4, is given by this integral expression, where A is the time when a line first begins to form. To the nearest whole number, we must find the greatest number of vehicles in line at the toll plaza in the time interval where t is between A and 4, and to justify our answer. There's a decent amount of notation going on here, but don't let that intimidate you. We will find the extreme values just the same as always. We start by taking the derivative of n of t, the number of people in the line, or the number of vehicles in the line. Because remember, we're looking for the greatest number of vehicles in line. So what is n prime of t? Well, because n of t is actually the integral of this expression, n prime of t is just the expression being integrated, which would be A of t minus 400. Now, in order to determine when this number of vehicles is maximum on this interval, we'll have to check the endpoints of the interval, so that's t equals A and t equals 4, and we will also have to check the critical points. For the critical points, we need to see where is this derivative, A of t minus 400, undefined or equal to 0. It's not undefined anywhere, but clearly it's going to be equal to 0 when a of t equals 400. That's not a super easy equation to solve for t, but thankfully we have our calculator. All right, now on the graphing calculator, you would press y equals. I've already entered our function, so we can press the graph button, and here our function is. We can zoom in on the interesting part here. We can see that a of t minus 400 is going to hit the x-axis, which means it's equal to 0, when x, or in our case t, is about 1.4694. So 1.4694. And it's also going to come back to 0 when x is about, let's look, we'll just scroll over here. It hits 0 again when x is about 3.5977. Now, the question asked us to determine when there is a maximum number of people in the line. So we're going to have to check the values of n of t at the possible candidates where there could be a maximum. The candidates are the critical points, which are these zeros of the derivative we just found, where t is 1.4694, t could be 3.5977, or we also have to check the endpoints of the interval, which were a and 4. Now 4, obviously, we can add to the table, but what the heck is a? Well, a is when the line actually starts to form. There isn't a line unless the function a of t is at least 400. From the graph we just looked at, we saw that a of t is actually less than 400, which is why the graph was negative, up until this first critical point. That's when a of t finally matched 400 and then proceeded to surpass it. So at t equals 1.4694, that actually is the lower endpoint of this interval when a line first starts to form. Now, n of t is this integral from a to t. So if we let t equal this lower bound, which actually is a, then n of t will clearly be 0, because this is right when the line starts to form, but technically hasn't actually formed yet. If you're thinking about this integral as area under a curve, this would be no area at all because no time has passed. For the other t values, we will consult our calculator. So we'll press math and then the integration function. We are integrating from a when the line starts to form, which as we just discussed is actually 1.4694. And we're integrating to, first, let's do this one. T equals 3.5977. So we're integrating to 3.5977. What we are integrating, by definition of n of t, is a of x minus 400. So we'll have to type in the a function here and then subtract 400. So this is 450 multiplied by the square root of sine of 0.62. Again, on the calculator, we're going to use x instead of t. And then we are subtracting 400. And we are integrating here with respect to x. And there we go. So n of 3.5977 is about 71.25. At this time, there's about 71.25 vehicles in line. Now we'll do the same exact thing, but with t equals 4. Plugging in the integral again, but with t equals 4, you'll get about 62.34. So we see the greatest number of vehicles in line between when the line starts to form and t equals 4. The greatest number of vehicles in line is about 71. You can't have 71.25 vehicles, so our final answer would be 71. And that completes our solution to free response question 1 from the 2022 AP Calc AB exam. Next up are problems on areas and volumes. For these problems, make sure that you use a picture. A lot of these problems provide a bit of a picture that you can start with, but not all of them. Regardless, a picture is an invaluable tool for making sure that you represent the information that you have correctly and are more easily able to interpret that information to write correct integral expressions. This is problem 1 from the 1998 AP Calc exam, and as we can see, this is from the graphing calculator section, so we may find ourselves in need as we go through this problem. Let's read it. Let R be the region bounded by the x-axis, the graph of y equals root x, and the line x equals 4. Part A is to find the area of the region R. So that should be pretty straightforward. We'll just start out with a sketch of the function y equals root x and the line x equals 4, and we just need to find the area of the region enclosed. You should know by now that y equals root x looks something like that, and the line x equals 4, I'll draw in just a second. We should probably just go ahead and label this y equals root x. And then in orange, we will write the line x equals 4. And maybe that's right here. So there is x equals 4. It's a vertical line. And so we are looking for the area of this enclosed region, because remember, this region is also bounded by the x-axis, right? So it's this region here that we're looking for. This is the region R. We need to find its area. So that's just the area under the curve y equals root x from x equals 0 to x equals 4. So very simple for part A. We're just going to integrate our function, square root of x, from 0 to 4 to find the area underneath it. Now, square root of x is the same as x to the 1/2. So to integrate this, we're just using the power rule. We need to increase the power by 1, so x to the 1/2 goes up to x to the 3/2, and then divide by that new power, which is the same as multiplying by its reciprocal. That's the integral, and we're evaluating this from 0 to 4. Now, when we plug in 0, the lower bound, we're just going to get 0. So all we have to worry about is plugging in the 4, and we're going to have 2/3 times 4 to the power of 3 over 2. Now remember, a fractional exponent is kind of like two separate operations. It tells us we need to take the square root of 4 because of that denominator of 2, and then we need to cube the result. The order, of course, doesn't actually matter. That's just the way I like to think of it. So first, we take the square root of 4, which is 2, and then we have to cube that. So this ends up being 2/3 times 2 cubed. 2 cubed is 8, so it's 2 times 8 over 3. And so the answer is 16/3. That is the area. That's the answer for part A. I'm going to shrink our work for part A, and then we're going to move on to part B. Part B says that we are to find the value of h such that the vertical line x equals h divides the region R, so the same region as before, into two regions of equal area. So this sketch that we had before is still useful, but what we're looking for now is what line x equals h would we have to draw so that the area to the left is the same as the area to the right. So we'll have to set up an integral for the area on the left and an integral for the area on the right, and then we can solve that for the unknown, which is where does this vertical line have to be to make these two regions equal. So I've just copied the picture and made it a little bigger. There is our line, x equals h. We're not sure exactly where it has to be. We're just putting it somewhere on the picture to help us set up our integrals. So the first integral is going to be the area of the region of R that's to the left of x equals h. That's this part over here. So for that, we're just going to integrate the square root of x from 0 to h. And this has to equal the right side of the region, which is the integral from h to 4. We're still stopping at x equals 4. And so these things need to equal each other. We can just go through and evaluate this and then solve for h. This integral on the left is a lot like the integral we did in part A, except instead of going from 0 to 4, we're going from 0 to h. In the part A integral, you may remember that we ended up with 2/3 times 4 to the 3/2. By the same process, on the left side here, we would end up with 2/3 times h, the upper limit of this integral, to the power of 3/2. Now, on the right side, similar stuff will happen. We'll integrate the square root of x, which again becomes 2/3 times x to the 3/2, applying the reverse power rule, so to speak. And we're evaluating this from h to 4. Now on the left, we have 2/3 h to the 3/2, and then evaluating the right side First, we plug in the upper limit, and we already saw before that when we plug 4 into this integral, what we get is 16 over 3. So I'm just going to write that as 16 over 3. And then we subtract, plugging in the lower limit, which in this case is h. So minus 2/3 times h to the 3/2. Then we can go ahead and add 2/3 h to the 3/2 to both sides to collect all of the h's together. So we now have 4/3 h to the 3/2 equals 16/3. Let's go ahead and multiply both sides by 3/4 to get rid of this coefficient in front of the h. That's going to give us h to the 3/2 equals, multiply both sides by 3/4. So we're multiplying by 3/4 over here. 3's cancel out. A factor of 4 will cancel out. And so on the right side, we're just going to be left with 4. Now we can square both sides to get rid of that power of 1/2. Thus, we'll have h cubed equals 16, and then take the cube root of both sides. And that is the answer to our question. Remember, the question here was to find the value of h such that the vertical line x equals h divides the region R into two regions of equal area. So if we were to draw the line x equals cube root of 16, that would split the region into two regions of equal area. Let's move on then to part C. Find the volume of the solid generated when R is revolved about the x-axis. So this is a pretty standard volume of a solid of revolution problem. So let's set up the appropriate integral. I'm just going to shrink our work for part B, and then we can get on with it. So moving on to part C, we are revolving this curve about the x-axis, and what that will do, I'll draw in a different color. I'm sure you know, but it's helpful to sketch these solids of revolution, especially in more complicated cases. It's going to look like this, right? Because we're creating this solid by revolving the curve, the cross sections are circles, which makes finding the volume of this solid rather easy. And notice that those circular cross sections have radii, which are the values of the function root x at those x coordinates. So this is a very classic example, nothing weird going on here. What we're doing is adding up infinitely many circles, which is why in this type of situation, we have to integrate pi r squared from, in this case, 0 to 4, right? From x equals 0 out to 4. Now the pi we can take out of the integral. The r, remember, is the radius of a cross-sectional circle, and we are integrating this, by the way, with respect to x. So how do we express the radius as a function of x? Well, like we just said, from the sketch too, we can see this. The radius of each circle is just the value of the function, root x. It's like a height. So we can rewrite this integral, writing r squared in terms of x. This is, let me take the pi out. So this is pi times the integral from 0 to 4 of the radius squared. The radius is the function. That's what gives us the height. That's root x. And we have to square that. And then this is getting integrated with respect to x. This, of course, works out pretty nicely because the square root of x squared is just x. So this is pi times the integral of x from 0 to 4. The integral of x, applying the reverse power rule, is just 1/2 x squared. This is from 0 to 4. Plugging in the upper bound is going to give us 1/2 of 4 squared. So that's 1/2 of 16, which is 8. Plugging in 0 will just give us 0. And so our final answer for the volume is 8 pi, and we could say units cubed. Finally, we can move on to part D. This is very similar to part B. The vertical line, x equals k, divides the region R into two regions, such that when these two regions are revolved about the x-axis, they generate solids with equal volumes. We need to find the value of k that causes this. So it's just the three-dimensional version of problem B. We need to find a vertical line so that the solids of revolution on either side of that line will be equal. I just shrank our work for problem C. Here's a copy of the picture. And remember, we're now looking for a vertical line. So I'll just draw it like that. This is the vertical line x equals k. And we need to make sure that this volume on the left is the same as this volume on the right, still going from 0 to 4 because that's how the region R is created. So just like with problem B, we'll set up two integrals representing the volume of the side on the left and the volume of the side on the right, set them equal, and then we can solve for k. Now the volume of the solid to the left of x equals k, which perhaps I should have drawn as a curve to more accurately be consistent with the 3D sketch. But regardless, we're integrating from 0 to k, and we can take the pi out. The radius squared, we know, is just x dx. So that's going to be the volume of this part of the solid that's to the left of the vertical line x equals k. And this is going to equal pi multiplied by the integral from k to 4 of the radius squared. The radius, again, is just root x, so when we square that, we get x. Now we can evaluate these integrals and then just solve for k. So on the left, we're going to have pi multiplied by 1/2 x squared evaluated from 0 to k. This equals, on the right, pi multiplied by 1/2 x squared evaluated from k to 4. On the right, we now have pi multiplied by, plug in the upper limit, so 1/2 k squared, and then plugging in 0 won't do anything. On the right, we have pi multiplied by, plugging 4 in will give us 8, and then plugging in k for our lower bound, that's going to be minus 1/2 k squared. And now we'll just have to solve this for k. On the right, you can see that we have negative half pi k squared. So let's add that to both sides. On the right, we have 1/2 pi k squared, and we're going to add another half pi k squared from the right. So that's going to give us a full pi k squared on the left, which equals 8 pi. Divide both sides by pi, and we have that k is equal to the square root of 8, right? Divide by pi, take the square root of both sides. K equals the square root of 8, which we can simplify because 8 is 4 times 2. So you can take this square root 4 out, giving us 2 root 2. If we were to draw the vertical line, x equals 2 root 2, the volume of the solid to the left would be the same as the volume of the solid to the right. This is problem 1 from the 2002 AP Calc AB exam. This is part of the graphing calculator section, so we will be using a graphing calculator throughout this problem. Let's read it. Let f and g be the functions given by f of x equals e to the x and g of x equals lnx. I'm going to refer to lnx as log x, if that's okay with you. Part A is to find the area of the region enclosed by the graphs of f and g, e to the x and log x, between x equals 1/2 and x equals 1. So we need to integrate the difference of the functions from 1/2 to 1. That's how you find the area between curves. You may want to sketch these functions. E to the 0 is 1, and from there it grows exponentially. And as x gets very negative, e to the x approaches 0. On the other hand, log x, for values of x that are very close to 0, log x is very big and very negative. And then as x gets larger, log x grows indefinitely, although it does it very slowly, and is certainly less than e to the x. And remember, we want to find the area between x equals 1/2 and x equals 1. So maybe that's right around here. This is x equals 1/2. And then x equals 1 is going to be right here. And we know that x equals 1 is where log x intersects the x-axis because log 1 is 0. All right, so we can see that log is the lower function and e to the x is the upper function. So for our integral, we're going to integrate from 1/2 to 1, that's given, and we're going to integrate the upper function, e to the x, minus the lower function, log x. This is going to give us the area of that region. And we can use our graphing calculator to figure this out. So I'll open up the graphing calculator, press the math button to get access to all these functions, and I'm going to use the integration function. We're integrating from 1/2 or 0.5 up to 1, and the thing we're integrating is e to the x minus log x. And then, of course, we're integrating this with respect to x, and we can enter this to get our answer about 1.22. So that is the area of this region. All right, let's move on to part B. Find the volume of the solid generated when the region enclosed by the graphs of f and g between x equals 1/2 and x equals 1. That's this region here, which we just found the area of. We want to find the volume of the solid generated when that region is revolved about the line y equals 4. So that's a line that's up here, which is above this region. And we're going to revolve the region about that horizontal line, and we need to find the resulting solid. Now, hopefully you can picture if we revolve this region about that line, y equals 4, you can see that it is the green curve, which is log x, which will be tracing the exterior of this surface. The interior is going to kind of be carved out by e to the x. And so this is what we call a washer problem. To find the volume of this solid of revolution, we need to integrate or add up the areas of all of these washers. So what are we going to do for part B? Well, again, we need an integral from 1/2 to 1. And what we're integrating is the areas of these washers. We can find those areas by taking the areas of the outer circle, which is traced by log x, and subtract the area of those inner circles, which is traced out by e to the x. Now, the area of the bigger circles will, of course, be pi r squared, and r, the radius of this bigger circle, which is traced out by revolving log x about the line y equals 4, the radius of that circle is this distance here. And that distance is just 4 minus log x. I just redrew it a little more nicely. Once more, the radius of those bigger circles is the distance from y equals 4 to that lower function, and that is 4 minus log x. As for the smaller inner circles, the radius of those is the distance from y equals 4 to that upper function, and that is e to the x. That distance is 4 minus e to the x. Those are our smaller radiuses of the inner circles, which are actually being carved out of this solid. Okay, so coming over to set up our integral. Both of these areas have a factor of pi in them, so we'll just take the pi out of the integral. The radius squared for the larger circles is going to be 4 minus ln x squared. And then we're subtracting the areas of those smaller inner circles, which is 4 minus e to the x squared. We're integrating this with respect to x, and we can just calculate this on our graphing calculator. So on the calculator, again, I press the math button to access these functions. Press the integration function. We're integrating from 1/2 up to 1. What we are integrating is the difference of the squares of the radii. We'll multiply by pi after the fact, so let me enter in these radii squared. So there's the difference of the squares of the radii. We're integrating this with respect to x, and there is our answer, about 7.52. But don't forget, we need to multiply this by pi. So finally, the volume of this solid is about 23.61. Finally, moving on to part C. Let h be the function given by h of x equals f of x minus g of x, so just the difference of e and log. Find the absolute minimum value of h of x on the closed interval from 1/2 to 1. And find the absolute maximum value of h of x on the closed interval from 1/2 to 1. And show the analysis that leads to our answers. Okay. To find maximums and minimums, of course, we're going to need to take the derivative of h. That way we can find any critical points. We also know that we're going to have to check the endpoints, because remember, this is defined on a closed interval between 1/2 and 1. So this is sometimes called the candidates test. What are the candidates for the extreme values? Well, those would be the endpoints, 1/2 and 1. So we will need to check those. And then also the critical points. But to find the critical points, we have to take the derivative. So let's just jot this down. What do we need to check? Well, we'll have to check 1/2 and 1. And by check them, I mean we need to plug them into the function h of x and see what those values are in order to establish minimums and maximums. And then we'll also have to find any critical points and check those. So let's find h prime of x, and then we'll be able to find the critical points. Now remember, h of x is just f of x minus g of x, which is e to the x minus log x. So h prime of x is just f prime minus g prime. F prime is e to the x, because the derivative of e to the x is e to the x. And then we subtract g prime. G is log x, so g prime is 1 over x. All right, so what are the critical points? Well, the critical points are where this derivative doesn't exist. It doesn't exist at x equals 0, but 0 is not in this interval, so that doesn't matter. And also where the derivative is equal to 0. So let's set this derivative equal to 0, and then we can use our graphing calculator in order to solve that. So I'm going to enter this function e to the x minus 1 over x into my calculator. And then we can look at the graph. Pressing the graph button, we see a function that looks like this, and we need to see where does it pass 0 in our interval. And that would be right about here. Let's see if we can get the calculator to give us this number. It appears to be about 0.567. That's when y is 0, when x is about 0.567. So I'll write that over here. That is our critical point. So we need to check x equals 1/2, x equals 1, and our newly discovered critical point at x equals 0.567. We need to plug all three of these values into the function h of x and see which is the maximum and which is the minimum. Plugging them in, these are the values we get. And we can see the lowest value is at that critical point where x was about 0.567. Here, the value of h is about 2.33, so that would be our minimum. And the maximum we see is at x equals 1, where h takes on a value of 2.72. And remember, these were discovered on a closed interval. So on that closed interval, this is actually an absolute maximum and an absolute minimum. And that completes our solution to problem 1 of the 2002 AP Calc AB exam. This is free response question 2 from the 2004 AP Calc AB exam. This is part of the graphing calculator section, so we will be using a calculator throughout this problem. Let's read it. Let f and g be the functions given by f of x equals 2x times 1 minus x, and g of x equals 3 times x minus 1 times root x, for x between 0 and 1. And we're given a graph of these curves for free. You can see they go from 0 to 1. We have f of x as the upper function, that's right there, and g of x as the lower function. Part A is to find the area of the shaded region enclosed by the graphs of f and g, which is what we have a picture of. You're not going to get a much easier part A than this. We can already see a picture of this situation. We're trying to find the area of this region, and we can use a calculator. So all we have to do is take the integral of the upper function, f of x, so I'll write the integral of f of x, minus the lower function, which is g of x. This is going to give us the area between the curves, and we want this area from 0 to 1 because this shaded region goes from 0 to 1. Now, f of x, of course, is 2x times 1 minus x, and g of x is 3 times x minus 1 times root x. So let me just write those things in place of f and g. All right, so that there is the integral that we're calculating, and we will just use our graphing calculator to do that. So I'm going to press the math button, and that's going to give me access to all these functions. I'm going to go with function 9, the integration function, and we are integrating from 0 to 1. What we're integrating is 2x times 1 minus x minus 3 times x minus 1 multiplied by the square root of x. And we see from the calculator, this area is about 1.133. So let's write that. This is about 1.133. And that completes part A. Moving on to part B, find the volume of the solid generated when the shaded region enclosed by the graphs of f and g, so this shaded region here, is revolved about the horizontal line y equals 2. Now we know from the picture the horizontal line y equals 2 is somewhere up here, right? Because y equals 1 is right there. So we're revolving this shaded region about that horizontal line way up there. I've just done a rough redrawing of the figure that gives us a little bit more room to work with. This is our shaded region that we found the area of in part A, and for part B, we're creating a solid of revolution by revolving this shaded region about this horizontal line y equals 2. So that's going to look something like this. You can see how the lower curve, which is g of x, the lower curve is going to trace out the exterior of this solid of revolution. The interior is going to kind of be cut out by the upper function, which was f of x. As we do this revolution, it would look something like that. We have these middle circles cut out by that upper function. So this is what we call a washer problem. To find the volume of this solid, we're going to have to add up the areas of all of these washers. I said add up, and of course that means we are integrating still from 0 to 1, because we are still talking about this shaded region from 0 to 1, and what happens when we revolve it about a horizontal line. What we need to add up are the areas of all of these washers. And the way we find those areas is by taking the area of the bigger circle, traced out by the lower function, and subtract the area of the smaller circle, which is traced out by this upper function. Each circle has an area of pi r squared. Let's just take the pi out. So we have a pi in front of the integral, and then we're going to need the radius squared of the bigger circles, and subtract the radius squared of the inner circles. Now, what is the radius of these big circles? Well, that would just be the distance from the line y equals 2, which is the center, down to the curve that's tracing out the circle. That curve is g of x, the lower curve. So this radius here is just 2, the horizontal line, minus g of x, because it's the distance between the line and the curve g of x. So we'll put that radius in here. This is 2 minus g of x. That's the radius of the big circle. The radius of the small circle is similar. It's the distance from the horizontal line, y equals 2, to the curve that's tracing out the smaller inner circles. That curve, of course, is f of x. So in here, we'll put the radius of the smaller circles, which is being subtracted, and that's 2 minus f of x. Again, remember from the picture, we see that g of x is that lower curve, f of x is that upper curve, which is actually tracing out the smaller circles. And here's what that integral looks like once we plug in the pieces. We still have the pi out front. We're integrating from 0 to 1, 2 minus g of x, and this is g of x. This is getting squared, minus 2 minus f of x, and this is f of x and this is getting squared. Let's jump over to the calculator and find the value of this integral. Again, I'll press the math button and then go to function 9, which is the integration function, and then I will go through the long process of typing this whole thing out. You want to make sure you're careful when you're typing these long expressions with parentheses and squaring into your calculator. This looks right to me, so I'm going to go ahead and press enter, and we see this is about 5 3/20, but we don't want to forget that we took a pi out of the integral, so we also have to go ahead and multiply this by pi. Once we do that, we get about 16.18. I'll round to 3 decimal places and call it 16.179. That completes our solution to part B, so let's go ahead and move on to part C. Let h be the function given by h of x equals kx times 1 minus x for x between 0 and 1. Notice that h of x is just like our function f of x, except instead of being scaled by 2, it's being scaled by k, where k is positive. So it's either being shrunken down a little bit and maybe looks like that, or it's being stretched and looks something like that. Finishing the question, for each k greater than 0, the region, which is not shown, because remember this is f of x, it's not h of x, the region enclosed by the graphs of h and g is the base of a solid with square cross-sections that are perpendicular to the x-axis. There's a value of k for which the volume of this solid is equal to 15. So we could stretch this function h of x by some k that's going to make the volume of the described solid equal to 15. We need to write but not solve an equation involving an integral expression that could be used to find the value of k. This problem is actually pretty easy, but there is a lot going on here. We need to read it very carefully. Let's come back to our picture and draw what h of x could look like. Like we said before, it looks just like f of x, but scaled up by some factor, or potentially scaled down, but let's draw it as if it has been scaled up. So this is y equals h of x. Now the question is asking us about a solid whose base is enclosed by the graphs of h and g. That is the base. So this region between h and g, f has nothing to do with this at this point, remember? This region between h and g is the base of the solid in question. I'm going to erase this shading just so our picture isn't too cluttered, but just remember that f of x isn't important right now. It's this region between h of x and g of x that is important. The problem is saying that we have a solid, and the base of this solid is this region. And the way that this solid is constructed is by basically taking squares that lie in this region and that are perpendicular to the x-axis. That means it looks kind of like this if we were to take a cross-section. That's perpendicular to the x-axis. It lies in this region, and the cross-sections, as it says, have to be squares. They're square cross-sections. So just to give you some of this 3D perspective, they might look something like this if we were to do kind of a rough perspective sketch of the cross-sections. That's coming up out of the screen. It is a square cross-section, and its base, the base of this square, we can clearly see is just the distance between the upper function, h of x, and the lower function, g of x. So this base, the side length of this square, is just h of x minus g of x. Now, what about the height of the square? Well, it's a square, so of course this other length is just another side length of the square. It also has a length of h of x minus g of x, because that's the base length, and this is a square, so it's equilateral. Thus, the area of the square is h of x minus g of x squared. To find the volume of this solid, which we know is 15 for some value of k, remember k is part of the definition of h of x, to find the volume, we just have to add up all of the areas of the square cross-sections. So let's set up this integral. We have to integrate from 0 to 1 the areas of the square cross-sections. The areas of the square cross-sections are the squares of the side lengths. Each side length is h of x minus g of x. We have to square those to get the area. We're adding this up. This integral gives us the volume, which is equal to 15 for some value of k. Now, where does the k come in here? Well, let's just rewrite this integral one more time, replacing h of x and g of x with what those functions actually are. H of x is kx times x minus 1, and g of x, the lower function here, is 3 times x minus 1 times root x. And remember, this whole thing is the side length of the square cross sections, and so we need to square it to get those areas. This integral is equal to 15 for some value of k, and we could use this equation to solve for k. That's the answer to part C. And that completes our solution to free response question 2 from the 2004 AP Calc AB exam. This is free response question 5 from the 2019 AP Calc AB exam. Let R be the region enclosed by the graphs of g of x equals -2 plus 3 cosine of pi over 2x, and h of x equals 6 minus 2 times x minus 1 squared, the y-axis, and the vertical line x equals 2, as shown in the figure above. So this was just a description of the region R, enclosed by these curves and these vertical lines. Part A is to simply find the area of R. And note, this is problem 5. This would have been part of the no calculator section, so we will not be using a calculator for this. All right, so for part A, we're just going to have to do an integral. The integral should go from x equals 0 to x equals 2. We know that because the problem told us this region R is bounded by the y-axis, which is x equals 0, and the vertical line x equals 2. So we need to integrate from here to here. Then what we're integrating is the upper function minus the lower function. You could totally disregard which is upper and which is lower and just take the absolute value of your answer for this integral. But at a glance, you may be able to notice this is clearly the cosine function. That's g of x. That's the lower function. This one up here is the quadratic. That's the upper function. So we're going to be integrating that upper function, 6 minus 2 times x minus 1 squared, minus the lower function. The lower function is g. That's -2 plus 3 cosine, etc. It'd be great to have a calculator for this, but let's not fret. We can do this by hand without too much difficulty. Let's begin the integral. Integrating 6 just gives us 6x. As for -2 x minus 1 squared, we'll have to keep the -2, and then the power of 2 in the x minus 1 squared needs to be increased by 1. But then you also have to divide by that new power, so divide by 3. So we end up having -2/3 as the coefficient. Since we have a function inside the parentheses, we also have to divide by its derivative, but its derivative is just 1. So we're actually done with that already. Moving on to this next part, -2 is +2. So that integrates to plus 2x. As for -3 cosine of pi over 2x, we know that we're going to need a -3 sine of pi over 2x. The derivative of sine of pi over 2x is going to give us that cosine of pi over 2x. But by the chain rule, it would also give us a factor of pi over 2. We need to divide that out since we're doing integration. Dividing by pi over 2 is the same as multiplying by 2 over pi. So -3 times 2 over pi is -6 over pi. So let's just put that, minus 6 over pi. And there we go. We're integrating this from 0 to 2. You might have to watch that again if you haven't practiced integration much. And if this part with the cosine was difficult, you might want to just try using u sub. Hopefully with practice, you won't use u substitution in situations where the inside function is linear, because in those situations, you just have to divide by the derivative. It's pretty straightforward, but it does take some practice. So use the u sub if you need to. All right, let's start now by plugging in this upper bound, and then we'll subtract, plugging in the lower bound. Plugging in the upper bound of 2 gives us 12 at first, so we have 12. And then here we'll have 2 minus 1 cubed, which is just 1 cubed, so we'll just be left with the coefficient of -2/3. Then plus 2 times 2, so that's going to be plus 4. And then with the sine function, pi over 2 times 2 is pi, and sine of pi is 0. So this whole last term is gonzo. All right, now we will subtract, plugging in the lower bound, plugging in 0. Plugging in 0 is going to get rid of that, and the sine function, because sine of 0 is 0. So all that's left is this term here. 0 minus 1 is minus 1, and then when we cube that, we get minus 1. So this should just be negative 2/3 times negative 1, which is positive 2/3. All right, now we just have to evaluate this. Let's give everything a denominator of 3 so that we can combine all of these fractions. 12 is the same as 36 over 3. Then we're subtracting 2 over 3, and then 4 is the same as 12 over 3, and then we're subtracting another 2 over 3. All right, now what does this add up to? 36 thirds plus 12 thirds is 48 thirds. Minus 2/3 is minus 4 thirds. So this is a total of 44 thirds. And that is our answer for part A. All right, let's move on then to part B. Region R, so the same region we've been talking about, is the base of a solid. So it's like we have a solid coming up from the paper. For this solid, at each x, the cross-section perpendicular to the x-axis has area 1 over x plus 3. We need to find the volume of the solid. This is actually a really straightforward question. If the area of the cross-sections perpendicular to the x-axis are 1 over x plus 3, we just need to integrate those areas from x equals 0 up to x equals 2. So setting up this integral, all we're doing is integrating from 0 to 2 the areas of the cross-sections. That's how we find the volume of this solid. The areas of the cross-sections are given to us as 1 over x plus 3. Sometimes in these types of problems, we're just told that the cross-sections are squares, and then we could use the base length to figure out what the areas of the squares are. But this example is honestly even easier because we're just given the areas of the cross-sections outright. Now let's go ahead and integrate this. The integral of 1 over x plus 3 is the natural log of x plus 3. And we don't have to worry about absolute values around the inputs because we're evaluating this from 0 to 2, where the input of the log function will always be positive here. So let's just plug in the upper bound, that's going to be ln of 5, and then subtract the lower bound, which is going to be ln of 3. And that is the volume of the solid described in part B. Again, notice this is a situation where the inside function, x plus 3, is linear, so no u sub is really required. We would just have to divide by the derivative of this inner function. In this case, that derivative is 1, which is why it didn't really come up. Let's move on then to part C. Write, but do not evaluate. Oh good, we don't actually have to do the integral this time. Write, but do not evaluate, an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 6. Coming up to the picture provided, y equals 6 is this horizontal line here. So what's happening is our region R is getting revolved about this horizontal line. And if that happens, then hopefully you can see that this lower function, or what was the lower function, the cosine function, is going to be the outer function in the revolution. And this, what was the upper function, the quadratic, is going to be the inner function in the revolution about this horizontal line. The cross sections of this solid of revolution will be these washer shapes where the outside is traced by the cosine function revolving, and the inside hole is carved out by the quadratic function revolving. So what we need to do is take the areas of the big circles traced out by the cosine function, and then subtract the areas of the inner circles which are removed by the quadratic function. This is a washer problem. So let's set up the big picture here. We are integrating from 0 to 2 the area of some circles minus the area of some other circles. Both of those will have a pi in them, right? It's like pi big R squared minus pi little r squared. let's just pull a pi out of the whole thing and put the pi in front of the integral, okay? And then we're going to need that big radius squared minus the little radius squared, and this integral will be taken with respect to x. We can go back up to our picture to see what these radii are. The radius of the big circles is the distance from the line y equals 6 down to the cosine function g of x. That distance, I'll write it over here, that distance is just 6 minus g of x. That's the distance between them, which is the radius of the outer circles, or the big circles. The inner circle has a smaller radius. Let's do it in, I guess, purple. It's the distance from y equals 6 down to the quadratic function, that little distance right there. Now that distance is found in a similar way. It's just 6, the horizontal line, minus the quadratic function h of x. That's the distance between them, which is the radius of one of these smaller circles. With that, we can finish our integral setup. The big radius, big R squared, we can replace that with the radius of the outer circles, which we found to be 6 minus g of x squared. And then we're subtracting the squared radius of the smaller circles, which are cut out. That's why we're subtracting them. They are cut out from the cross sections. Those radii we found to be 6 minus that inner function h of x. Again, squared, and don't forget the dx. And there we go. That is our integral expression, which we don't need to evaluate, but just to make it very clear that all of this is in the integral, let's put it in one big set of parentheses. And that will complete our solution to free response question 5 from the 2019 AP Calc AB exam.
Next up are problems on differential equations. Recall that we can think of a slope field as a graph of a bunch of tiny tangents to the solutions of the differential equation. Also recall that for separation of variables, you're trying to get the dx term with the x's and the dy term with the y's. You don't want the dx in the denominator, you don't want the dy in the denominator. Once you've separated variables, you can integrate both sides of the equation.
This is problem 5 from the 2006 AP Calc AB exam. Consider the differential equation dy dx equals 1 plus y over x, where x is non-zero. Part A says, on the axes provided, sketch a slope field for the given differential equation at the 8 points indicated. So when you sketch a slope field, of course, you've got to decide how many slopes should you draw and where should you draw them. This is telling us how many to draw and where to draw them at these 8 points. So we'll just have to use the differential equation to find the slopes at those points and sketch little tangent lines representing those slopes. So let's get into it. This should be pretty quick because there's only 2 parts to this problem. It might help to organize our information in a table for part A, so we can put the coordinates on the left side and we can put their corresponding derivatives on the right side. I've split this up into 2 tables just so that the table's not super long and I have to scroll way down the page to fill it out. So it's just space reasons. All right, we'll start with the first 4 points in this table. Those are -2, 0. So I'll put that here, -2, 0. We've got -1, 0. We have -1, 1. And we have this point here, -1, -1. We'll have to plug these points into the derivative given, the differential equation, in order to find the slopes at these points. Plugging in -2, 0 gives us a 1 in the numerator, because we'd have 1 plus that y coordinate of 0, divided by that x coordinate of -2. So the slope here should be -1/2. Plugging in the point -1, 0 should give us 1 plus 0 in the numerator, so 1, divided by that x-coordinate of -1. So in total, the slope would be -1. Plugging in the third point, -1, 1, we should have 1 plus 1, or 2, in the numerator, divided by -1 in the denominator, for a total of -2 being the slope. Last point, -1, -1, we should have 1 plus -1 in the numerator, which is 0, divided by -1 in the denominator, but it ends up just being 0. We will sketch little tangent lines to represent those slopes, but first let's finish calculating the slopes for the other 4 points, which we'll do in this table. All right, so we've got this point, which is 1, 0. We've got this point, which is 2, 0. We've got this point, which is 1, 1. And we have this point here, which is 1, -1. And we'll plug these in and find the slopes just as we did for the previous 4 points. If we plug in 1, 0, the numerator will be 1, and the denominator will be 1 also, so the slope will be 1. If we plug in 2, 0, we'll have 1 in the numerator and 2 in the denominator, so that will be a slope of 1/2. If we plug in 1, 1, the numerator will be 2, and the denominator will be 1, so the slope will be 2. If we plug in 1, -1, the numerator will be 0, and the denominator will be 1, so the slope will be 0. All right, let's go ahead and plot tangent lines representing these slopes at the appropriate points. Note, if you were actually doing this on the exam for real, you would have been asked to use the axes provided in the pink exam booklet, but we're going to do it right here. And remember, these things don't have to be exact, right? -1/2, I don't have to draw a slope of exactly -1/2 there. I'm doing this by hand. That's not really possible. But I do need to get the big details right. So I need it to be going down because it's negative, and I would need it to be less steep than the slope of -1, which should be less steep than the slope of -2. Got to get those big relative details right. But let's start with a real simple one, the slope of 0 at the point -1, -1. At this point here, -1, -1, we should have a horizontal tangent. So I'll just draw a little segment. You can see it there representing the slope at that point. Then going back to the top of the table, at the point -2, 0, we should have a slope of -1/2. Here is -2, 0. A slope of -1/2 should be a slight downward slope, so maybe something like that. Then at -1, 0, we should have a slope of -1. So it should be downwards, and it should be steeper than that slope of -1/2. And again, this is at -1, 0. So maybe that looks something like that. Then at the point -1, 1, we should have a slope of -2. So right here, we should again have a downward slope, and it should be the steepest yet. So maybe it looks something like that. Now, if we had arranged this data more intelligently, let's say we swap rows 1 and 2, we could easily see that the remaining points and their corresponding slopes are just the opposites of everything we just did. These are the same slopes that we have left to sketch that we just did, except opposite. Instead of negative, it's positive. Instead of negative, it's positive. Instead of negative, it's positive. You see that? After noticing that, I can very quickly finish this slope field by just drawing a mirror image of everything we just did. So I'll try to do that quickly. Maybe it looks something like this. And there is our slope field. Remember, you just got to get those big details right. Like this slope of +1 is going upwards, and it's less steep than this slope of +2, which is going upwards. Let's move on then to part B. We are asked to find the particular solution, y equals f of x, to the differential equation with the initial condition f of -1 equals 1, and to state its domain. The differential equation in question here, of course, is this one that we were originally given. So we can find a particular solution using this differential equation and this initial condition. And we can do it using the separation of variables technique. So I've written the differential equation and the given initial condition. Let's multiply both sides of the differential equation by dx to get the x's together, and divide both sides by 1 plus y to get the y's together. If we do that, on the left, we're going to have 1 over 1 plus y, dy, and on the right, we're going to have 1 over x, dx. After separating the variables, the next step is to integrate. We integrate both sides. On the left, integrating 1 over 1 plus y, that's just the natural log of 1 plus y. Remember, the absolute value is necessary here in the event that y might be negative. If we knew for sure y would never be negative, we would not have to bother with those absolute values, but in this case, we do. Over here on the right side, similar situation, the integral of 1 over x is the natural log of the absolute value of x. In theory, there is an arbitrary constant on the left and the right, but let's just say we gathered them both together on the right side and called that c. Now remember, we're trying to get y by itself because we want y equals f of x. We want some actual function that is a particular solution to the differential equation, given this initial condition. So to get this y by itself, or to take one more step towards that goal, we will exponentiate both sides of this equation. That's going to give us e to the ln absolute value of 1 plus y on the left side equals e to the ln absolute value of x plus c on the right. But by our exponent laws, that's the same as e to the ln absolute value of x times e to the c, right? Because we could bring these together by just adding the exponents. But e to a constant is just a constant. So let's just agree to call that constant c and move it to the front. Order of multiplication doesn't matter. We just prefer to write it this way. Finally, the e's and the ln's cancel out. That was the whole point. And so now we have the absolute value of 1 plus y on the left equals this constant c multiplied by the absolute value of x. Now, we can clean this up some, because remember, we're looking for a function, y equals f of x, that is a solution to our differential equation with this initial condition. So we know it can't be the case that 1 plus y can take on multiple values. Sure, 0.5 and negative 0.5 have the same absolute value, but if that was allowable, then we would not have a function, because that would mean you could plug in an x and I could give you a couple valid options for y to make this equation true because of the absolute value. So does 1 plus y take on negatives or positives? Because it can't possibly take on both. Well, from the particular solution, we know that it must take on positive values because we have a positive y. We know that for a fact. So this absolute value of 1 plus y must only take on positive values, and thus the absolute value can be dropped because it will not change the positive input. So we have that 1 plus y equals c times the absolute value of x. Then we can plug in our initial condition in order to solve for the constant c. The initial condition gave an x-coordinate of -1, so we have c times the absolute value of -1, and the corresponding y-coordinate was +1, so we have 1 plus 1 on the left. The absolute value of -1 just goes away since it's 1, and we find that c equals 2. Then we can rewrite our equation with this information. We have that 1 plus y equals 2 multiplied by the absolute value of x. All right, now what about the domain? Well, let's make the one more step of getting y by itself. So y equals 2 times the absolute value of x minus 1, just moving that 1 over. And now we can figure out the domain by consulting our initial condition. The initial condition said that we have a negative x value in the domain. And looking at the slope field and the differential equation, we know that x can't equal 0, so our function either lies on this side of the slope field or this side. And since we know we have a negative x value, it must be on the left side. And so the domain is x is less than 0. And since x is negative, we know exactly what the absolute value is going to do. It's going to apply an additional negative to make the x positive. So we could also write the function like this: y equals negative 2x minus 1, where again the domain is that x is less than 0, as suggested by the initial condition. And that completes our solution to free response question 5 from the 2006 AP Calc AB exam. This is free response question 4 from the 2015 AP Calc AB exam. Let's read it. Consider the differential equation dy dx equals 2x minus y. Part A. On the axes provided, sketch a slope field for the given differential equation, this one here, at the 6 points indicated. All right, let's just create a quick table with the xy values that we are interested in, see what the derivatives are at those points, and then sketch some little tangents so that we end up with a slope field. Here's my table of xy pairs, and then in this third column, we'll put the derivative dy dx, which is just 2x minus y. At, let's see, this point here, where x is 0 and y is negative 1, 2x minus y is 0 minus negative 1, which is positive 1. At this point here, where x is 0 and y is positive 1, 2x minus y is 0 minus 1, which is negative 1. At this point 0, 2, 2x minus y is 0 minus 2, so that's negative 2. At this point here, 1, negative 1, 2x minus y is 2 minus negative 1, so 2 plus 1, so 3. At this point here, 1, 1, 2x minus y is 2 minus 1, which is 1. Finally, at this point, 1, 2, 2x minus y is 2 minus 2, which is 0. All right, now we can sketch the slope field by sketching some little tangents that capture the right idea of what's going on here. Like, for starters, the point 1, 2 right here has a derivative of 0 at that point, so we should have a horizontal tangent like that. At, let's go back to the top. So 0, negative 1, that's right here. We should have a slight upward slope because that's a positive slope of 1. So something like that. Let me try again just to make that a little more straight. Then at this point, 0, 1, we should have the same sort of slope as before, but negative. So at 0, 1, right here, we'll have a slight negative slope, something like that. At the point 0, 2, so way up here, we should have a steeper negative slope of negative 2. So something like that, perhaps. Then at 1, negative 1, we should have our steepest slope of all, a slope of 3, and it's positive. That's right here at 1, negative 1. So maybe something like that, or maybe that, just a little bit steeper. At the point 1, 1, that's our last one to sketch, we have a slight positive slope of 1, so it should be the same sort of slope as this guy here, so maybe that looks something like this. And there you go. Remember, you're not going to be able to sketch these slopes exactly, but you want to keep the general idea correct. This guy here with the slope of positive 3 should be steeper than any of the other lines, and obviously it should be going upwards. This one should be horizontal. This one here should be steeper than these others that have slopes of plus or minus 1. Just get the general details correct. Moving on then to part B. Find the second derivative of y with respect to x in terms of x and y, and then determine the concavity of all solution curves for the given differential equation in quadrant 2. So the differential equation here, we're going to be able to make a statement about the concavity of its solution curves by finding this second derivative. Also remember in quadrant 2, x is negative, but y is positive. So we will consider that once we find this second derivative. To find the second derivative, we'll just differentiate both sides of the first derivative. This is the differential equation that we were given. Let's differentiate both sides. If we do that, then on the left, we are going to have the second derivative of y with respect to x equals, on the right, the derivative of 2x is just 2, and the derivative of y is dy dx. But of course, we know that dy dx is this, 2x minus y. So let's just replace that dy dx with 2x minus y. And then we can distribute the negative here and find that this equals, let's put the positive y first. It's going to be y minus 2x, and then plus 2. And if we want to factor out the 2, we could rewrite this as y, let's say plus 2 multiplied by 1 minus x. Then, addressing the concavity part of the question, in quadrant 2, like we said, x is negative and y is positive. So if we look at our second derivative, we know that 1 minus x is going to be 1 minus a negative in quadrant 2. which is 1 plus a positive. So 1 minus x is obviously going to be positive in quadrant 2, and that makes it clear that this whole second derivative is going to be positive, because the only other thing in question would be y. But if we're in quadrant 2, then we know that y is positive. So we can say for sure this second derivative, y plus 2 times 1 minus x, is positive, which means that in quadrant 2, every solution curve has to be concave up. All right, moving on to part C. Let y equals f of x be the particular solution to the differential equation with the initial condition that f of 2 equals 3. Does f have a relative minimum, a relative maximum, or neither at x equals 2? And justify our answer. To determine if there's a relative minimum or a relative maximum, let's first plug x equals 2 into the derivative and see if this is a critical point. If it's not a critical point, then no further investigation is needed. If in fact this is an extreme value, the derivative should be 0, where x is equal to 2. So let's evaluate this. So for part C, we're evaluating dy dx at x equals 2. And remember, in this problem, we're told that when x equals 2, the function is equal to 3. So we could say this is at x equals 2, y equals 3. Now the derivative, dy dx, is 2x minus y. So this is 2 times x, which is 2, minus y, which is 3. This is 4 minus 3, which is positive 1, which is not equal to 0. Thus, no further investigation is necessary. F does not have a relative minimum nor a relative maximum at x equals 2 because its derivative there is not 0. So there is our conclusion. There is no extreme value at x equals 2. Moving on to part D. Find the values of the constants m and b for which the line y equals mx plus b is a solution to the differential equation. All right, well, if y equals mx plus b, what is dy dx, the derivative? Naturally, that would just be m, the slope. So we would need m to equal 2x minus y. All right, let's write this down and start doing some work. All right, again, if y equals mx plus b, its derivative is just the slope, which is m, which, if it's a solution to our differential equation, we know that this should equal 2x minus y, because that is the differential equation that it must satisfy. Now, what can we do with this? Well, we might have that m equals 2x minus y, but we also know that y equals mx plus b. So this is the same as m equals 2x minus mx minus b. We can then do some factoring to see that m must equal 2 minus m times x. That's factoring the x out of those two terms. And then, of course, minus b. Now we can use a method called equating coefficients. On the left side, we see there are no x's. The coefficient of x is 0. So 0 must equal the coefficient of x on the right side, which is 2 minus m. 0 must equal 2 minus m, which means that m must equal 2. On the other hand, there's one constant on the left, which is m, which has to equal the constants on the right, negative b. So that gives us this other equation, m equals negative b, which if we want to learn about b here, we could say that means that b equals negative m. And since we found that m equals 2, this means that b must equal negative 2. So there is one possibility for m and b in order to have a curve, or in this case a line, that satisfies the differential equation in question. That one pair of values is m equals 2 and b equals negative 2, which gives us this solution curve y equals 2x minus 2. And that completes our solution to free response question 4 from the 2015 AP Calc AB exam. This is free response question 3 from the 2023 AP Calc AB exam. A bottle of milk is taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius and t is the number of minutes since the bottle was placed in the pan. M satisfies the differential equation dm dt equals a fourth times 40 minus m. At time t equals 0, the temperature of the milk is 5 degrees Celsius, so we have a nice initial condition there. It can be shown that m of t is less than 40 for all values of t. All right, part A. A slope field for the differential equation dmdt equals, etc., is shown right here. We are asked to sketch the solution curve through this given initial condition 0, 5. So coming down to the slope field, notice that this point 0, 5 is already labeled on the picture for us. We just have to sketch the curve that is in agreement with the slope field. So that curve should generally follow the path of the tangent lines, something like this. And then it's got sort of a horizontal asymptote around m equals 40. And so it would continue to proceed in this manner. The rate at which it is increasing is getting very, very slow as time goes on. When you first started graphing things like lines back in the day, your teacher might have often told you to make sure to put arrowheads at the ends. So it's perhaps interesting to note that according to the College Board's official scoring guidelines, you do not need arrows on this graph. So this would be a perfectly fine answer. All right, anyways, let's move on to part B. Use the line tangent to the graph of m at t equals 0, so using that initial condition that we have, to approximate m of 2, the temperature of the milk at time t equals 2. Remember, what a tangent line is a linear approximation of a function at a point. We're looking for the tangent line at t equals 0, so if I were to sketch that in blue, that might look something like this, and for values of t near t equals 0, this line is a decent approximation of the function. So we'll need to find the equation for this tangent line, which requires a point and a slope, and then we'll plug t equals 2 into that equation to get an approximation of the temperature of the milk. Let's do part B down here. Like we said, we need a point and a slope for an equation of a tangent line. The slope we'll figure out, we'll put it in that box. The point is very straightforward. We're given the point as the initial condition. At time t equals 0, the temperature of the milk is 5. So the point is y minus 5, y minus the y-coordinate, equals the slope multiplied by x minus the x-coordinate, or in this case, the t-coordinate, and that is 0. And in fact, instead of using y and x, let's be consistent with the context here. The y is m, the temperature of the milk at time t, and the x is t, the time since the milk was placed in the pan. All that's left for this equation is to find the slope, which is dm dt at the time t equals 0. And this is easy to calculate with our differential equation. The differential equation given was 1/4 multiplied by 40 minus m. However, we know that when t equals 0, m is 5. That was given to us. So we can replace m here with 5. Thus, the slope that we're looking for is 1/4 of 35, or 35 over 4. Since we're trying to approximate m, the temperature of the milk, let's solve this tangent line equation for m. That's going to give us m equals 35 over 4t plus 5. Then, to approximate the temperature of the milk at time t equals 2, we just have to plug 2 into this tangent line. So that's going to be 35 over 4 multiplied by 2 and plus 5. This is 17.5 plus 5, or 22.5. And this, of course, is in degrees Celsius. And there is our written out conclusion. The temperature of the milk at time t equals 2 is about 22.5 degrees Celsius. We just found the equation of the tangent line using that initial condition that we had, and then plug in t equals 2. Moving on to part C. Write an expression for the second derivative of m with respect to t in terms of m, and then use this expression to determine whether the approximation from part B that we just got is an underestimate or an overestimate for the actual value of m of 2, and give a reason for our answer. All right, so we will take the differential equation 1/4 times 40 minus m, and we'll differentiate both sides to get the second derivative. So here is the differential equation. Differentiating the left side gives us the second derivative of m with respect to t, and differentiating the right Well, there's two things going on here. There's 1/4 times 40, which is just a constant whose derivative is 0. And then the other thing is minus 1/4 m. The derivative of minus 1/4 m is minus 1/4. But since m is a function itself, which is changing with respect to time, we also have to multiply by its derivative, which is dm dt. Because remember, we're not taking the derivative with respect to m, we're taking the derivative with respect to t, and m is a function of t. Now we can simplify this because we know what dm dt is. It's written right here. That was given to us. So this second derivative is negative 1/4 times dm dt, but dm dt we know is 1/4 times 40 minus m. And finally, we can write this as negative 1/16, combining the negative fourth and the positive fourth, multiplied by 40 minus m. This is an expression for the second derivative purely in terms of m. Now, based on this second derivative, is our approximation from part B an overestimate or an underestimate? Well, if our function is concave up, then the tangent lines are underestimates. On the other hand, if the function is concave down, the tangent lines are overestimates. So we need to assess the sign of this second derivative. As far as the sign goes, there is a negative here, so the second derivative is going to be negative unless 40 minus m is negative, because then the two negatives would cancel out. So is 40 minus m negative? No, it's not. We know for sure that 40 minus m is positive because we know for sure that m is less than 40. That was given to us in the question. It said right here that it can be shown that m of t is less than 40 for all values of t. So for sure, this part 40 minus m is positive. So for sure, the second derivative is negative, which means the function is concave down, and so our tangent line approximation would have been an overestimate. And there that reasoning is written out. Let's move on then to part D. Use separation of variables to find an expression for m of t, the particular solution to the differential equation dm dt equals 1/4 times 40 minus m, with the initial condition we've been working with so far, m of 0 equals 5. All right, so we will use separation of variables, and then we will use this initial condition to get the particular solution. And let's see if we can fit part D over here. The differential equation we have is dm dt equals 1/4 times 40 minus m. Now, we need to separate the m's and the t's. We'll want the m's over on the left with the dm, and then we'll move the dt over to the right. To get the m's over to the left side, we'll divide both sides by 40 minus m. Thus, we'll have 1 over 40 minus m dm, and then multiply both sides by dt, and so we have 1/4 dt on the right side. Now we can go ahead and integrate the left and right sides. Integrating 1 over 40 minus m gives negative natural log of absolute value 40 minus m. And on the right, we have 1/4 t. Let's suppose that all of the arbitrary constants we gathered to the right side, and so I'll just put a plus c over there on the right. Notice this negative came from the fact that 40 minus m inside the log has a derivative of -1. So this negative is there to undo that. And we need the absolute value bars because you can't have negatives in the natural log. Although, oh wait, we already know that 40 minus m isn't negative. It's always positive. So in fact, we don't need those absolute value bars. Let's just use parentheses. Now let's go ahead and use our initial condition to solve for the constant c. We know that when t equals 0, the temperature of the milk, m, is 5. So on the right side of the equation, we have 1/4 times 0 plus c. And on the left side, we have negative natural log of 40 minus 5. So on the right, we're just going to have c, and thus this tells us that c equals negative natural log of 35. That is the value of c, so we can move on with this and find our particular solution by solving for m. This is our equation now that we've replaced c with its known value. Let's go ahead and multiply both sides by -1 to get rid of this negative in front of the log on the left. So we have the natural log of 40 minus m. Multiplying the right side by -1 turns it into natural log of 35 minus a fourth t. Then we'll have to exponentiate both sides as we continue to try to get m by itself. So to get rid of this log, we need to exponentiate both sides. On the left, exponentiating the ln will just cancel it out, and so we'll have 40 minus m. And on the right, we'll have e to the ln 35 minus 1/4 t. Now, by our exponent laws, we can split that up into e to the ln of 35 times e to the minus a fourth t. This, of course, works out nicely because e and ln cancel out. So we have 40 minus m equals e and ln cancel out to just 35, multiplied by e to the negative 1/4 t. Then we can add m to both sides and subtract this guy from both sides. Then we'll have m all by itself equals 40 minus this term, so minus 35e to the negative 1/4 t. And that completes our solution to free response question 3 from the 2023 AP Calc AB exam. Next up are problems on series. For these, it's useful to know the general form of the Maclaurin series and the Taylor series. It's also useful to keep in mind that if you have a Taylor series, say for a function like sine of x, you can find a series for similar functions like sine of x squared by replacing the input x in your Taylor series with x squared. Good luck. This is problem 6 from the 2001 AP Calc BC exam. So this would have been the final question. No graphing calculator allowed. Let's take a look. A function f is defined by f of x equals this power series, where we can see a general nth term given there. This equation, of course, is only true for all x in the interval of convergence of the given power series, so that's the domain. And part A is to find this domain, this interval of convergence for the power series. And of course, we must show the work that leads to our answer. So let's go ahead and get into part A. We're going to use the ratio test. This is what the series in question looks like. The form, of course, was given to us, and we know that n has to start at 0 so that we agree with that first term, because there shouldn't be any x's in that first term, so we need x to the power of 0 for that first term. Now, hopefully you remember the ratio test. The ratio test involves a limit statement, and we take the limit of this expression, the absolute value of the n plus 1th term of the series divided by the nth term of the series. And in this case, that's going to work out pretty well, because 3 to the n plus 2, I say n plus 2 because we're plugging in n plus 1. So 3 to the n plus 2 and 3 to the n plus 1 are going to cancel out fairly nicely, and n plus 2 and n plus 1 will also cancel out as n goes to infinity. We have to take this limit as n goes to infinity, and when we do that, n plus 2 and n plus 1 are barely different, right? They would approach 1. So let's go through the details of evaluating this limit. Again, this is the ratio test, and we don't need our series to have any special properties to apply the ratio test. We can just jump right in to the limit. So for the ratio test, like I said, we're going to take the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. We're going to write that division, though, as multiplication by a reciprocal. Let's begin with the n plus 1th term. So where you see n, we are plugging in n plus 1. So the numerator, n plus 1, is actually going to be n plus 1, which is n plus 2. Again, that's because we're replacing n with n plus 1. We also have x to the n plus 1 up here. And then in the denominator, we have 3 to the n plus 1, but we're plugging in n plus 1 for n, so that's 3 to the n plus 2. Then we divide by an. To do that, we'll multiply by the reciprocal. So the stuff in the numerator, n plus 1 and x to the n, will be in the denominator. We have n plus 1 and x to the n. And the denominator, 3 to the n plus 1, because we're multiplying by the reciprocal, that's going to go up to the numerator. Now, we just have to see what needs to be true about x to make this limit less than 1. The ratio test tells us that the series is going to converge so long as this limit equals something less than 1. So we need to see what condition does this force on x. And in order to figure that out, we're just going to have to make some simplifying steps. And there is a lot of simplification we can do here. I just duplicated the limit so we can start crossing stuff out. 3 to the n plus 1 and 3 to the n plus 2 almost completely cancel out. It just leaves one factor of 3 in the denominator. N plus 2 and n plus 1, those cancel out as well. In theory, we could split this up into a product of limits, and when we have just n plus 2 over n plus 1 on its own, well, as n goes to infinity, these two things are virtually identical, and so they would approach 1, and thus they're not actually having an effect on the limit. The x's will also almost cancel out. X to the n plus 1 and x to the n, that's just going to leave a single factor of x in the numerator. And so we have simplified this considerably. At this point, we don't even need the limit statement because we've gotten rid of all of the n's. So we need the absolute value of x over 3 to be less than 1. This means that x over 3 is less than 1 and greater than negative 1. Multiply everything by 3, and we get that negative 3 is less than x is less than positive 3. Now, the ratio test tells us as long as this limit is less than 1, and so all of this has to be true, then our series will converge. But it doesn't tell us anything about the endpoints, so we'll have to check these endpoints separately. We know that our series will converge when x is between negative 3 and 3, but it's possible it also converges at the endpoints. We'll have to check. And here's what happens if we evaluate those endpoints where x is negative 3 and where x is positive 3. In the negative 3 case, this x to the n, of course, becomes negative 3 to the n. The effect that has is almost canceling out with the denominator, just leaving a single factor of 3 in the denominator, and also giving us a negative 1 to the n up in the numerator. This series clearly diverges because it just gets bigger and bigger while flipping from negative to positive. In the case where x is positive 3, this x to the n is just 3 to the n, and so the same thing happens except without that negative 1, and again, this series will diverge because the terms just get bigger and bigger. The terms don't approach 0 in either case, so both of these series will diverge by what is called the divergence test. If the terms of the series don't converge to 0, the series must diverge. And so our final answer for the interval of convergence is from negative 3 to positive 3. Neither of the endpoints are valid points where the series converges, and so that is our final answer for part A. Part B asks us to find the limit of f of x, that's our power series, remember, minus a third all over x as x approaches 0. So let's write out this limit statement. X approaching 0 is within our interval of convergence, right? So this is totally valid. And also notice, as we go to write this, that we are subtracting 1/3. So this 1/3 at the start of our power series, we don't have to worry about that. That's just going to get canceled out with this minus 1/3. And we'll just be left with f of x over x, but without the 1/3. So this is what the limit statement looks like. In the denominator, of course, we have x. In the numerator, we just have our series, excluding that 1/3 at the beginning that canceled out with the minus third. So we just have 2 over 3 squared x plus 3 over 3 cubed x squared, and so on. In each term, the power of x and 3 both increase by 1, and this numerator increases by 1. So what's going to happen is one factor of x in every term will cancel out with the x in the denominator. So let's write that step. So now we're looking at the limit as x approaches 0 of 2 over 3 squared, that factor of x got canceled out, plus 3 over 3 cubed x. It did have an x squared, but one of the x's got canceled out, and so on. Every term of our series just has one less power of x. So since x is approaching 0 in this limit statement, all of these terms that have an x in them are going to go away, which just leaves this first term without the x, which is 2 over 3 squared. And so this limit is equal to 2 over 9. All right, I just shrank our work and moved it out of the way so we have a little bit more room for part C, which asks us to write the first 3 non-zero terms and the general term. So that's just like they did here, right? They wrote the first 3 non-zero terms of the series and then a term representing a general form. That's what we're supposed to do, right? The first 3 non-zero terms and the general term for an infinite series that represents the integral of this function f of x from 0 to 1. So let's go ahead and set this up. I'm going to write the integral from 0 to 1, and then I'll put our power series in here. So here's what it looks like, the integral of our power series. Now we can go ahead and integrate each individual term, and we'll be evaluating that from 0 to 1. The first term, 1/3, integrates to 1/3 x. The second term, well, we have to increase the power of x by 1, so we would increase it from 1 to 2, and then divide by that new power of 2, which is going to cancel out with that numerator. Thus, it's going to be 1 over 3 squared x to the power of 2. In the third term, the power of 2 will again go up to 3, and when we divide by that new power, we're going to cancel out the numerator. And so this is going to be 1 over 3 cubed times x to the power of 3. Then we can go ahead and integrate the general term. In the general case, you can see increasing the exponent to n plus 1 and then dividing by that new exponent will cancel out the numerator. So what does an integral of the general term look like? Well, it has 1 over 3 to the n times x to the n plus 1. And this continues. We are evaluating this, of course, from 0 to 1. When we plug in 0, all of these terms have an x in them, so they will all go away when we plug in 0. Thus, we just have to plug in x equals 1. I was just writing out what we get when we plug in x equals 1. I'm sorry though, I just noticed an error. Here where I've written 3 to the n, we should have had 3 to the n plus 1. So I'll just go ahead and correct that now. That doesn't really change anything too major. It's just that the nth term of the series has a 3 to the n plus 1. So here where I'm representing the nth term of our series, we should have 3 to the n plus 1 in the denominator. All right, so that is the series representing this integral of our series from 0 to 1, and we've written it by writing 3 non-zero terms, and then we've included a general term as well, which is exactly what the question asked for. And so we are done with part C. And we're in luck. Part D is very easy. We just have to find the sum of the series that we just found in part C. And you probably recognize that the sum we found, this thing, is a geometric series. So to find the sum of the series will be a very easy task. The first term is 1/3. Let's just call this, well, we don't have to call it S. We could just represent it as the integral from 0 to 1, because that's what it is. The integral from 0 to 1 of our function we found is equal to this series, which we can evaluate using the geometric series formula. That's going to be the first term, which was 1/3, divided by 1 minus the common ratio. The common ratio, of course, is 1/3. Each term is 1/3 of the preceding term. 1/3, 1/3 squared, 1/3 cubed, and so on. So 1 minus 1/3. And what is this? Well, 1 is the same as 3/3. So 3/3 minus 1/3 in the denominator, that's 2/3. So this is 1/3 divided by 2/3, and that, of course, is 1/2. Those 3's cancel out, and that is our answer. And that completes our solution to free response question 6 from the 2001 AP Calc BC exam. This is free response question 6 from the 2002 AP Calc BC Form B exam. The Maclaurin series for the natural log of 1 over 1 minus x is this sum, with an interval of convergence from -1 to +1. Part A asks us to find the Maclaurin series for the natural log of 1 over 1 plus 3x and determine the interval of convergence. Now, this expression, the natural log of this, is super similar to this expression for which we already have a Maclaurin series. So all we have to do is take this series and replace the x with whatever we would need to replace the x with in this expression to produce the desired expression. So for part A, what we want is 1 plus 3x in the denominator. What we were given was 1 minus x in the denominator. So we just need to replace x with minus 3x. If we plug minus 3x in for x, we're going to get plus 3x because of the double negative, right? That's going to give us what we want. So in the known Maclaurin series that we were given, we will just replace x with negative 3x. So the natural log of 1 over 1 plus 3x is equal to this Maclaurin series. So that's the sum from n equals 1 to infinity of negative 3x to the n, because we're replacing that x with negative 3x, negative 3x to the n, divided by n. Again, all we did was replace x in the given series with what we need to replace x with in the expression in order to produce the expression that we want. Now, where does this Maclaurin series converge? Well, we know that the expression we used has its Maclaurin series convergent when the input is between -1 and +1. So our input, which is negative 3x, needs to be between -1 and +1. And make sure you pay attention to the strictness of the inequality. Our input, negative 3x, needs to be greater than or equal to -1 and less than 1. So the interval of convergence, we just need to solve this for x, so divide everything by -3. That then produces x is greater than -1/3 and less than or equal to +1/3. And that is our interval of convergence. We just took the interval of convergence of the original input, changed the input to our new input, which is -3x, and then solve for x. Moving on then to part B. Part B asks us to find the value of this infinite series. And this is just the given infinite series, notice, but with -1 plugged in for x. Is -1 in the interval of convergence of the original series? Yes, it is. X is greater than or equal to -1. So this series in part B is just the original given series with an input of x equals -1, which means it equals the natural log of 1 over 1 minus x, where x is -1. So for part B, we are evaluating this series from n equals 1 to infinity of -1 to the n divided by n. And we know from the given information that's just this natural log expression, but with x equals -1 plugged in. So the natural log of 1 divided by 1 minus -1, and 1 minus -1 is just 2. So this is the natural log of 1 over 2. All right, moving on to part C. Give a value of p such that the infinite series, as shown here, converges, but this one, where the power of n in the denominator has been doubled, diverges. And we need to give reasons why our value of p is correct. Now, note, this series is just a p series, but instead of p, the exponent is 2p. Now, a p series in general will diverge when this exponent of n is less than or equal to 1. So we would just need p to be less than or equal to 1/2. That way 2p is less than or equal to 1. And in fact, p equals 1/2 is a perfectly good answer. Plugging p equals 1/2 into this other series, which needs to converge, yes, indeed it will converge, because it's an alternating series where the terms converge to 0. n to the 1/2 is just a square root of n, which certainly diverges to infinity. Meanwhile, the numerator is just alternating between +1 and -1. So yes, by the alternating series test, this series would converge for p equals 1/2. So there's our conclusion for part C. For p equals 1/2, this series converges by the alternating series test, but this series is the harmonic series and thus diverges, right? This is the series of 1 over n to the 2p. If p equals 1/2, then 2p is just 1, and so this is actually just the harmonic series, which is known to diverge. For the alternating series test, I should point out it's important that the absolute value of the terms are decreasing, which is the case, because again, the numerator has an absolute value of 1 the whole time, whereas the denominator is just diverging to infinity, because it's root n. In the case that p is 1/2. Part D asks us to give a value of p such that the series 1 over n to the p diverges, but 1 over n to the 2p converges, unlike last time where 1 over n to the 2p had to diverge. And of course, we need to give reasons why our value of p is correct. Now, 1 over n to the 2p would diverge when the exponent of n is between 0 and 1. Inclusive. To converge, on the other hand, we need the exponent of n to be greater than 1 so that the terms get small enough, fast enough for the series to converge. This is just a p series we're talking about. Now, if we need 2p to be greater than 1, p just needs to be greater than 1/2. We could pick a simple fraction like 3/4, for example. Choosing p equals 3/4 will also make this series diverge as necessary, because in this case, the exponent of n would be between 0 and 1, p equals 3/4. But over here, the exponent of n would be greater than 1, because 2 times 3/4 is 6/4. So here's our answer. For p equals 3 over 4, the series 1 over n to the p diverges because it's a p series with p between 0 and 1. But the series 1 over n to the 2p, which is equal to 1 over n to the 1.5, converges because it's a p series with p greater than 1. And that completes our solution to free response question 6 from the 2002 AP Calc BC Form B exam. This is free response question 6 from the 2016 AP Calc BC exam, part of the no calculator section. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 equals 1, f prime of 1 equals -1/2, and the nth derivative of f at x equals 1 is given by this equation here for n greater than or equal to 2. So we have all the information we need to write the Taylor series. Part A asks us to write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 1. So we'll put part A down here. In order to answer this question, naturally, you have to know what a Taylor series looks like in general. In general, a Taylor series will look like this. The nth derivative of the function f evaluated at the center a, in our case the center is 1, multiplied by x minus the center to the power of n, and then divided by n factorial. So we want to keep that in mind as we begin to write the first 4 non-zero terms of the Taylor series for our function f of x. The first term of the Taylor series is with n equals 0, so the 0th derivative of the function, which is just the function evaluated at the center. So that's just the function evaluated at 1, which is given to us as 1. So we're going to have a 1 there, and then everything else when n equals 0, everything else is just 1. X minus a to the 0 is 1, and 0 factorial in the denominator is 1. So that's the first term of the Taylor series. We can move on to the next term when n equals 1. Then we have the first derivative, f prime, evaluated at the center, which is 1, and we're told that f prime of 1 is -1/2. So we're going to have minus a half, and then we have x minus the center of 1 to the power of 1 divided by 1 factorial. We don't have to divide by 1 factorial because that's just a division by 1. So we'll just write the x minus 1 part, which is in the numerator. X minus 1 to the power of 1. I'm not going to bother writing that power though.
Then let's move on to the next term, term 3, where n equals 2. For this term, we're going to have to consult the somewhat complicated equation it gave us for evaluating the nth derivative of the function at 1. Let's worry about the simpler parts first before we do that. We're going to have x minus 1 to the power of 2, because this is n equals 2, the third term, and then divide by n factorial. Again, in this case, that's 2 factorial. All right, then all of this is going to have to be multiplied by the second derivative of the function evaluated at 1, and we are told how to find that. We're told up here that to evaluate this, we need negative 1 to the power of 2 multiplied by 2 minus 1 factorial divided by 2 to the 2. Now, negative 1 to the 2 is just positive 1, so we don't have to worry about that. 2 minus 1 factorial is just 1 factorial, so we don't have to worry about that either. We just have to worry about the 2 to the 2 in the denominator. So coming back to this expression, we actually have more space in the numerator than we need, but in the denominator, we have to add a 2 squared. That's part of multiplying by the second derivative of the function, evaluated at 1. And there we go. Those are the first 3 non-zero terms. We need to write one more non-zero term, and then we can write the general term. So now we're doing this again, but with n equals 3. So let's again focus on the easy pieces first, x minus 1 to the power of 3, and divide by 3 factorial. And now let's consult the equation for the derivative again. We're looking for the third derivative of the function, evaluated at 1, which is going to be negative 1 to the 3, which is just negative 1, multiplied by 3 minus 1 factorial, which is 2 factorial, divided by 2 to the 3, so divide by 2 to the 3. All right, so we just have to add all that stuff in here via multiplication. The plus becomes a minus because we have this negative factor. And then in the numerator, we have 2 factorial, and in the denominator, we have 2 cubed. And that is going to be the fourth non-zero term. Notice, however, in this term, the factorials cancel out a bit. 2 factorial divided by 3 factorial. If you think about what that is, everything cancels out except the 3 in the denominator. So we might as well rewrite that in that slightly simplified form. 2 factorial is going to be canceled out by the 3 factorial in the denominator, and all that's left behind is that factor of 3. With that done, we can go ahead and move on to writing the general term of this Taylor series. The general term is going to look just like that. So we're going to have the nth derivative of the function evaluated at the center, which is 1, multiplied by x minus the center to the power of n, and then all of this is divided by n factorial. Now, of course, we know what the nth derivative of the function is, evaluated at 1. It's given to us here. So let's replace this fn of 1 with the given expression. Fn of 1, we know, is negative 1 to the n, and then multiply by n minus 1 factorial. So we're going to have to make a little bit more room up here in the numerator, n minus 1 factorial. And then we also have to divide by 2 to the n. So we'll also throw a 2 to the n down there in the denominator. So that's what a general term of this series looks like. But just like in the previous term, this one here, we have factorial cancellation. N minus 1 factorial divided by n factorial. Those are going to cancel out completely except for a factor of n in the denominator. So we might as well go ahead and simplify this a little bit. Those factorials are just going to leave n behind in the denominator, and so the general terms of our series will look like that. You want to make sure to also include the plus ... at the end to indicate it's a series. It goes on forever. Let's move on now to Part B. Part B says, the Taylor series for f about x equals 1 has a radius of convergence of 2. We want to find the interval of convergence and show the work that leads to our answer. So for part B, we already know this series is centered at x equals 1, and we know the radius of convergence is 2. So we could go up 2 to get to 3, and we could go back 2 to get to negative 1. The question is, do the endpoints also result in a convergent series? We know everything in here, everything between these bounds is going to be convergent if we plug those x values into the series. But
what about the endpoints? That's what we actually have to figure out for this question. Does the interval of convergence look like this? X is less than or equal to 3 and greater than or equal to -1. Or maybe x can't equal -1, it has to be strictly greater than -1, or any other combination of inequalities. That's what we're asking. Does the series converge for these endpoints? The information about the interval is pretty much given to us, right? We know the center is 1, we know the radius is 2. That's how we get -1 and 3. The only lingering question is, does the series converge at the endpoints or not? To figure that out, let's first consider the lower endpoint. If we plug -1 into our series, what's going to happen? Well, let's look at a general term of our series to get a sense of what that's going to look like. X minus 1. If x is -1, then x minus 1 is -2. And so this is actually -2 to the power of n. Then the negative with that 2 would cancel out with this -1. So in fact, there would be no negatives. What we would have left would be 2 to the n divided by 2 to the n times n. Oh, so the 2 to the n's cancel out, and this is actually just the harmonic series, 1 over n. We just have to be a little bit careful, because seeing that this actually is the harmonic series when x equals -1, that was using this general term, which relied on this derivative formula. The derivative formula that applies only when n is at least 2. So what happened for n equals 0 and n equals 1? Well, looking at these terms, the first term obviously is 1. The second term, if x is -1, the second term is just -1/2 times -2, which is also just +1. So what our series would look like for f of -1 is 1 plus 1, and then at n equals 2 is when the harmonic series kicks in. 1 over 2 plus 1 over 3, and so on. Again, that's because the harmonic series that we found resulted from considering this derivative formula, which only applies when n is at least 2. We were given specific values rather than a formula for the other possibilities. So for x equals -1, this is what our series looks like. Clearly, it's just the harmonic series with 1 added at the beginning. So yeah, this is going to diverge. It's not actually in the interval of convergence. So we can start to write our interval. X definitely has to be greater than -1. When x equals to -1, we basically just get the harmonic series, which diverges. All right, to finish this up, let's consider what happens if we plug in the upper bound. What is f of 3? Again, let's come over to the general term of our series in order to figure out what this would look like. If we're plugging in x equals +3, then this guy, x minus 1, is going to be 3 minus 1, so +2. So again, we're going to have 2 to the n divided by 2 to the n. The 2 to the n's will cancel out. It's just that in this case, there's nothing to cancel out the -1. So we're still going to have that alternating behavior resulting from the -1. So this is actually just going to be like an alternating harmonic series, with the exception again that it starts with those two ones, except in this case, the second one is negative, because 3 minus 1 is 2 times -1/2 is -1. So 1 minus 1 plus 1/2 minus 1/3, and so on. It's just an alternating harmonic series. This converges. The alternating harmonic series converges, and having a +1 at the beginning does not change convergence. So the interval of convergence does not include -1, but it does include +3. So that's the interval. Let's move on then to part C. The Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms, so these 3 terms, to approximate f of 1.2. So you can approximate f of 1.2 by taking as many terms of the series as you like. The more terms you take, the better approximation you get. We're going to use the first 3 terms because that's what the question asked us to use. So what is f of 1.2? Well, based on our series, it's about these 3 terms, which I'll just go ahead and copy and paste, but we're going to plug in 1.2 for x. So I'll bring these right down here, change it so it's color matches. And let's just consider plugging in 1.2 for x. 1.2 minus 1, that's just going to be 0.2. So right there we get 0.2.
1.2 minus 1, that's just going to be 0.2. All right, so here we go. Let's just finish with this calculation. 1/2 times 0.2 is 0.1. So this is 1 minus 0.1, which is 0.9. As for this fraction, let's see, what do we have? 0.2 squared, that's going to cancel out with the 2 squared in the denominator. It's just going to also leave a factor of 1/10 squared, which is 100 in the denominator. There's also a 2 factorial in the denominator, which is just 2. So this is 0.9 plus 1 over 200. Just like 1 over 20 is 0.05, 1 over 200 is 0.005. So this sum is 0.905. That is our approximation, which finishes part C. So moving on to part D. Show that the approximation found in part C, this approximation of 0.905, is within 0.001, or 1,000th, of the exact value of f of 1.2. In this case, we're dealing with an alternating series, and there's a nice way to estimate the error on an alternating series approximation. And here is that application of the theorem for the remainder of an alternating series approximation. The series for f of 1.2, we looked at the first 3 terms of that series in part C, but the series, the one that goes on forever, alternates with terms that decrease in magnitude to 0. We know that because this is our series. We're thinking about the case where x equals 1.2. So clearly the terms will decrease in magnitude to 0 because the numerator is going to be 1.2 minus 1 to the n, so 0.2 to the n. That's just going to get really small, and it's getting divided by these massive numbers as n gets larger. So yeah, it's decreasing in magnitude to 0, and the terms are alternating because of this -1 to the n. Thus, we can say confidently that the error, given any approximation, the error is going to be at most the magnitude of the first excluded term in the approximation. So in this case, when you have an alternating series where the terms are decreasing in magnitude to 0, if you approximate something with, say, n terms, the error in that approximation is at most the magnitude of the n plus 1th term of the series. For our approximation, we used the first 3 terms, so the error is at most the magnitude of the 4th term, which looks like this when n equals 3, right? Because we use the n equals 0 term, the n equals 1 term, the n equals 2 term. The first one we excluded is the n equals the fingers are weird. The first one we excluded is the n equals 3 term. That's the 4th term of the series. That's where this is coming from. The magnitude of the 4th term looks like this, and that is an upper bound on our error. Now, what does this thing actually equal? Well, let's see. The -1 just goes away because this is inside of magnitude bars. The 0.2 cubed will just cancel out with the 2 cubed in the denominator, but there will also be a 1/10 cubed left behind in the denominator, so that's 1/1000th. And then we also have that factor of 3. So 1 over 1,000 times 3. We have this in absolute value bars, but the absolute value bars don't matter now because everything is positive. Now remember, we were actually asked to show that the approximation from part C is within 1,000th of the exact value of f of 1.2. We've just shown that, hey, the error has this as an upper bound. This is equal to this, which is clearly less than 1/1000th. This is certainly less than 0.001 because this is 1 over 1,000. This is 1 over 3,000. So yes, by applying the alternating series remainder theorem, we found that the approximation from part C is within 1,000th of the exact value of f of 1.2. So pretty darn good approximation using only 3 terms. And that completes our solution to free response question 6 from the AP Calc BC exam from 2016. This is free response question 6 from the 2022 AP Calc BC exam. Here is the mark of the beast, the mark of the BC exam, an infinite series problem. The function f is defined by the power series f of x equals, and you can read this for yourself, for all real numbers x for which the series converges. Part A.
Using the ratio test, a very useful test indeed, find the interval of convergence of the power series for f and justify our answer. All right, so let's set up the ratio test. What the ratio test has us do is look at the ratio of a term of the series, say an plus 1, to the preceding term, which would then be an. We look at the absolute value of this ratio, the ratio of a term of the series to the preceding term. We look at the limit of this as n goes to infinity. And if this ratio is approaching something less than 1, then the series converges. So for part A, here's what that looks like setting up the ratio test for our series. Notice in the numerator, we've plugged n plus 1 into the general form of a term of the series. So for example, when we plug n plus 1 in right there, that becomes 2 times n plus 1, which is 2n plus 2, but there's also a plus 1 over there, so that's why we have this 2n plus 3 right there. So this whole thing in the numerator is the n plus 1th term of the series, and then we're dividing by the nth term. So here in the denominator, what you see looks just like this. That's the nth term of the series. This, of course, is all in an absolute value, so we will be able to discard those negatives. And we're taking the limit of this as n goes to infinity. The idea is that we'll try to simplify and evaluate this limit, and whatever ends up equaling, we need that thing to be less than 1, which will typically place some restriction on x. This turns out to be fairly easy to evaluate. The ratio test often does work pretty nicely, no major difficulties. This first step is just discarding those negatives, like I said before. We have these absolute value bars. Those negatives then aren't going to do anything. Then, let's simplify the x's. X to the 2n plus 3 divided by x to the 2n plus 1. That's just x squared. Most of those factors of x will cancel out, but there are 2 more factors of x in the numerator than there are in the denominator. So we're left with an x squared. As far as the n's go, this division by 2n plus 1 in the denominator of a fraction gets sent up to the numerator. It's like multiplying by the reciprocal, right? And then this guy, 2n plus 3, that stays in the denominator. So we have 2n plus 1 divided by 2n plus 3. Now as n goes to infinity, 2n plus 1 and 2n plus 3 behave pretty much the same. Their ratio approaches 1. The addition of a constant at the end doesn't really do anything, because as n gets really, really big, the primary character here is the 2n. So these will have a ratio approaching 1. And so the limit of this is just the absolute value of x squared. That is the limit of this thing, and we need this to be less than 1 in order for the series to converge. Then the absolute value of x squared, which is this limit, being less than 1, that implies that the absolute value of x is less than 1. Thus, the series converges when x is between -1 and +1, because that's when it has an absolute value less than 1. Unfortunately, we do also have to separately consider the case where the absolute value of x equals 1. In that case, when this limit equals 1, the ratio test is not conclusive. So although we know it does converge in this interval, we do have to check the endpoints, because right now we cannot say anything definitively about the series behavior at the endpoints. So let's check the endpoints. We'll start with x equals -1 and see how the series behaves. If we plug in x equals -1, the first term of this power series is going to be -1, and then we'll have plus a third, and then minus a fifth, and then plus a seventh, and so on. It looks like this. And this is an alternating series, which we can quickly see converges by the alternating series test. Because it's an alternating series, right? It goes negative, positive, and so on. And the absolute values of its terms are decreasing to 0. The absolute values of the terms are just reciprocals of odd numbers. 1, a third, a fifth, a seventh, and so on. So the absolute values are approaching 0, and they're decreasing. Thus, by the alternating series test, this series converges. So the interval of convergence for our series includes -1. Now let's check x equals +1. Turns out it's going to be practically the same. If we go back up to our power series, if x equals +1, then we're going to have 1 minus a third plus a fifth minus a seventh. So same idea. When x equals +1, the series looks like this, which again is an alternating series with terms whose absolute values decrease to 0. Thus, by the alternating series test, the AST, this series will converge. So it actually converges at both of these endpoints, both -1 and +1. So we can state with confidence our final interval of convergence. The interval of convergence is x less than or equal to 1 and greater than or equal to +1. All right, that completes part A, which took up quite a bit of space, so we will have to shrink this to give us some room for part B. Part B is to show that the absolute value of f of 1/2 minus a half is less than 1/10. Let's do part B over here. We know certainly that f of 1/2 is a convergent series, because in part A we showed that the interval of convergence is everything from -1 to +1. So certainly it's convergent at x equals 1/2. It's also an alternating series, because we could just see from the definition it is alternating. Thus, we can use the alternating series error bound. Notice that the first partial sum of the series, which is just the first term, in this case is 1/2. If we plug in 1/2, that first term, which is the first partial sum, will be 1/2. So the alternating series error bound tells us that the distance between 1/2, the first partial sum, and the actual value that the series converges to, the distance between them, which is what we're trying to prove something about for part B, that distance has to be less than the absolute value of the next term of the series. Once again, what the alternating series error bound tells us in general is that the distance between the true value of an alternating series and its nth partial sum is less than the absolute value of the n plus 1th term. If you add all of the terms up to the nth term, that has to be within the absolute value of the next term of the true value that the series converges to. A lot of words there. Hopefully this makes sense. Check out a video introducing the alternating series error bound if you need a review of that. But as far as this goes, let's see. What is the second term of the series? We know the distance we're interested in is less than the absolute value of the second term of the series. So what is that? Well, if we're plugging in x equals 1/2, the second term of the series is 1/2 cubed divided by 3. And of course, this is in an absolute value. So 1/2 cubed divided by 3. This, of course, is 1/8 divided by 3, which is 1/24. The absolute value is not going to do anything to it at this point. That's 1/24, and remember, we were trying to show that this distance is less than 1/10. We've shown that it's less than 1/24, which is indeed less than 1/10, since this denominator is bigger than this one. Thus, we have completed part B. By the alternating series error bound, the distance between f of 1/2 and 1/2 has to be less than 1/10. Moving on to part C. Write the first 4 non-zero terms and the general term, so just like this, the first 4 non-zero terms and a general term, for an infinite series that represents the derivative f prime of x. All right, let's do part C down here. For convenience, I have rewritten the power series f of x. We're just going to have to use the power rule to take the derivative of this guy. All right, so what is f prime of x? The first term would be 1. Then we're going to have minus x squared, because the exponent of 3 comes down as a factor, cancels out the denominator, and then the power gets reduced by 1. So we're just left with an x squared. The next term will have a derivative of x to the 4 plus x to the 4. The next one is minus x to the 6, and so on. You can see how this works. We're getting alternating signs with the even powers of x. The general term is going to be -1 to the n. That checks out because when n equals 0, this would just be 1, and we do need that first term to be positive, so there should be no negative factor when n equals 0. So we know that works fine. And then the power rule applying to the rest of this is just going to give us x to the 2n. Of course, we've just got an even power there. And that is it. That is f prime of x. We've got the first 4 non-zero terms and a general term. This is just using the power rule, which we can see behaves very nicely with this function. Finally, we can move on to part D, which says use the result from part C to find the value of f prime of 1/6. So what is the value of f prime when x equals a sixth? Well, let's plug it in. F prime of 1/6, based on our previous work, is going to be 1 minus 1/6 squared plus 1/6 to the power of 4 minus 1/6 to the power of 6, and so on. This, hopefully you notice, is a geometric series. It's geometric where each term has a ratio of -1/6 squared with the previous term. Notice, if we multiply 1 by -1/6 squared, let me rewrite that 6, we get here. And then if we multiply this by -1/6 squared, we get here, right? You've got it positive now because of the two negatives, and 1/6 to the 4 because square and the square, and this continues. Each term has a ratio of -1/6 squared with the preceding term. Clearly then, this is geometric. And again, that ratio is -1/6 squared. And the absolute value of this is less than 1, which means that it will converge. This is a geometric series that converges. Now, what does it converge to? Well, hopefully you remember your geometric series formula. F prime of 1/6, it's a geometric series. It's going to converge to this. The first term, which is 1, divided by 1 minus the common ratio. The common ratio is -1/6 squared. This, of course, is the same as 1 over 36 over 36. That's because 1 is just 36 over 36. And minus 1/6 squared is minus 1 over 36. But since we're subtracting it, it's like we're adding it. So it's plus 1 over 36. So this is actually equal to 1 over 37 over 36. And dividing by 37 over 36 is the same as multiplying by the reciprocal. So our final answer is 36 over 37. And there you go. That's a pretty fun problem, isn't it? That completes our solution to free response question 6 from the 2022 AP Calc BC exam. Next up are the polar coordinate problems. Recall that if you're trying to find the area of a polar region, you can't just integrate the polar curve. This comes from the area of a sector of a circle. What you actually have to do is 1/2 times the integral of your r function squared. It's like 1/2 radius squared over whatever your relevant interval is, which will be in terms of theta. Have fun. This is problem 4 from the 2009 AP Calc BC Form B exam. So this was part of the no calculator section, and this is on polar curves, something which is not in the AB exam. The graph of the polar curve r equals 1 minus 2 cosine theta for theta between 0 and pi is shown above. We see this beautiful curve here. Let S be the shaded region in the third quadrant bounded by the curve and the axis, so we can see the region S there. Part A is to write an integral expression for the area of this shaded region S. So we just have to write the expression, we don't have to evaluate it. This is a pretty straightforward question, you just got to remember how to find the area of a polar region. It of course is going to be an integral, and we have a 1/2 out front, and then the radius, or r, squared. In this case, r is given to us as 1 minus 2 cosine theta. And we need to square this, and the integral is taken with respect to theta. Remember, this 1/2 and the radius squared comes from the fact that when we figured out how to do this originally, it comes from the area of a sector of a circle. Just like traditional integrals are built from rectangles, polar integrals are built from sectors of circles. And that's why we have 1/2 integral r squared. That's how we're going to calculate the area of this region. The question is, what are the bounds, the lower bound and the upper bound? Well, we have to think. Let's look at this picture. We see that the region S starts where r equals -1. So we need to figure out what theta value gives us an r of -1. That will be the lower bound of our integral. Now, the curve, or the region, I should say, is closed. The region is closed when the curve comes back to this point, the origin. That's where r equals 0. So we'll also have to figure out where does theta make r equal to 0, and that's going to be the upper bound of the integral. Let's begin with -1. So we'll write 1 minus 2 cosine theta, that's our r, is equal to -1. Subtract 1 from both sides, and we find that -2 cosine theta equals -2. Divide both sides by -2, and we find that cosine theta equals +1, and thus theta equals 0. Cosine of 0 is 1, so theta is 0. That's the lower bound of our integral, and we'll do a similar thing for r equals 0. We'll say that 1 minus 2 cosine theta equals 0. Remember, we're trying to find the upper bound of our integral now. And let's add 2 cosine theta to both sides. So 1 equals 2 cosine theta. And then divide both sides by 2. So 1/2 equals cosine theta. And if you remember your unit circle, which you should, this means theta has to equal pi over 3. Cosine takes on a value of 1/2 at the angle pi over 3. So that's the upper bound of our integral, and that actually completes the answer to part A. That is our integral expression. Remember, this all comes from the standard way that we calculate the areas of polar regions, which is integrating from A to B, 1/2 out front, r squared d theta. This is how you find the area of a polar region, and that's all we did for part A. All right, moving on to part B. Write expressions for dx d theta and dy d theta in terms of theta. Okay, so you'll have to remember some formulas for this. We know that x is equal to r cosine theta, and y is equal to r sine theta. These are relationships between Cartesian coordinates and polar coordinates that you should know. Now, in order to find dx d theta, we're going to have to take the derivative of this equation, which is going to involve a dr d theta, because we're going to have to take the derivative of r. So let's just go ahead and find that first. Let's find dr d theta. We know that r is 1 minus 2 cosine theta. And if we take the derivative of that, we're just going to get 2 sine theta. So that's what dr d theta is. All right, now we can go ahead and take the derivative of x and the derivative of y. Let's start with x. Taking the derivative of this equation, both sides, we're taking the derivative with respect to theta. On the left, we have dx d theta. On the right, we have to use the product rule because we have a product of functions, r, which changes with respect to theta, and cosine theta, which of course is also changing. So the product rule is f prime g plus g prime f. In this context, that's dr d theta cosine theta plus the derivative of cosine theta, which is negative sine. So let's just write minus sine theta times r. Dr d theta, of course, we know, is 2 sine theta. So this is just 2 sine theta cosine theta. And then we are subtracting sine theta times r. But of course, r is just 1 minus 2 cosine theta. So we have minus sine theta times r, which is 1 minus 2 cosine theta. Now notice on the left, we have 2 sine theta cosine theta. If we were to distribute over here on the right, we'd have minus sine theta times minus 2 cosine theta. So that would be another 2 sine theta cosine theta. In total, then, we have 4 sine theta cosine theta. The other term we would have is minus sine theta times 1, which is just minus sine theta. And that is dx d theta. Next, we'll do a similar procedure in order to find dy d theta. So we're going to take the derivative on the left and right side of this equation with respect to theta. I'll write that here, dy d theta. What is this going to be? Well, again, it's the product rule. F prime g, so dr d theta times sine theta, plus g prime f, so cosine theta times r. Dr d theta, of course, we know is 2 sine theta. So dr d theta times sine theta is 2 sine theta times sine theta, so 2 sine squared theta. Then we add cosine theta r, but of course we know that r is 1 minus 2 cosine theta. So that is our expression for dy d theta, and thus we have completed part B, which was just to write expressions for dx d theta and dy d theta in terms of theta. So we didn't want any r's in there, and indeed these are those final answers. Moving on to part C. Part C asks us to write an equation in terms of x and y for the line tangent to the graph of the polar curve, this one here, of course, at the point where theta equals pi over 2. And we want to show the computations that lead to our answer. Now, to write the equation of a tangent line, we're going to need a point and a slope. A point is a pair of x and y coordinates. We know that x equals r cosine theta, and we know that y equals r sine theta. So, since we're looking for the tangent line at theta equals pi over 2, we can figure out what the x and y coordinates have to be. When theta equals pi over 2, x is r times cosine of pi over 2. Cosine of pi over 2, though, is 0. So x would be r times 0, which is just 0. As for y, y is r times sine of pi over 2. Sine of pi over 2 is 1, so y would just equal r. But we know r is 1 minus 2 cosine theta, but theta is pi over 2, so it's 1 minus 2 cosine pi over 2. Cosine pi over 2 is 0, so y is just 1. Thus, the point on the curve that our tangent line is passing through at pi over 2 is the point 0, 1. So we can start to write the equation of the tangent line now. Y minus 1, that y coordinate, equals the slope, which we'll figure out, multiplied by x minus the x coordinate, 0. Now, I shrunk our work in part B to make a little bit more room. To find the slope, we need to look at dy dx, because we are trying to write this equation in terms of y and x. So what is dy dx? Well, to find it, we need to take dy d theta and divide it by dx d theta. And let's just write this whole time, what we're actually doing is evaluating this, dy dx, when theta equals pi over 2. So I'll put this vertical line. That means we're evaluating the expression at theta equals pi over 2. To evaluate this, let's first focus on the numerator, dy d theta, when theta is pi over 2. Looking at our previous work, this is dy d theta. So what is it when theta is pi over 2? Well, cosine of pi over 2 is just 0, so this term would disappear. Sine of pi over 2 is 1, so sine squared pi over 2 is 1, and so 2 sine squared pi over 2 is 2. Okay, so the numerator then is 2. That's dy d theta evaluated at theta equals pi over 2. As for the denominator, dx d theta, when theta is pi over 2, let's look at our previous work right here. Again, cosine of pi over 2 is 0, so this term disappears, and all that's left is negative sine of pi over 2.
Sine of pi over 2 is 1, so that would be -1. And thus, the slope is -2, and we can plug that into this box. I'll just erase the box. We know what the slope is now. It's -2, and that is our tangent line. Or if you prefer to put it in slope-intercept form, you could say this is just -2x because the 0 doesn't matter, and then add 1 to both sides, and you'd find that y equals -2x plus 1. And that completes our solution to part C. This is free response question 2 from the 2013 AP Calc BC exam. It's part of the graphing calculator section. We will use a calculator throughout this problem. The graphs of the polar curves r equals 3, which is a circle, and r equals 4 minus 2 sine theta are shown in the figure above. The curves intersect when theta equals pi over 6, which we can see right here. I'll just go ahead and label that. And when theta equals 5 pi over 6, which is right over here. Part A asks us to consider this shaded region that's inside both the circle and inside r equals 4 minus 2 sine theta, so this shaded region here. We would like to find the area of S. Looking at this area, we can split it up into two things. Part of it is just the area under the curve 4 minus 2 sine theta between theta equals pi over 6 and theta equals 5 pi over 6. We can simply calculate the area that is under the curve using our typical polar integration methods, the 1/2 r squared. And what that leaves, that we still have to calculate, is this area that is present in the circle. Now, we know the area of the circle is just pi r squared, and since this has a radius of 3, that would be 9 pi. But this is not all of the area of the circle, so we need to figure out what fraction of the circle is it. Well, in total, a fraction has 2 pi radians. How many of the radians have we cut out? This part here is what we have cut out. Well, you've got pi over 6 here and 5 pi over 6 there. So 2 pi, 3 pi, 4 pi, 5 pi over 6. So in total, we cut out 1, 2, 3, 4 pi over 6. 4 pi over 6 out of the total 2 pi radians have been cut out. So we need to multiply by the proportion of the circle that we actually have. The total radian count is 2 pi, but if we are removing 4 pi over 6 of those radians, what remains is 8 pi over 6. Again, this is the area of the circle, so we'll go ahead and simplify this to figure out what that area is, and then we'll just need an integral to find this area that's underneath the more complicated curve. Simplifying this, we have pi's canceling out in the top and bottom, so what's left is 9 pi multiplied by 8 over 12. Now, 8 over 12 is the same as 2/3. So this is 9 multiplied by 2/3 multiplied by pi. Then we can cancel a 3 out of the 9 and the denominator, thus giving us a final answer of 6 pi. That is the area here in our circle. So for part A, we have 6 pi, and then the area of our region, which we did not already account for, we will find by just doing an integral. If we imagine a ray opening up along the polar plane, you can see that our region is bounded by the circle from here to here, which is why we calculated that part just using the circle. But then from here to here, our region is bounded by 4 minus 2 sine theta, which is why we now have to focus on this function for this part of the region. To calculate the area of this polar region, we have to do 1/2 multiplied by the integral from pi over 6 to 5 pi over 6 of our function squared. It's like radius squared. So 4 minus 2 sine theta squared d theta, and we'll bust out the calculator for this. On the calculator, I'll press math and then option 9 for the integration function. We are integrating from pi over 6 to 5 pi over 6, and what we are integrating is 4 minus 2 sine
theta, but I'm just going to use sine x because we're on the calculator. And this needs to get squared, and we're integrating with respect to x. Notice my careful use of parentheses as we enter this. That's the integral. Don't forget about the 1/2 out front. So now on the calculator, we'll divide by 2. And then add the 6 pi, so plus 6 pi. So our final answer is about 24.7087. That's the area. Moving on then to part B. A particle moves along the polar curve r equals 4 minus 2 sine theta, so that at time t seconds, theta equals t squared. Find the time t in the interval between 1 and 2, for which the x-coordinate of the particle's position is -1. So we need to think about Cartesian coordinates. X, we know, is equal to r cosine theta. Now, in this context, r is 4 minus 2 sine theta, so this is 4 minus 2 sine theta multiplied by cosine theta. But remember, our particle is moving along the curve in such a way that theta equals t squared. So we can replace these thetas with t squareds. So we have 4 minus 2 sine of t squared and multiplied by cosine of t squared. Now the question is, what time t in the interval between 1 and 2 is the x-coordinate, which is described by this expression, is the x-coordinate -1. All we have to do is go on a calculator, graph y equals -1, and graph this function, and we will see the intersection. So on the calculator, like I said, we're using y, so instead of writing x as a function of t, on the calculator, we're writing y as a function of x, but all the numbers are going to work out the same. So on the calculator, I've gone to graph the x function, 4 minus 2 sine of x squared times cosine of x squared is what it looks like on the calculator, and y equals -1. And I want to see where these things intersect, so I press the graph button to go to my graph, and I can just zoom in and see where these things intersect. Of course, how you find the intersection will depend a bit on your calculator. You might have to use a trace function. But we can see that this happens when x is about 1.428. Now, in the context of our problem, x is actually t on the calculator. So t is 1.428. We can see that there are other intersections as well, but they happen outside of the requested interval, which was between 1 and 2. So the answer we're looking for is t equals 1.428. So I'll write that this, the x position, equals -1 when t equals about 1.428. Finally, part C. For the particle described in part B, the one that moves such that theta equals t squared, find the position vector in terms of t. We already have a description of the x position in terms of t, so we'll just have to do the same thing with y. And then find the velocity vector at time t equals 1.5, and so for that we'll just need a derivative. All right, let's start putting part C down here. We know that just like x equals r cosine theta, y equals r sine theta. But again, we're talking about the same particle that's moving along r equals 4 minus 2 sine theta. So r we will replace with 4 minus 2 sine theta. But remember, theta, because we're still talking about the same particle, theta is just t squared. So sine of t squared. And then sine of theta is sine of t squared. Remember, this sine of t squared comes from r, and this sine of t squared comes from sine theta, which is part of the y equation. Now, part C wanted us to give the position vector, so the position vector is this x component and this y component. So I'll write this with angle brackets to denote that it is a vector, and we can just do a little bit of copy and paste. The x component is up here in part B, so I'll bring that down here and change its color to green. And the y component we just figured out is right here, 4 minus 2 sine of t squared times sine of t squared. And just put a comma between these and close the vector. That is the position vector. Now the other part of the problem asks us for the velocity vector at time t equals 1.5.
Velocity is the derivative of position. So all we have to do is use our calculator to evaluate the derivative of both the x and the y components at t equals 1.5. So I will write v of 1.5, and we'll see what this equals. I will do the derivative of the x component on the calculator and show you, and then I'll just do the derivative of the y component by myself so we don't spend all day looking at the calculator. So on the calculator, I'll press Math and then option 8 for the derivative function. Instead of using t on the calculator, we're going to use x. So take the derivative with respect to x. And now what we're differentiating is 4 minus 2 times sine of x squared. And this is getting multiplied by cosine of x squared. And we are evaluating this derivative at 1.5. Let's just double check that. That is at, yes, 1.5. And we get about negative 8.072. And now I'll do the same thing for the y component. And the calculator gives a derivative of about negative 1.672 for the y component at 1.5. And that is our velocity vector. So the particle is both moving to the left and moving downwards at t equals 1.5. And that completes our solution to free response question 2 from the 2013 AP Calc BC exam. This is free response question 5 from the 2018 AP Calc BC exam. You know it's from the BC exam because you can see this beautiful polar graph here. Let's read it. The graphs of the polar curves r equals 4, that's a circle of radius 4, and r equals 3 plus 2 cosine theta, which is this cardioid, are shown in the figure above. The curves intersect at theta equals pi over 3 and theta equals 5 pi over 3. Part A says, let R be the shaded region that is inside the circle, but outside the cardioid. That's this shaded region here. It's labeled very nicely for us. And what we want to do is write an expression involving an integral for the area of this shaded region. We don't even have to evaluate the integral. We just need to write it. Let's do part A down here. Hopefully you recall that the area of a polar region is found by taking 1/2 the integral from a to b, whatever those bounds happen to be, the integral of r squared with respect to theta. This comes from the area of a sector of a circle. Instead of building integrals in polar coordinates up from rectangles, like we did with rectangular coordinates, in polar coordinates, we build integrals from sectors of circles. That's where this comes from. Hopefully that's familiar. But we're looking for the area specifically between two polar curves. So we're going to need to find the area underneath one curve and subtract the area that is underneath the other. We can see in the graph that the outside curve is the circle, r equals 4, and the inside curve is the cardioid. So this is actually going to be very straightforward. All we're going to have is 1/2 times the integral from pi over 3, that was given to us, to 5 pi over 3. And again, that was given to us. We were told that the curves intersect at theta equals pi over 3 and theta equals 5 pi over 3, which you can also see there in the figure. So we're integrating across that region. Now, the outer curve is the circle, r equals 4. So we're going to have 4 squared, and then we need to subtract the smaller curve squared, or the inner curve squared. The inner curve is the cardioid, 3 plus 2 cosine theta. So we subtract 3 plus 2 cosine theta squared. This is just like finding the area between curves in rectangular coordinates, where you take the upper function minus the lower function. But of course, this is polar coordinates, so there's a little bit more going on, and this is taken with respect to theta. And why don't we go ahead and just put this whole thing in parentheses so it's super clear what we are integrating here. And that is the correct solution for part A. Now, what you have to know is that the rest of this video was recorded separately because in the first take, I accidentally did this integral wrong. Instead of writing d theta,
I wrote dr. But the rest of the first take is correct. So this part is actually recorded afterwards, but I'm going to send you back to the original recording now. You're just going to have to remember that this integral you see on screen is wrong. Everything else will be correct, but part A will be wrong. You're going to see dr instead of d theta. D theta is what it should be, but throughout the rest of the video, you're going to see dr, which is wrong. All right, enjoy the rest of the video. Moving on then to part B. Find the slope of the line tangent to the graph of r equals 3 plus 2 cosine theta at theta equals pi over 2. In order to do this, we can write an equation for x, write an equation for y, find their derivatives with respect to theta, and then we can use those to find dy dx. That's going to let us find the slope of the tangent line. So here for part B, what we are looking for is how much y changes with respect to x at theta equals pi over 2. So we're looking for dy dx at theta equals pi over 2. That's going to be the slope of the tangent line at that point. In order to do this, we need an equation for x, an equation for y, and then we need to take some derivatives. Now you should know that x equals r cosine theta and y equals r sine theta. Then we can replace r in each of these equations with what r equals. In this context, we know that r equals 3 plus 2 cosine theta. So x equals 3 plus 2 cosine theta, that's r, times cosine theta. Y also equals 3 plus 2 cosine theta, that's r, multiplied by sine theta. Then we'll distribute and differentiate. Distributing with the x equation, we have 3 cosine theta plus 2 cosine squared theta. Distributing on the y equation, we have 3 sine theta plus 2 sine theta cosine theta. Now, if this is x, we can quite easily find dx d theta. Dx d theta is the derivative of this expression with respect to theta. That's going to be negative 3 sine theta. That's the derivative of 3 cosine. And then we're going to need the chain rule over here. That's going to be plus 4 cosine theta. That's the derivative of the outside function, multiplied by negative sine theta, the derivative of the inside function. And if y equals this, we can differentiate both sides to find dy d theta. Now, on the right, we could actually simplify this a little bit to make the derivative easier. 2 sine theta cosine theta. You might recognize a double angle identity in there. That is the same as sine 2 theta. So that will make this derivative a little bit easier. Let's go ahead and find dy d theta. Dy d theta is, looking at this expression on the right, the derivative of 3 sine theta is 3 cosine theta. And then the derivative of sine of 2 theta is 2 cosine of 2 theta. Now, going back to the original goal to find dy dx at theta equals pi over 2, the way we're going to calculate this is by evaluating dy d theta at pi over 2 and dividing this by dx d theta at pi over 2. So now that we've found dy d theta and dx d theta, let's evaluate both of them at pi over 2, and then we can divide them to find the slope of the tangent line that we've been looking for. Beginning with dy d theta evaluated at theta equals pi over 2, cosine of pi over 2 is 0, so this term goes away. 2 times pi over 2 is pi, and cosine of pi is negative 1. So this term is 2 times negative 1, or negative 2. As for dx d theta, sine of pi over 2 is 1. So this is negative 3 times 1, which is negative 3. As for the other term, cosine of pi over 2 is 0, so this term goes away. Thus, dy d theta is negative 2 when theta equals pi over 2, and dx d theta is negative 3 when theta equals pi over 2. So we can come back up to our fraction and plug in negative 2 in the numerator for dy d theta, and negative 3 in the denominator for dx d theta. So how is y changing with respect to x when theta equals pi over 2? What would the slope of the tangent line be? Well, it is just 2 over 3, 2/3. That completes our solution for part B. Finally, part C. A particle moves along the portion of the curve r equals 3 plus 2 cosine theta for theta between 0 and pi over 2. The particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. We want to find the rate at which the angle theta changes with respect to time at the instant when the position of the particle corresponds to theta equals pi over 3 and indicate units of measure for this rate of change of the angle theta. So in this problem, we will be looking for d theta dt, the rate at which the angle is changing. We don't know d theta dt, we're trying to find it. We do know dr dt. The problem tells us that the distance between the particle and the origin, that's r, the radius, so to speak, is increasing at a constant rate of 3 units per second. So we'll use an equation for dr dt in order to get d theta dt involved, and then we can solve for d theta dt. So here in part C, what is dr dt? We happen to know that it's 3, but if we were just using a formula to try to calculate it, dr dt would be dr d theta, because r is a function of theta. The radius changes as the angle changes. But theta is a function of time because we're thinking about a particle tracing out our curve, the curve in this case being this cardioid. Theta is changing as time passes. So yes, dr dt is going to be dr d theta, but also we have to multiply by d theta dt, because theta changes with respect to time. This is just the chain rule. Now, we know that r is 3 plus 2 cosine theta. That is the curve that the particle is moving along, 3 plus 2 cosine theta. So dr d theta is just the derivative of this with respect to theta, which is negative 2 sine theta. So we have negative 2 sine theta multiplied by d theta dt. Then, since we have that dr dt equals negative 2 sine theta times d theta dt, let's solve for d theta dt, because that's what we're actually trying to find. We have then that d theta dt is equal to dr dt on the left side, but then we're dividing both sides by negative 2 sine theta to get the d theta dt by itself. Divide this side by negative 2 sine theta, so we have d theta dt by itself. And then on the right, we're just going to have 1 over negative 2 sine theta. Finally, recall that we want to know d theta dt when theta equals pi over 3, and we also want to indicate units of measure. So let's plug pi over 3 in this equation. So finally, what is d theta dt when theta equals pi over 3? Well, it's dr dt, which we'll put in the numerator. We were told that dr dt is 3. The distance between the origin and the particle is increasing at 3 units per second. So that's 3. And in the denominator, we have negative 2 times sine theta when theta is pi over 3. Sine of pi over 3, hopefully you know your unit circle, that's root 3 over 2. So if we multiply that by negative 2, we're just going to have negative root 3. This simplifies to negative root 3 because this is 3 to the 1, this is 3 to the 1/2. Just subtract the exponents, you get 3 to the 1/2 in the numerator, which is root 3. So it's negative root 3, and the units, because we're talking about how the angle theta changes with respect to time, this is negative root 3 radians per second. And that is our answer to part C. And that completes our solution to free response question 5 from the 2018 AP Calc BC exam. Next up are parametric and vector equations. Recall that when you're asked to find the speed of a particle whose path is described by parametric equations, you will have to take the derivative of the x and y functions in order to find the velocity functions, and then you'll have to take the square root of the sum of the squares of those derivatives. This is free response question 1 from the 2002 AP Calc BC Form B exam. It is part of the graphing calculator section. We'll use a calculator just a little bit for this problem. Let's read through it. A particle moves in the xy plane so that its position at any time t for t between negative pi and positive pi is given by these parametric equations. Part A asks us to sketch the path of the particle in the xy plane provided, and to indicate the direction of motion along the path. So for part A, here is a recreation of the provided xy plane. Let's get some basic information about these parametric equations before we start sketching. We know that x is a function of t. It equals sine of 3t. And we know that y of t equals 2t. We might as well begin by eliminating the parameter. If y equals 2t, then t equals 1/2 y. And so we can express x as a function of y rather than having this parameter. We don't actually need the parameter. So we could say that x as a function of y is equal to sine of 3t, but t is half y, so 3/2 y. Now, if we express x as a function of y, we should ask how small and how big can y get? Well, t could go from negative pi to positive pi, and y equals 2t. So y can go from negative 2 pi to positive 2 pi. So we will write that here. Y goes from negative 2 pi, that's twice the lower bound of t, to positive 2 pi, which is twice the upper bound of t. All right, so x is sine of 3/2 y, where y goes from negative 2 pi to 2 pi. This means we're going to have a sine function, but instead of going along the x-axis, the sine function is going to go along the y-axis. Also, because it's sine of 3/2 y, the frequency is sped up by 3/2. So y going from negative 2 pi to 2 pi, that's a total of 4 pi, which would normally be enough space for 2 full periods of sine. But in our case, the frequency of the sine function has been sped up by a factor of 1.5. So this space from negative 2 pi to positive 2 pi will actually be enough for 3 full periods of sine. So before even sketching this, I know that we should have 3 full periods of sine in our graph, and it should be a sine function going along the y-axis. So all that remains is to plot some points. When y equals 0, x is sine of 0, which is just 0, so this curve should pass through the origin. Now this is 2 pi up here, which means this is 1 pi right here, so maybe we should label that. That's pi, which means this is 1/3 pi, this is 2/3 pi, and so on. So right here, where y is 1/3 of pi, if we plug that in, we would get pi over 2. And sine of pi over 2 we know is 1. So let's plot that point. Then right here is 2/3 pi. If we plug y equals 2/3 pi, we'll actually get sine of pi. And sine of pi we know is 0. So here it goes to 0. And then if we plug in y equals pi, we will have sine of 3/2 pi. Sine of 3/2 pi is -1. So here at y equals pi, the x value will be -1. And this pattern will continue in both directions. So here at pi and 1/3 pi, it'll go back to 0, and then it'll go back to +1, and then at 2 pi, it comes back to 0. And this curve goes similarly in the direction of the -y. If we go to -1/3 pi, the x-coordinate is going to be -1. And then when we get to -2/3 pi, it comes back to 0. And then if we get to negative pi, it is +1. And then if we get to negative pi and 1/3, we come back to 0. And then at negative pi and 2/3 pi, we are back to -1, and then back to 0 at the end. Then we can just do our best to connect these points, sketching our sine curve. All that remains is to draw a couple arrows indicating the direction. Now, let's think, how does y change as t changes? Well, y is just 2t. So as t increases, as time passes, y also increases, which means the direction is moving upwards along the y-axis. So here are just a couple of arrows to indicate that direction. And that completes part A. Part B says find the range of x of t and the range of y of t. We're actually already halfway done that. We already know that y goes from negative 2 pi to positive 2 pi. So we can just copy and paste that interval that we already discussed. As for x is even easier because x is just a sine function, which means it's going to be between negative 1 and positive 1. And as we already saw, it does indeed achieve all of those values. So it's not just a piece of the sine function, it completes, as we know, 3 full periods of the sine function. 1, 2, 3. So the range of x is from negative 1 to positive 1. X is between positive 1 and negative 1. Now part C says find the smallest positive value of t for which the x-coordinate of the particle is a local maximum, and then find the speed of the particle at this time. Now, if we're trying to find maximum values of the x-coordinate, we're going to want to take the derivative of the x function. So let's look at x prime of t. Well, x of t is sine of 3t, so the derivative of that is going to be cosine of 3t, but then we need to multiply by the derivative of the inside function, so throw a factor of 3 in front there. Now, this we need to set equal to 0 to find the critical points. The derivative, of course, exists everywhere, so the critical points will just be where the derivative equals 0. Now, we could divide both sides of this equation by 3. That's just going to get rid of the 3, and we have cosine of 3t equals 0. Where does cosine equal 0? Well, at infinitely many places, but we're looking for the one that produces the smallest t value. The first time that cosine is 0 is at an input value of pi over 2. So we would need 3t, the argument of the cosine function, to equal pi over 2. That's the first time that cosine is 0. This means that t equals pi over 6. That's the t value we are looking for. That, of course, is when cosine is 0 and sine is 1. That would be our first maximum x value, which is right here on the graph. That is at t equals pi over 6. All right, the other part of this question, part C, was to find the speed of the particle at this time. To find the speed of the particle, we need to look at the magnitude of the velocity vector. So in general, the speed of the particle is going to be the square root of the sum of the squares of the derivatives of the position functions. So x prime squared plus y prime squared, all in a square root. Now, we already found what x prime was, so let's start to expand this expression. We have the square root of x prime, we know, is 3 cosine of 3t. If we square that, we get 9 cosine squared of 3t. And then we have to add the square of the derivative of the y position function. Y, you may recall, is 2t, and its derivative is just 2. So if we square that, we get 4. So that is the speed function in general. We need to evaluate it at t equals pi over 6. So let's plug in pi over 6 and see what this equals. Plugging in t equals pi over 6, we have the square root of 9 cosine squared of 3 times pi over 6 is pi over 2. So we will put pi over 2 there, and then plus 4. Now, cosine of pi over 2 is 0. So cosine squared of pi over 2 is 0. This whole term just goes away. So it's actually just the square root of 4, which is 2. So that is the speed at t equals pi over 6. Finally, moving on to part D. Is the distance traveled by the particle from negative pi to pi greater than 5 pi? And we need to justify our answer. To find distance traveled, we need to accumulate the speed function. So we need to take this function that we found for the speed, that's the magnitude of the velocity, and we need to integrate it. Accumulating that speed over time is going to give us the distance traveled. And for the integral, we will use a calculator, but let's go ahead and write out the integral first. So here for part D, we are integrating. It said from negative pi to positive pi, and what we're integrating is the speed function, which we know is that square root there. So it's the square root of 9 cosine squared of 3t plus 4 And let's make sure that square root is long enough. And this integral is taken with respect to t. And we'll just find this on a calculator. So on the calculator, I'll press the math button, and then option 9, the integration function. We are integrating from negative pi to positive pi. What we are integrating is the square root of 9 times cosine of 3t, but it's more convenient to use x on the calculator, so I'm going to use x. And that's squared and then plus 4. And we're integrating with respect to x on the calculator. We get about 17.973. And remember, the question also asked, is this distance traveled, which we just found is about 17.973, is this distance traveled greater than 5 pi? The answer is yes, it is, because pi, which is about 3.14, is obviously less than 3.15. And so 5 pi then would have to be less than 15.75. So yeah, 17.973, that's greater than 15.75, which is certainly greater than 5 pi. And that completes our solution to free response question 1 from the 2002 AP Calc BC Form B exam. This is free response question 2 from the 2012 AP Calc BC exam. Let's read it. For t greater than or equal to 0, a particle is moving along a curve so that its position at time t is x of t, y of t. At time t equals 2, the particle is at position 1, 5. It is known that dx dt equals this and dy dt equals this, and we have a 4-part question here, and this is part of the graphing calculator section. We'll use the calculator quite a bit in this problem to compute some derivatives and whatnot. Note that the given information tells us the rate of change in the horizontal direction and the rate of change of the particle in the vertical direction. With that in mind, let's move on to part A. Is the horizontal movement of the particle to the left or to the right at time t equals 2? And we need to explain our answer and then find the slope of the path of the particle at time t equals 2. Beginning with the horizontal movement of the particle, which is described by the x of t function, is that horizontal movement to the left or to the right at time t equals 2? To answer that question, we need to ask, how does the horizontal position x of t change at time t equals 2? Well, that's described by the derivative dx dt. So in fact, all we have to do is plug t equals 2 into the derivative. If the derivative is positive, that means that the position is changing to the right, the positive direction, and so the movement is to the right. If it's negative, then the movement is to the left. It's in the negative direction. So we will look at dx dt evaluated at t equals 2, and this is straightforward because dx dt is given. Dx dt has a numerator of square root of t plus 2. T is 2, so this becomes the square root of 4, which is just 2. And the denominator is e to the 2. Both the numerator and denominator are positive, so this is positive, and thus the particle is moving to the right at time t equals 2. And there that logic is written out. At time t equals 2, the particle is moving to the right because the rate of change of its horizontal position is positive. Now, the other part of the question asks us to find the slope of the path of the particle at time t equals 2. To find that, we just have to look at dy dt divided by dx dt with t equals 2 plugged in. This will tell us how the vertical position is changing with respect to the changes in the horizontal position, and that's going to give us the slope. And we just have to plug these pieces in. In the numerator, we have dy dt, but with t equals 2 plugged in. So that's going to be sine squared of 2. We are dividing by dx dt, so the denominator of dx dt will actually move to the numerator with t equals 2 plugged in. The numerator of dx dt will be in the denominator because we're dividing by it. That's going to be the square root of 4, which is just 2. Then we'll go ahead and plug this into a calculator. So in the calculator, we'll type sine of 2 squared multiplied by e to the power of 2. And then this is getting divided by 2. This gives us a slope of about 3.054. So the line tangent to the path that the particle is traveling at time t equals 2, that tangent line to the path, has this slope. Let's move on then to part B. Find the x-coordinate of the particle's position at time t equals 4. We'll write this in blue. In order to find the x-coordinate of the particle's position at time t equals 4, we need to take the x-coordinate that we are given, which is at time t equals 2, so I'll write x of 2, and then we need to accumulate the rates of change from t equals 2 to the desired ending time of t equals 4. So we're going to accumulate dx dt. Those are the rates of change. So x of 2 is given to us as 1. That's the horizontal position of the particle at time t equals 2. And then we are integrating from t equals 2 to t equals 4 dx dt, which was also given to us as the square root of t plus 2 divided by e to the t. That was given to us. And we are integrating this with respect to t. Again, this is taking the position at the time we know t equals 2 and then accumulating the change in horizontal position from 2 to 4. Now we can find this using our trusty graphing calculator. So in the calculator, I'll press 1 plus the math button, and then function 9, that's the integration function. We are integrating from 2 to 4. And what we are integrating is the square root of t plus 2, but in the calculator we'll use x because that's more convenient, divided by e to the power of t, but we're using x, integrating with respect to x here on the calculator, and we get a position of about 1.252, or rounding up, this is about 1.253. Now let's move on to part C. Find the speed of the particle at time t equals 4, and find the acceleration vector of the particle at time t equals 4. All right, to find the speed of the particle, we're going to need to take the magnitude of the velocity vector of the particle. The velocity vector is just the vector consisting of the rate of change of the horizontal position, dx dt, and the rate of change of the vertical position, dy dt. This is basically just the derivative of the position function. So then the speed at time t equals 4 is just going to be the magnitude of this velocity vector with t equals 4 plugged into it. So let me write this big square root so that we have room to fit it all in here. And the velocity vector, we know what its components are because dx dt and dy dt were given to us. So we'll just plug t equals 4 into those, and you have to square the components, right? It's just part of the magnitude formula. So let's write this out. So there is the magnitude of the velocity vector at time t equals 4. I just plugged t equals 4 into dx dt, and plugged t equals 4 into dy dt. Both of them are squared. They're getting added together in a square root. We, of course, will calculate this using our calculator. Got to be careful typing in these big, ugly expressions into calculators, so let us be careful. We've got the square root of 6 divided by e to the power of 4, and this whole thing is getting squared. And then we are adding sine squared of 4 squared. So we have sine of 4 squared, close parentheses, square. All this is in the square root. That looks good. It's about 0.5745. Now, we also are asked in part C to find the acceleration vector of the particle at time t equals 4. So to find the acceleration vector at time t equals 4, we're going to need to take the derivative of the velocity vector and plug in 4, so v prime of 4. That's going to be the acceleration vector. All right, for this, we're definitely going to want to use the calculator. No point dealing with more manual derivatives and stuff than we have to. So for the horizontal component of the acceleration vector at t equals 4, we will take the derivative of dx dt with the evaluation at t equals 4. So let's open up the calculator. So on the calculator, I'll press math and then option 8, that's the derivative function. We are differentiating with respect to t, but it's more convenient to use x on the calculator. Now for starters, we're going to take the derivative of dx dt, which is right there. So we have the square root of x plus 2 divided by e to the power of x, and we're evaluating this derivative at x equals 4. This tells us that the horizontal component of the acceleration vector at t equals 4 is about negative 0.0411. Now we will do a similar thing for the vertical component of the acceleration vector. Press math, option 8 for the derivative function. We're differentiating with respect to x, and then dy dt is sine squared of t, or on the calculator, we'll just put sine of x squared. And then we are evaluating this derivative also at x equals 4, and we get about 0.9894. So that's the acceleration vector at time t equals 4. Just take the derivative of the velocity vector with 4 plugged in. And that was the speed at time t equals 4. That completes part C. Finally, part D asks us to find the distance traveled by the particle from time t equals 2 to t equals 4. So for part D, distance traveled is found by accumulating speed. We need to integrate the speed function from time t equals 2 to time t equals 4. Adding up all those speeds will tell us how far the particle traveled. So we are going to integrate from time t equals 2 to t equals 4, this same thing that we were using for speed in part C, but without t equals 4 plugged in, because for the integral, of course, we want t to be allowed to vary. So we're going to have the square root of dx dt squared plus dy dt squared. So I'll write those things out. And there it is. This is the integral of the speed function, the magnitude of the velocity vector, from t equals 2 to t equals 4. We're integrating, of course, with respect to t. Let's open up the calculator to figure out this integral. So I'll press math, option 9, the integration function. We are integrating from 2 to 4. And now we have to very carefully type in the function we're integrating. We have the square root of, and then what we have is the square root of x plus 2 divided by e to the power of x. And this whole thing is getting squared. That's dx dt squared. And then we need to add dy dt squared. So I'll open up parentheses, put in sine of x. Sine of x is getting squared. And then that whole thing is getting squared. That's dy dt squared. We are integrating, of course, with respect to x, and there we go. It's about 0.651. So from t equals 2 to t equals 4, the particle traveled about 0.651 units. This is not, remember, displacement. Displacement would be found by integrating the velocity. We integrated the speed, so we just get the total distance traveled. And that completes our solution to free response question 2 from the 2012 AP Calc BC exam. This is free response question 2 from the 2016 AP Calc BC exam. Let's read it. At time t, the position of a particle moving in the xy plane is given by the parametric functions x of t, y of t, where dx dt equals t squared plus sine of 3t squared. The graph of y, consisting of 3 line segments, is shown in the figure above. At time t equals 0, the particle is at position 5, 1. So if you look at the graph, at time t equals 0, you can see the y-coordinate, which is what this is telling us. The y-coordinate is at 1. This is part of the graphing calculator section. We will use the calculator throughout this problem. Part A asks us to find the position of the particle at time t equals 3. In order to find the position of the particle at time t equals 3, well, we know that this is given by x of 3, y of 3. For the x component, we are going to have to use our calculator and the given dx dt function. For the y component, we're going to have to use the graph, which is given to us. Using this graph, we can find dy dt. Dy dt is just the slopes of these 3 line segments. But let's start off with x of 3. To find x of 3, the horizontal position of the particle at time t equals 3, we need to take the initial position at time t equals 0. So I'll just write x of 0, which we know is 5, but I'll just write it as x of 0 for now. And then we need to integrate all of the horizontal rates of change. So integrate from 0 to 5 dx dt. But dx dt is given to us, so let's just write what it is. Dx dt is t squared plus sine of 3t squared. We are integrating, of course, with respect to t. Now we'll just use a calculator to figure this out. I'll replace x of 0 now with the given initial horizontal position of 5. So this is approximately. So for part A, we are looking for the horizontal position at time 3, x of 3, and the vertical position at time 3, y of 3. Let's first begin with the horizontal position. The horizontal position at time t equals 3 is going to be the horizontal position at time t equals 0 plus the accumulation of the horizontal rates of change. So we need to integrate from t equals 0 to t equals 3 the horizontal rates of change, dx dt. But dx dt is given to us, so let's just write it in this integral. Dx dt is given as t squared plus sine of 3t squared. So this is our integral. It is with respect to t. And x of 0 over here is also given to us. So let's just replace that. X of 0, we're told, is 5. So this is 5 plus this integral. And we will go ahead and evaluate this using our calculator. So here on the calculator, I'll press 5 plus the math button. Option 9 for the integration function. We are integrating from 0 to 3. And what we're integrating is t squared, but we're going to use x in the calculator just because that's more convenient, plus sine of 3 times t squared. And we are integrating on the calculator with respect to x. And we get about 14.377. So the horizontal position at time t equals 3, we know is 14.377. In order to find the vertical position, y of 3, we are going to have to use the provided graph. We're looking for the y-coordinate right here, where t equals 3. So let's study this line. What is the equation of this line? Well, it goes from the point 2, -1, up to the point 4, 0. So when the x-coordinate increased by 2 from 2 to 4, the y-coordinate increased by 1 from -1 to 0, which means the slope is positive half, which means that at t equals 3, it must have gone up 1/2 from -1. -1 plus a half is -half. So y of 3 would be -1/2. If you wanted to do this really carefully, you could just write the equation for this line segment and plug in t equals 3. But writing that y component of -1/2, that completes part A. That's the position of the particle at time t equals 3. Part B asks us to find the slope of the line tangent to the path of the particle at t equals 3. That's really easy. That's just dy dt divided by dx dt. So what we are looking for is dy dt, how the y is changing, divided by dx dt, how the x is changing. And specifically, we are evaluating this at t equals 3. So this fraction is going to tell us the vertical change with respect to the horizontal change. This is equal to, well, for dy dt at t equals 3, we already said that the slope of this line, which is what's applicable at t equals 3, the slope of this line is positive 1/2. We see from here to here, it goes forward 2 and up 1. So its slope is 1/2. So dy dt here is just 1/2. As for the denominator, dx dt, when t equals 3, we know that dx dt is this. So we'll just plug 3 into that using our calculator. So here on the calculator, we'll just type in dx dt, but with t equals 3 plugged in. So 3 squared is what we start off with, and then plus sine of 3t squared. Now, if t is 3, then t squared is 9, so 3t squared is just 27, so sine of 27. This turns out to be 9.9564, just about, so I'll write that there. 9.9564, and we'll just wrap this up by doing the division on the calculator. The numerator of 0.5 divided by dx dt that we just evaluated, it's about 0.0502. So the path that the particle is traveling along has a tangent at t equals 3 with this slope. That's the slope to the path at t equals 3. Moving on to part C. Find the speed of the particle at t equals 3. Speed is going to use a lot of the same information we've been using because speed is just the magnitude of the velocity function. So we need to take the square root of the horizontal component of the velocity function at t equals 3 squared. The horizontal component of the velocity function is dx dt, and we will need to plug 3 into that. We already did plug 3 into that for this problem, so let's just write that, 9.9564 squared. And then we need to add the vertical component of the velocity function, which we already know is just 1/2, and we need to square that, so plus 1/2 squared. This is the magnitude, again, of the velocity function, which is the speed. Now we'll just evaluate this on the calculator. So we have the square root of 9.9564 squared plus 1/2 squared. This is about 9.969. So that is the speed of the particle at time t equals 3. Moving on then to the final part, part D. Part D says, find the total distance traveled by the particle from t equals 0 to t equals 2. So looking on our graph, t equals 0 to t equals 2 is from here to here. Now, to find distance traveled, we need to accumulate speed. Speed depends on dx dt and dy dt. dx dt doesn't change exactly. It's the same function, right? dx dt is just this. dy dt, however, does have an abrupt change here at t equals 1. So as we integrate the speed to find the distance traveled, we're actually going to have to split it up into two integrals to account for this sudden change in the dy dt. dy dt is the slope of these line segments, and it's right there where we see that sudden change. Over here, from 0 to 1, we have that dy dt is what? What's the slope of the line? Well, when it goes from 0 to 1, it decreases by 2. So that would be a slope of -2. Meanwhile, over here from 1 to 2, the slope is clearly 0. It's a horizontal line segment. So over there, dy dt is 0. So we are going to have to integrate from 0 to 1, because that's where that dy dt change happens. From 0 to 1, the speed of the particle, which is the square root of dx dt squared. Now, dx dt is given to us as this function, so let's write that out. And then we need to add the square of dy dt. Now, from 0 to 1, like we saw, dy dt is -2. That's the slope of this line segment. So that's dy dt squared, and we're integrating with respect to t. And then, separately, we have the integral from 1 to 2 of this same thing, but at this point, the dy dt has changed to 0. So I'm just going to duplicate this, and then we can change dy dt to 0. So in fact, we don't even have to write it. The integral, though, is still with respect to t, and now we'll just have to consult the calculator to evaluate this big nasty sum. Carefully typing this into the calculator with the integration function, we get about 4.349. That is the distance traveled by the particle from t equals 0 to t equals 2. Again, we had to split it up because at t equals 1, there's a sudden change in dy dt. And that completes our solution to free response question 2 from the 2016 AP Calc BC exam. Make sure you read these questions carefully. It's a lot harder if you don't understand immediately that this graph is just a graph of y of t, and x of t is not actually given to us. We are only given dx dt explicitly as a function, but we don't have any graph relating to x. Next up are problems on Euler's method. For these problems, recall that the little steps that you take in x will be given to you in the problem, and then the steps that you have to take in y are the changes in x multiplied by the derivative's value at the previous x coordinate. Good luck. This is free response question 4 from the 1998 AP Calc BC exam. This is part of the graphing calculator section. Consider the differential equation given by dy dx equals xy over 2. Part A says, on the axes provided below, sketch a slope field for the given differential equation at the 9 points indicated. So we need to look at each of these 9 points and, based on their coordinates, assess what the derivative, dy dx, should be, and sketch a tangent segment that has that slope. So let's first go through all of these points and label each one with the appropriate dy dx value. Once we can see what all of their slopes should be, we can draw them so that the slopes look accurate, right? If this point has a slope of 2, but this point here has a slope of 1, then this segment should be steeper than this one. So we want to go through and find all the slopes before we start sketching. Let's go from top to bottom. So let's start up here. The coordinates of this point are -1, 3. So what should the slope be? Well, the numerator of the derivative, xy, is -1 times 3, so -3, divided by 2, so -1.5. Again, we'll just label with the slopes, and then we'll go through and sketch the segments. Now, this point here has coordinates 0, 3, so the dy dx value would just be 0. This point over here has coordinates 1, 3, so the dy dx value would be 1.5 because it would just be 3 over 2. Then this point here has coordinates -1, 2, so the dy dx value would be -2 over 2, so just -1. This point has an x-coordinate of 0, so the slope would again be 0. This point over here has coordinates 1, 2, so it would have a slope of +1. This point over here has coordinates -1, 1, so its slope would be -0.5. This point has a slope of 0, and this point has a slope of +0.5. To sketch the slope field, then, we just need to draw segments that have roughly these slopes, and we want to make sure that they look correct relative to each other. So this guy over here with a slope of -1.5 should be more steep than this guy with a slope of -1. All right, let's go through. We could do the horizontal lines first, because that's really easy. Slopes of 0 at those points, so just drawing horizontal lines there. And then this point should have a slope of -1.5, so something like that. And then this point over here should have the same slope over here, but going up, so something like that. And then this should be a slope of -1, so like -1.5, but a little less steep, so maybe like that. And then over here, same thing, but going in the positive direction. Something like that. And then this should be a downward slope at -0.5, but it should be quite shallow. So maybe something like this. And then on the other side, over here, we have the same sort of thing, but going up. And now that I've sketched the slope field, I'm just going to go ahead and erase the slopes that we jotted down because we don't need them anymore. And that is our answer for part A. There is our sketched slope field. Moving on to part B. Let y equal f of x be the particular solution to the given differential equation with the initial condition f of 0 equals 3. Use Euler's method starting at x equals 0 with a step size of 0.1 to approximate f of 0.2 and show the work that leads to our answer. For part B, recall that the given differential equation is dy dx equals xy over 2. Now, to use Euler's method to approximate f of 0.2, we need to start by approximating f of 0.1. That's because the initial condition is at x equals 0, and we were told to use step sizes of 0.1. So first, we step forward 0.1. Now, what is f of 0.1? Well, it is approximately the value at f of 0, which is 3, plus the change in x, which is 0.1, our step size, multiplied by the derivative, the slope, at x equals 0. This is our approximation for f of 0.1, so that's 3 plus, what is f prime of 0? Well, if you plug 0, x equals 0, I should say, into dy dx, clearly the slope is 0. So this should just be 3 plus 0. And so 3 is our approximation of f of 0.1. Now we have to step forward another 0.1 to get our approximation of f of 0.2. What's f of 0.2? Well, it should be about f of 0.1, which is 3, plus the change in x, which is 0.1, multiplied by the slope, or the derivative, evaluated at 0.1. Making these incremental steps using tangent line approximations is Euler's method. All right, now what is f prime of 0.1? Well, we don't know exactly what f prime of 0.1 is because f prime of 0.1 depends on y, and we don't know the true value of y when x equals 0.1. The best we can do is use our approximation that when x equals 0.1, y is about 3. So the value of the derivative, which I'll put in parentheses here, the value of the derivative should be about 1/2, that denominator of 2, multiplied by x, which is 0.1, multiplied by y, which at 0.1 we approximate as about 3. Now 0.1 times 3 is 0.3, times 1/2 is 0.15, times 0.1 is 0.015. So this is 3.015. And that is our answer for part B, using Euler's method, starting at x equals 0, since that's where the initial condition was, and step sizes of 0.1. This is our approximation for f of 0.2. Now, part C says, find the particular solution, y equals f of x, to the given differential equation with the same initial condition as before, and then use our solution to find f of 0.2, which is what we approximated in part B. So here for part C, we are going to need to use separation of variables. We know that dy dx equals xy over 2. Now we will move the dx to the right, so all the x's are together, and move the y to the left, so all of the y's are together. So we're going to multiply both sides by dx and divide both sides by y. Then on the left, we have 1 over y because of the division by y, 1 over y dy, equals, we multiply both sides by dx, so on the right, we have x over 2 dx. And now we can go ahead and integrate both sides of this equation. The integral of 1 over y dy is the natural log of the absolute value of y. In theory, we also have the addition of an arbitrary constant, but let's imagine that we just gather all the arbitrary constants on the right side. So on the right side, we have the integral of x over 2, which is just going to be 1/4 x squared. And then we have all of the arbitrary constants just wrapped up in this 1 plus c. Now we need to solve for y, and we also need to use the initial condition to solve for c. Let's first exponentiate both sides of this equation to get rid of that natural log. Exponentiating on the left will, of course, cancel out with the natural log, and so we have the absolute value of y. And then on the right, we would have e to the power of 1/4 x squared plus c, which by our exponent laws is the same as e to the 1/4 x squared times e to the c. But e to an arbitrary constant is just some other arbitrary constant. So we could just say c times e to the 1/4 x squared. This is being slightly sloppy with notation because e to the c is different from c, so using the letter c over and over again is a little bit careless, but this is typically how we would do it. If you want to be a little bit more formal, you could call the original constant c1, and then we can call this new constant, which is e to the c1, we can just call it c. Now, we actually don't need the absolute value on y because we were told that we're finding the particular solution that passes through this initial condition, f of 0 equals 3. So for this particular solution to the differential equation, the y values are actually positive, and so we can drop the absolute value, and thus we have that y equals c times e to the 1/4 x squared. Now we can plug in the initial condition, which is 0, 3, in order to solve for c. Plugging in the initial condition of 0, 3, which I'll just do in a different color, produces the equation 3 equals c times 1. So c equals 3. There we go. Thus, our particular solution is y equals 3 times e to the 1/4 x squared. So that's our particular solution, but don't forget the other part of the problem. We're supposed to use this solution to find the value of f of 0.2. Now that we have this particular solution for our function f, we can just plug 0.2 into it. So let's write this. F of 0.2 equals, using this particular solution, it equals 3 times e to the 1/4 multiplied by 0.2 squared. Now let's just go ahead and simplify. This is 3e to the power of 1/4 multiplied by 0.2 squared is 0.04. And then 1/4 of 0.04 is 0.01. So this is 3e to the 0.01. Plugging this into a calculator, this is about 3.03. You can see that our approximation was a bit off, but not by too much. And that completes our solution to free response question 4 from the 1998 AP Calc BC exam. This is free response question 6 from the 1999 AP Calc BC exam. We will use a calculator throughout this problem. Let f be the function whose graph goes through the point 3, 6 and whose derivative is given by this equation. Part A asks us to write an equation of the line that's tangent to the graph of f at x equals 3, and to use this tangent line to approximate f of 3.1, a value of the function near the point of tangency. All right, so let's start off here with part A. In order to write an equation of the tangent line, we will use point-slope form. So we need y minus a y-coordinate. Now, at x equals 3, we know the y-coordinate of our function is 6 based on the given initial condition. So this should be y minus 6 equals, and then we need the slope. To find the slope, we just plug x equals 3 into f prime, and f prime is given. So plugging x equals 3 into the given value of the derivative, we have 1 plus e to the 3 divided by 3 squared, which is 9. That's the slope, and this needs to be multiplied by x minus the x-coordinate. The x-coordinate in question is 3. Finally, we could add 6 to both sides just to get this in a more standard form. So writing this with y by itself, we have that y equals 6 plus all the stuff from the prior equation. And there we go. That is our equation of the tangent line at x equals 3. And now we need to use it to approximate f of 3.1. In order to do that, all we have to do is plug x equals 3.1 into the tangent line. Since 3.1 is pretty close to 3, the point of tangency, this should give us a decent estimate of the function's value. So f of 3.1 should be about 6 plus 1 plus e to the 3 over 9 multiplied by x minus 3, but where x equals 3.1. 3.1 minus 3 is just 0.1, so this is just getting multiplied by 0.1. If you plug this into a calculator, you'll find it's about 6.234. Moving on to part B. Using Euler's method, starting at x equals 3, with a step size of 0.05, we must approximate f of 3.1, and then use f double prime to explain why the approximation is less than the true value of f of 3.1. All right, so for Euler's method, if we're going to approximate f of 3.1 using step sizes of 0.05 and starting at x equals 3, we first need to take our first step away from x equals 3. Thus, we begin with an approximation of f of 3.05. That's taking one step of size 0.05 away from x equals 3. What is the value of f of 3.05? Well, it should be about the value of f at 3, which we know is 6 because the function passes through the point 3, 6, plus the change in x, or the step size, 0.05, multiplied by the derivative's value at 3, so multiplied by f prime of 3. Because remember, the derivative is giving us a change in y per change in x using the tangent line. So if this is the change in x, 0.05, we have to multiply it by the derivative, which tells us how much y should change. All right, so let's just plug this into the calculator. We have 6 plus 0.05 multiplied by the derivative evaluated at 3. That's right here, right? 1 plus e to the 3 over 9. So 1 plus e to the power of 3 divided by 9. This is about 6.117. Then we can take the next step, going forward another 0.05 to approximate f of 3.1. It should be about f of 3.05, which is about 6.117, plus the change in x, which is 0.05, the step size, multiplied by the value of the derivative at 3.05. To get this approximation, we can again use the calculator. So we're going to have 6.117 plus 0.05 multiplied by the derivative, but this time with 3.05 plugged in. The derivative, of course, is 1 plus e to the x, so 1 plus e to the power of 3.05, and then this needs to get divided by 3.05 squared. This gives us an approximation of about 6.236. Now, let's not forget the other part of the problem. Part B also wants us to use the second derivative of our function. We have the first derivative. We're supposed to use the second to explain why the approximation we just got is less than the true value of f of 3.1. You may recall that if a function is concave up, then its tangent lines lie below the graph. Now, concave up means the second derivative is positive. So what we're going to do is take the derivative of the derivative in order to find the second derivative. And if we can show that it's positive in the space that we're concerned with, which is around 3 and 3.1, the second derivative is positive there, the function must be concave up, which means the tangent lines, which we're using to construct this approximation, that's how Euler's method works, those tangent lines, and thus our approximation, must be underestimates. So let's just write the first derivative, which is given to us. The first derivative is 1 plus e to the x divided by x squared. So to take the derivative of this and find the second derivative, we are going to need to use the quotient rule. So we'll begin with the derivative of the numerator, which is e to the x, multiplied by the denominator, x squared, minus the derivative of the denominator, so 2x, multiplied by the numerator, 1 plus e to the x. And then all of this needs to get divided by the denominator squared, so x to the 4. Now, everything has a factor of x, so we can cancel out a factor of x from everything. So simplifying this a little bit, we have x to the power of 1 multiplied by e to the x minus 2 times 1 plus e to the x divided now by x to the 3. Now we have x e to the x and minus 2 e to the x, so we can factor out an e to the x from both of those terms, which leaves behind x minus 2. And then we also have minus 2 times positive 1, so let's not forget that. And still x cubed is in the denominator. So this is our second derivative, and the space we are interested in is really between 3 and 3.1, because that's the space within which we were constructing approximations. So what is the shape of the graph in this space? Is it concave up or concave down? Well, if x is at least 3, this second derivative is clearly positive, because if x is at least 3, then x minus 2 is at least 1, and e to the x is a lot bigger than 2, so the numerator would definitely be positive, and it would also be getting divided by a positive number. So for x at least 3, it's clear that e to the x times x minus 2 is greater than 2, and thus this second derivative will be positive in the space that we are interested in. So yes, in fact, our approximation of 6.236 is an underestimate of the true value. If x is at least 3, the second derivative is clearly positive, so f is concave up on the interval of interest, and thus the tangent lines, and consequently the Euler approximation that we found, is an underestimate. Again, this is because if a function's concave up, those tangent lines are underestimates. All right, let's move on then to part C. Part C asks us to use the integral of f prime of x from 3 to 3.1 to evaluate the value of the function at 3.1. So for part C, we want to use this integral of f prime of x from 3 to 3.1 to calculate f of 3.1. By the fundamental theorem of calculus, we know that the integral of f prime from 3 to 3.1 is f of 3.1 minus f of 3. And we know that f of 3 is actually equal to 6, right? That was given as an initial condition in the problem. So this on the right is f of 3.1 minus 6, and on the left, for our integral, we'll use a calculator to get an approximation. Here on the calculator, I'll press the math button, and then option 9, that is the integration function. We are integrating from 3 to 3.1. The function we're integrating is f prime, which is this guy here, 1 plus e to the x over x squared. So we'll write that, careful with our parentheses, 1 plus e to the x divided by x squared. And we are integrating with respect to x. This turns out to be about 0.2378, we'll say. So 0.2378. And then finally, to solve for f of 3.1, we just add 6 to this. And so f of 3.1 should be about, and this will be a very good approximation because it's using a calculator, it'll be about 6.2378. So maybe we don't know what f of x is, but just using its derivative and an initial condition, we can figure out a whole lot. There's a lot of different ways you can approximate a function's value with this information. That completes our solution to free response question 6 from the AP Calc BC exam from 1999. Next are problems on improper integrals. Recall that the definition of the integral of a function f of x from a to infinity is the limit of the integral of the function from a to b as b goes to infinity. This is free response question 5 from the 2004 AP Calc BC Form B exam. Let g be the function given by g of x equals 1 over the square root of x. Part A asks us to find the average value of g on the closed interval from 1 to 4. So all we will have to do is integrate g of x from 1 to 4 and then divide by the length of that interval. That's how we calculate average value. Now the length of the interval is just 4 minus 1, which is 3. So we have 1/3, we're dividing by 3, the length of the interval. And we're integrating from 1 to 4, and what we're integrating is g of x, which is 1 over the square root of x. You may choose to rewrite this integral so that 1 over the square root of x appears as a power, x to the negative 1/2. Then it's very clear how we will integrate this using the power rule. This will be 1/3 multiplied by add 1 to the power, so instead of x to the negative 1/2, it will become x to the positive 1/2, and then divide by the new power. Dividing by 1/2 is the same as multiplying by 2, and so we get here 1/3 times 2x to the 1/2, evaluated from 1 to 4. Let's start evaluating. When we plug in 4, we get 4 to the 1/2, which is 2, multiplied by 2. So again, 4 to the 1/2 is 2 multiplied by 2. Then subtract, plugging in the lower bound, that's just going to be minus 2. So finally, this is 4 minus 2, which is 2, multiplied by 1/3. So the average value of the function over the interval in question is 2 over 3. Part B says, let S be the solid generated when the region bounded by the graph of y equals g of x, the vertical lines x equals 1 and x equals 4, and the x-axis is revolved about the x-axis. We want to find the volume of this generated solid. You may find a quick picture helpful in this situation. I'm not going to really include the negative x-axis in this picture because it's not super important. Now, the graph of 1 over root x looks very similar to the graph of 1 over x. It's going to look something like this. And the region that is getting revolved is the region under this curve from x equals 1 to x equals 4. So if this was x equals 1 and this over here was x equals 4, it's this region that is getting revolved about the x-axis. So the generated solid, maybe I can use purple here, the generated solid is going to look something like this. And a cross-section, of course, would just be a circle that looks like that, and the radius of the circle would be the value of the function, 1 over root x, at the horizontal position in question. So all we have to do to find the volume of this solid is add up all of the areas of these circular cross-sections. So we will integrate from 1 to 4 the area of the circular cross-sections, which is pi multiplied by the radius squared. The radius is just the value of the function at the point in question, so 1 over root x squared, and we are integrating with respect to x. We can, of course, take a pi out of this integral, so this is pi multiplied by the integral from 1 to 4, and then 1 over root x squared is just 1 over x. And this is very easy to integrate. This is pi multiplied by the natural log of x evaluated from 1 to 4. Finally, this is pi multiplied by the natural log of 4 minus the natural log of 1, but of course the natural log of 1 is 0. So this is just pi multiplied by the natural log of 4. That is the volume of the solid. Moving on then to part C. Part C says, for the solid S given in part B, find the average value of the areas of the cross-sections perpendicular to the x-axis. That's really easy because the cross-sections perpendicular to the x-axis are precisely the cross-sections that we added up in part B. So to find the average area of these cross-sections, we need to add all of the areas up, which we already did. It's pi ln 4, and then divide by the length of the interval. The length of the interval is just 4 minus 1. So all we have to do for part C is take our answer from part B, which was pi ln 4, because this is the sum of all of the areas of the cross-sections, and then divide by the length of the interval, which is 4 minus 1. So our final answer for part C is pi over 3 multiplied by the natural log of 4. Finally, part D. The average value of a function f on the unbounded interval from a to infinity is defined to be this limit. Show that the improper integral of g of x from 4 to infinity is divergent, but the average value, as just defined on the interval from 4 to infinity, is finite. Alright, so we must begin with this improper integral and show that it's divergent, the integral from 4 to infinity of g of x. So let's get into that. G of x, of course, is just 1 over the square root of x, and we already integrated this function in part A. So this is going to be the limit as b goes to infinity of the integral of 1 over root x, which we know from part A is just 2x to the 1/2. The 1/3 was not part of g of x. That was just because it was an average value calculation. So the integral of g of x is just 2x to the 1/2. So we are going to have 2x to the 1/2, or just 2 root x. And this is going from 4 to b, and b is going to infinity. All right, so this is equal to the limit as b goes to infinity of 2 multiplied by the square root of b, minus, plugging in the lower bound of 4, that's just going to be 2 times the square root of 4, which is 2 times 2, which is 4. And clearly this limit diverges because the limit of 2 times the square root of b as b goes to infinity is just positive infinity. So indeed this is divergent. Now the other part of part D is to show that the average value of g on the interval from 4 to infinity is finite. So now we've got to look at this limit. So using the definition the problem gave us, this is the limit representing the average value of the function on the unbounded interval from 4 to infinity. All right, so as we proceed with this, in the numerator, we have the integral of 1 over the square root of x, and we already know what that is. That's 2 times the square root of x. And in the denominator, of course, we just have b minus 4. So this will be the limit as b goes to infinity of, in the numerator, we have the integral, which is 2 root x from 4 to b. So that's 2 root b minus 2 root 4, which is 4. In the denominator, of course, we have b minus 4. And indeed, this is finite. In fact, this limit is equal to 0, because in the numerator, we have a root b, whereas in the denominator, we have plain old b. B grows much more quickly than root b. Its power is 1, which is greater than b's power of 1/2 in the numerator. So that's how we know this converges to 0. Again, if you wanted to rewrite this to put that focus on the powers, it's 2b to the 1/2, whereas we have b to the 1 in the denominator. So this is going to outpace this. The limit is 0. And that completes our solution to free response problem 5 from the 2004 AP Calc BC Form B exam. This is free response question 5 from the 2017 AP Calc BC exam. Let f be the function defined by f of x equals this big fraction. Part A asks us to find the slope of the line that's tangent to the graph of f at x equals 3. To do this, we'll just take the derivative of f using the chain rule and then plug in x equals 3. You could use the quotient rule, but I would say that is a little bit overkill here, because f of x we can rewrite with a negative power. F of x equals 3 multiplied by, in parentheses, 2x squared minus 7x plus 5 to the power of negative 1, at which point it's clear how we can take the derivative using the chain rule and the power rule. So the derivative, f prime of x, will be, bring the exponent down, and that will get multiplied by 3, so negative 3. And then don't change the inside function, so I'll just go ahead and duplicate this inside function. And we have to reduce the power by 1. Again, we're applying the power rule here. So now the power is negative 2. But we also have to multiply by the derivative of the inside function, which is just more power rule. 4x minus 7, there is our derivative. Now to finish our answer for part A, we just have to plug in x equals 3. So this will become negative 3 multiplied by 2 times 9 minus 21 plus 5 to the power of negative 2 multiplied by 12 minus 7. All right, now we just have to clean this expression up a little bit. The part with a negative 2 power, let's put that in the denominator. So we have 2 times 9, which is 18, minus 21 is negative 3, plus 5 is positive 2. So this is 2 to the power of positive 2. The power is positive because we moved it to the denominator. In the numerator, we have negative 3 still. And then 12 minus 7 is 5. So negative 3 times 5 over 2 squared. This is negative 15 over 4. Because this is the value of the derivative at x equals 3, this is the slope of the line tangent to the graph of f at x equals 3. Moving on to part B. We are asked to find the x-coordinate of each critical point of f in the interval from 1 to 2.5. Then classify each critical point as the location of a relative minimum, a relative maximum, or neither, and justify our answers. Now, we already found the derivative of f, which is certainly useful for critical points. We must ask, where does the derivative not exist, and where does the derivative equal 0? Here is our derivative that we can use to find critical points. First, we might ask about points where this doesn't exist. This derivative won't exist where this quadratic is equal to 0, because due to the negative power, this is actually in the denominator, so it can't be equal to 0. Now, the problem gives us endpoints, right? We're looking in the interval from 1 to 2.5, not including those endpoints. So we might check these endpoints by plugging them into the derivative. and seeing if the derivative exists at those endpoints. It turns out those endpoints are exactly where this derivative does not exist. If you plug in 1 or if you plug in 2.5, you will get 0 for this quadratic, and thus the derivative does not exist at those endpoints. But since those endpoints aren't in the interval, we just have to set our derivative equal to 0 to find the critical points. To set this derivative equal to 0, well, like we said, this part with the negative power will be in the denominator. So we just need the numerator, which is negative 3 times 4x minus 7, to be 0. Negative 3 times 4x minus 7 needs to be 0. Of course, we could just divide both sides by negative 3 to just get rid of the negative 3. Then we have 4x minus 7 equals 0. Adding 7 to both sides and dividing by 4, we have that x equals 7 over 4 as our only critical point. So this is a critical point. Then is it the location of a maximum or a minimum, or is it neither? To answer that question, we must ask if the derivative changes sign, and if so, how, at x equals 7 over 4. Turns out the derivative does change sign at x equals 7 over 4, because this part with the negative power is just a square in the denominator, so that's always going to be positive. That's not going to affect the sign. But 4x minus 7 does change signs at x equals 7/4. When x is less than 7 over 4, 4x minus 7 will be negative, and so the derivative will be positive because it will have this negative and this negative. But once x exceeds 7 over 4, this term is going to be positive, and so the derivative, because of the negative 3, will be negative. So at x equals 7 over 4, the derivative goes from positive, so the function is increasing, to negative, so the function is decreasing. And thus, at x equals 7 over 4, we have a relative maximum. And there, our logic is written out. The only critical point in this interval has an x-coordinate of 7 over 4. We set the derivative equal to 0 to find that. The points where the derivative does not exist are the endpoints of the interval, which aren't included. Since f prime changes sign from positive to negative at 7 over 4, we know that f has a relative maximum at x equals 7 over 4. Moving on to part C. Using the identity that 3 over this equals this difference, evaluate the integral of f of x from 5 to infinity, or show that the integral diverges. So here, the expression, this nasty expression, has been decomposed for us into these two partial fractions. These two fractions make up this one fraction. We've decomposed the fraction into parts. It is, of course, not generally easy to integrate rational expressions with quadratics in the denominator, so having it split up into a difference of fractions with linear polynomials in the denominators, this makes it a lot easier. We'll be able to integrate this because these will just be simple natural log functions, and then we'll have to see if those limits exist or not. Of course, this is an improper integral, so we'll be looking at limits as a variable goes to infinity. Getting started with this integral, we want the integral of this rational expression from 5 to infinity, which is equal to the integral of this difference of fractions, because we were given that this is equal to this. Now, by definition, this improper integral is going to equal the limit as b goes to infinity of the integral of this same difference of fractions from 5 to b. So now let's go ahead and integrate and then evaluate our limit. We have the limit as b goes to infinity, and then actually performing the integral, we are going to get some natural logs. So 2 over 2x minus 5, the integral of this is going to be the natural log of 2x minus 5. By the chain rule, if we were to take the derivative of this function, the factor of 2 would pop out in front, just like we want, because there's a 2 in the numerator. As for 1 over x minus 1, this is just going to be ln of x minus 1. So there's our integral. This is being evaluated from 5 to b. I've copied the limit over here on the left, so we have a little bit more room to work with. Let's rewrite the limit statement, the limit as b approaches infinity. And then before we do any evaluation, let's just simplify this expression. The natural log of 2x minus 5 minus the natural log of x minus 1, by our log rules, we can write that as the natural log of the quotient of these two things. So 2x minus 5 divided by x minus 1, just using log rules here. And we are evaluating this from 5 to b. Now, when we think about what happens as we plug in b and let b go to infinity here, inside the natural log, we have the ratio of two polynomials of the same degree, 2x minus 5 and x minus 1. They both have degree 1. So the limit of this rational function as b goes to infinity, when we plug in b, is going to be the ratio of the leading coefficients. It's just going to be 2 divided by 1. So if we plug in b and then take the limit as b goes to infinity, this is just going to be the natural log of 2 over 1, so the natural log of 2. And then if we plug in 5, we're going to have 10 minus 5 in the numerator, which is 5, divided by 4 in the denominator, so minus the natural log of 5 over 4. Doing some final simplification here with our log properties, this is equal to the natural log of 2 divided by 5 over 4. But dividing by a fraction is the same as multiplying by its reciprocal. So 2 divided by 5 over 4 is 2 times 4 over 5. So our final answer is the natural log of 8 over 5. The integral does converge, and it converges to the natural log of 8/5. At this point, I'm going to have to go ahead and shrink our work so we can read part D and actually have some room to write our answer. All right, part D. Determine whether the infinite series, as shown here, converges or diverges. State the conditions of the test used for determining convergence or divergence. Since we just did an integral, the integral test seems like a pretty good choice here. We integrated this exact function, right? Look at that. Now, in order to say that this series from n equals 5 to infinity converges, just because the corresponding integral from 5 to infinity converges, we just need to check a few conditions. The function needs to be continuous, positive, and decreasing on the interval in question, which is from 5 to infinity. So we're looking at this function. Is it continuous, positive, and decreasing on the interval in question? Well, it's definitely continuous because there would only be an issue if the denominator were to equal 0. But we already checked that its zeros were at these endpoints from part A, 1 and 2.5. The interval we are worried about now is from 5 to infinity, so those zeros are not part of this, so certainly the function is continuous. Now, is it positive? Well, the numerator is positive, so the only thing that could make it negative would be the denominator. But we know that this denominator, this quadratic, is an upwards-facing parabola, and we know that at x equals 5, we are well past the second zero of the parabola, because the second zero, like we said, occurs at x equals 2.5. So at x equals 5, and all subsequent x's, yes, this is going to be positive. The parabola just keeps going up. And since this denominator just keeps increasing on the interval in question, the polynomial itself is decreasing because it's 3 divided by an increasing denominator. We could also take the derivative of the denominator, in which case we would see that we get 4x minus 7, which is certainly positive when x is at least 5. Which it is on the interval in question. Suffice to say, we can apply the integral test. Since our function is continuous, positive, and decreasing from 5 to infinity, it must be that the integral we calculated in the previous part has the convergent behavior which matches up with our series. Our series must converge because this integral converges. And that completes our solution to free response question 5 from the 2017 AP Calc BC exam. Next are problems on the Lagrange error bound. For these problems, it is useful to know the formula for the Lagrange error bound. Also, in both of these problems, I will write the word Lagrange and accidentally write the second G as a C, so please forgive me. This is free response question 2 from the 2004 AP Calc BC exam. It is part of the graphing calculator section, but we won't actually need one for this problem.
Let f be a function having derivatives of all orders for all real numbers. The third degree Taylor polynomial for f about x equals 2 is given here. Part A asks us to find f of 2 and f double prime of 2. Because this is a Taylor polynomial for f centered at x equals 2, it will match the function's value exactly at x equals 2. So to find f of 2 for part A, all we have to do is plug 2 into the Taylor polynomial. F of 2 will equal t of 2. And if we plug 2 into this function t of x, we see these two terms will zero out, and we're just left with the initial term of 7. So f of 2 equals 7. Now for the second derivative of our function evaluated at 2, all we have to do is look at our Taylor polynomial and recall how Taylor series are constructed. In general, the nth term of a Taylor series looks like this: the nth derivative of the function evaluated at the center divided by n factorial multiplied by x minus the center to the power of n. So we can find information about the second derivative of our function here, where the power of x minus 2 is 2. So in fact, looking at this term, the second derivative of the function evaluated at 2 divided by 2 factorial must be negative 9. Again, the second derivative of the function evaluated at 2 divided by 2 factorial must equal negative 9. That's just how these polynomials are constructed. Okay, so then all we have to do is solve for f double prime of 2 by multiplying both sides by 2 factorial. 2 factorial is just 2, and so we have the second derivative of f evaluated at 2 equals negative 18. Moving on then to part B. Is there enough information given to determine whether f has a critical point at x equals 2? If not, explain why not. If so, determine whether f of 2 is a relative maximum, a relative minimum, or neither, and justify your answer. We certainly can determine if f has a critical point or not, because the Taylor polynomial, this third degree Taylor polynomial, does give us exact information about the first derivative of the function at x equals 2. So we just have to ask, is the first derivative of the function equal to 0 at x equals 2? Based on how Taylor polynomials are constructed, we know that the first derivative of our function at the center, x equals 2, will have to equal the derivative of the Taylor polynomial at x equals 2. They are created so that their derivatives match the derivatives of the function at the center. So all we have to do is look at t of x, take its derivative, and plug in x equals 2. And then we can see if it's 0. If so, it's a critical point. So coming up to the Taylor polynomial and taking the derivative to get t prime, the derivative of 7 is 0, and then the derivative of negative 9 times x minus 2 squared is negative 18 times x minus 2, and then the derivative of negative 3 times x minus 2 cubed is negative 9 times x minus 2 squared. You can see how if we took a second derivative, we would get negative 18 if we were to plug in x equals 2, which of course agrees with our answer from part A. But right now we are interested in the first derivative. What happens if we plug 2 into this first derivative? We actually get 0, right? 2 minus 2, 2 minus 2, we would get 0. So yeah, this is the location of a critical point. Now, is it a maximum or a minimum or neither? Well, it turns out it must be a maximum, because we already know the second derivative of the function at the center of 2 is negative, which means the function is concave down, and so this critical point is the location of a maximum. And there is our reasoning written out. F does have a critical point at x equals 2, and f of 2 is a relative maximum, because f prime of 2 equals 0, and f double prime of 2 is negative. So concave down means we've got a maximum. On to part C. Use t of x to find an approximation for f of 0. Is there enough information given to determine whether f has a critical point at x equals 0? And if not, and if so, let's just answer the problem. All right, to find an approximation for f of 0, all we have to do is plug 0 into the Taylor polynomial. It won't be a great approximation probably, because 0 isn't super close to the center of 2, but should be an alright approximation. So for part C, we are trying to approximate f of 0, and it should be
about t of 0. At least that's the best approximation we can come up with. Plugging in x equals 0 to this polynomial will give us what? I'll jot it down here and then move it down to where we are writing part C. This is going to be 7 minus 9 multiplied by negative 2 squared minus 3 multiplied by negative 2 cubed. And this is equal to 7 minus 2 squared is plus 4 times minus 9 is minus 36. Minus 2 cubed is minus 8. Times minus 3 is plus 24. And this adds up to negative 5. So that is our approximation for f of 0. As far as whether or not we can determine if there is a critical point at x equals 0, the answer is no, because our Taylor polynomial is centered at x equals 2, and thus only gives us exact values for the function at that center of x equals 2. And here that is written out. T of x gives exact information only at the center x equals 2, so we can't determine if we've got a critical point at x equals 0. Part D. The fourth derivative of f satisfies this inequality, that its magnitude is less than or equal to 6 for all x in the closed interval from 0 to 2. Notice that closed interval goes from 0, the number we were just discussing, to 2, the center of our Taylor polynomial. Use the Lagrange error bound on the approximation to f of 0, which we found in part C, to explain why f of 0 is negative. So the approximation we got was negative 5. We want to use the Lagrange error bound to show that the true value has to be negative. First, let's calculate the Lagrange error bound. This is the formula for the Lagrange error bound. We have x, which is the point of our approximation, which in this case is 0, minus c, the center, in an absolute value to the power of n plus 1, where n is the degree of the Taylor polynomial. For us, n equals 3. Then divide by n plus 1 factorial and multiply by the maximum value that the absolute value of the n plus 1th derivative of the function takes on in the interval from the point of approximation to the center of the Taylor polynomial. So this means that z is in the interval from 0 to 2, because our approximation is at x equals 0, and the center of our Taylor polynomial is at 2. So the maximum absolute value that the n plus 1th derivative of the function takes on in this interval, that's what this is. And we're told that the n plus 1th derivative, in our case the fourth derivative of the function, has an absolute value that's bounded above by 6 on this interval. We don't necessarily know if 6 is actually its maximum value, but we do know it's less than or equal to 6 on this whole interval. So plugging in all of our pieces, we get that this error bound is less than or equal to the absolute value of 0 minus 2 to the power of 4 divided by 4 factorial, times 6, because this maximum value is no more than 6. And do the math here, you will get 4 as the Lagrange error bound. This means our approximation from part C could be off by no more than 4 from the true value. 4 more than negative 5 is negative 1, which is still negative. So for sure, the true value must be negative. That's the conclusion written out. F of 0 must be less than or equal to the Taylor approximation at x equals 0, plus 4, because 4 is an upper bound for the error. And that's equal to negative 1, so f of 0 has got to be negative. And that will complete our solution to free response question 2 from the 2004 AP Calc BC exam. This is free response question 6 from the 2011 AP Calc BC exam. Let f of x equal sine of x squared plus cosine x. The graph of y equals the absolute value of the fifth derivative of f is shown above. Very nice derivative function there. Part A says write the first 4 non-zero terms of the Taylor series for sine x about x equals 0, and write the first 4 non-zero terms of the Taylor series for sine of x squared about x equals 0. So if we know the Taylor series for sine x, all we'll have to do is replace the x with x squared for this second part. Now, ideally, you have the Taylor series for sine x memorized, but if not, it's not a huge deal as long as you recall the general form of a Taylor series. In general, the nth term of a Taylor series is the nth derivative of the function evaluated at the center, which we call a, divided by n factorial multiplied by x minus a to the power of n. So if you don't remember the Taylor series for sine x, we can just construct it as long as we remember this general form. Now, before we start writing out terms of the Taylor series for sine x, let's think about what the derivative of sine x will look like when we plug in 0. First, before we take any derivative, so for n equals 0, when we plug in our center of 0, we would get 0. Then when we take the first derivative for the n equals 1 term of the Taylor series, we would have cosine of 0, which is 1. Then when we take the second derivative for the n equals 2 term, we would again get 0. Then when we take the third derivative for the n equals 3 term, we would get negative 1. So what's going to happen with the Taylor series for sine is that we'll only get odd terms when n equals 1, when n equals 3, when n equals 5, and so on, because the even derivative values are just sine functions evaluated at 0, which are 0. And also the sine, as in positive negative sign, the sign, positive or negative, of the odd terms that appear in the series will alternate. Positive, negative. The next one will be positive, and then negative, and so on. And that is enough for us to start writing the Taylor series for sine x. Sine x equals, when n equals 0, we're just going to get 0, so that first term will not show up. When n equals 1, the derivative will evaluate to 1 because we're plugging in 0, and then we'll just have to divide by 1 factorial. 1 factorial is just 1, so we don't really have to write the division at all. And so we're just left with x minus the center of 0 to the power of 1. But there's no need to write minus 0, so we will just write it as x to the power of 1. Then the n equals 2 term will again just be 0, so we don't have to write it. For the n equals 3 term, the third derivative with 0 plugged in will be negative 1, so we have a minus. And then we have to divide by 3 factorial, and we're going to have x minus 0, which is just x to the power of 3. So x cubed over 3 factorial. And this pattern continues. We will then have plus x to the 5 divided by 5 factorial, and so on. We are asked in part A to write the first 4 non-zero terms, so we'll want to write one more, minus x to the 7 divided by 7 factorial, and plus dot dot dot. Now, the second part of part A asks us to write the first 4 non-zero terms of the Taylor series for sine of x squared about x equals 0. So what we'll have to do for sine of x squared is just use the Taylor series that we just found, but replace each x with x squared. So the first term just becomes x squared, then x squared cubed is x to the 6th, and we are dividing by 3 factorial. This is a bit of a squeeze, so let me move this down so we have a little bit more room. Again, it's just like we're plugging x squared into the Taylor series we found before. So in the next term, we had x to the 5, but now we're replacing x with x squared. So we have x squared to the 5, which is x to the 10, divided by 5 factorial. And then the last term we'll have to write, because we need to write 4 of them, is x squared to the power of 7, which is x to the 14, divided by 7 factorial, plus dot dot dot. All right, so there's our answer for part A. Moving on to part B. Write the first 4 non-zero terms of the Taylor series for cosine x about x equals 0, and then use this series and the series for sine of x squared, which we just found, to write the first 4 non-zero terms of the Taylor series for f, because remember f is sine of x squared plus cosine, about x equals 0. All right, if you didn't remember the Taylor series for cosine, there's a good chance that finding the Taylor series for sine would jog your memory. the Taylor series for cosine is just like the Taylor series for sine, except with the even powers rather than the odd ones. That's because the 0th derivative of cosine, which is just cosine, when we plug 0 into that, we get 1. So we do have an n equals 0 term. Then when we take the first derivative, so n equals 1, this is when we get sine, and thus we get 0. But then when n equals 2, we take the second derivative, we get negative cosine, and this is going to be negative 1 when we plug in 0. So still these signs are alternating, but this time we are going to have the even n terms rather than the odd n terms. So cosine x has the following Taylor series: x to the 0, which is just 1, and then minus x squared divided by 2 factorial, plus x to the 4 divided by 4 factorial, minus x to the 6 divided by 6 factorial, and so on. Next, part B also asked us to write the first 4 non-zero terms of the Taylor series for that function f, sine of x squared plus cosine. So this Taylor series plus this one. We'll want to combine like terms and write the resulting first 4 non-zero terms. So there will be a 1, and then we'll have to combine the x squared terms. Then we'll have the x to the 4 term, and then we'll have to combine the x to the 6 terms. And we can write that here. So f of x equals 1, the first term, and then x squared minus what is actually just half x squared. X squared minus half x squared is just plus x squared over 2. And then we'll have plus x to the 4 over 4 factorial, and then minus x to the 6 over 3 factorial, minus x to the 6 over 6 factorial. To make the denominator 3 factorial match the denominator of 6 factorial, we would have to multiply by 6, by 5, by 4 on the top and on the bottom. 6 times 5 is 30, times 4 is 120. So this would be minus 120 x to the 6th over 6 factorial if we were to get common denominators. So then in total, we will have minus 121 x to the 6th over 6 factorial. So getting common denominators and combining the x to the 6's, we have minus 121 x to the 6th over 6 factorial. Again, that's because we'd have to multiply x to the 6 over 3 factorial by 120 over 120 to make those denominators match up, and then this is what we get once we combine. And then we can just write plus ... We do know that the next term will be positive because the next term is going to be x to the 8 over 8 factorial from the cosine x Taylor series, because the sine of x squared Taylor series does not have an x to the 8 term. At a glance, that might seem... Now part C asks us to find the value of the 6th derivative of this function f evaluated at 0. That might seem kind of intimidating at first, but then recall all these Taylor series we've been doing, they have information about the derivatives. We know that the 6th derivative of this function is going to be divided by n factorial, or 6 factorial, in the n equals 6 term of the Taylor series of this function. Now, if we look down at the Taylor series that we wrote in part B, we see that the n equals 6 term is right here, and the coefficient of x is negative 121 over 6 factorial. Just based on how Taylor series are constructed, this numerator, negative 121, must be the value of the 6th derivative of f at 0. Plain and simple. It's got to be negative 121. Finally, part D says, let P4 of x be the 4th degree Taylor polynomial for f about x equals 0, which is what we just found without the ellipses. Then, using information from the graph of y equals the absolute value of the 5th derivative of f of x, which is shown above, we have that picture here, show that the absolute value of P4 of 1/4 minus the true value f of 1/4 is less than 1 over 3,000. So this here, you should look at that and recognize as the error of the fourth degree Taylor polynomial approximation of the function at 1/4. The Taylor polynomial is centered at x equals 0, so when we plug in other values, we're going to get some error. This is the error, and we want to show that it's less than 1/3000. We'll do this using the Lagrange error bound. Here is the Lagrange error bound. It's the absolute value of x minus the center c, where x is the point we're evaluating at or approximating at. In our case, it's 1/4. To the power of n plus 1, where n is the degree of the Taylor polynomial being used, in our case it's 4, divided by n plus 1 factorial, multiplied by the maximum of the absolute value of the n plus 1th derivative of the function over the interval from the point of approximation to the center. So I could say that z here is an element of the interval from 0, which is the center of our Taylor polynomial, to 1/4, which is the point of our approximation. So the maximum value that the absolute value of the n plus 1th derivative of the function f takes on in this space, that's what this is, and that's the error bound. All right, so let's start to plug in some pieces. X in our case is 1/4, and c, the center of our Taylor polynomial, is 0. So this numerator is going to be the absolute value of 1/4, which is just 1/4, to the power of n plus 1. Again, n is the degree of the Taylor polynomial, which in our case is 4. 1, 2, 3, 4. We're not using any of the other terms. So this is going to be raised to the power of 4 plus 1, which is 5, divided by 4 plus 1 factorial, so 5 factorial. Then all that remains is to put at least an upper bound on the maximum of the absolute value of the fifth derivative of the function over the relevant interval. And for that, we can use the picture. This is a graph of the absolute value of the fifth derivative of the function. Now, the interval we're interested in goes from 0, the center of our Taylor polynomial, to 1/4. And you can see that 1/4 is right here. 1/4, 2/4, 3/4, 1. Very convenient graph. So this is the interval in question, and we can see over this entire interval, the derivative is, the absolute value of the fifth derivative is less than 40. That's a very convenient upper bound. So coming down to our Lagrange error bound, we can replace this with 40. The maximum of the absolute value of the fifth derivative of our function over this interval is certainly less than 40, so this is a valid upper bound for the error. All right, now all that's left is to evaluate this. 1/4 to the power of 5, what is that? Well, 4 squared is 16, so 4 cubed is 64, so 4 to the power of 4 is 256, so 4 to the power of 5 is 1024. So this is 1 over 1024. Now, the 40 can be canceled out by some pieces of 5 factorial. 5 factorial contains 5 times 4 times 2, and that is 40, so we could cancel those out. That would leave in the denominator 3, and, well, that's it, so let's just put it there. And look at that. This simplifies to 1 over 3072, 1 over 3072, and 1 over 3072 is less than 1 over 3000. And thus we've shown that the error in our fourth degree Taylor approximation for the value of the function at 1/4, that error is less than 1 over 3000, which is exactly what we set out to prove. And that will complete our solution to free response question 6 from the 2011 AP Calc BC exam. Finally, we will do a couple of problems on arc length. Recall that the formula for the arc length of a function f of x from a to b is the integral from a to b of the square root of 1 plus the derivative of f squared. That's the derivative squared plus 1 in the square root. Good luck. This is free response question 4 from the 2008 AP Calc BC Form B exam. Let f be the function given by f of x equals kx squared minus x cubed, where k is a positive constant. Let R be the region in the first quadrant bounded by the graph of f and the x-axis. Part A asks us to find all values of the constant k for which the area of R equals 2. Now, we are specifically interested in the first quadrant, which allows us to put some restrictions on x and k. Firstly, if we're in the first quadrant, of course, x has to be at least 0. But if we're in the first quadrant, we need y, or f of x, to also be at least 0. Now, that means that kx squared minus x cubed, which can be factored as x squared times k minus x, that has to be at least 0, and thus k has to be at least x. Otherwise, this term would force this to be negative. We need it to be non-negative, so k has to be at least x, and we know x has to be at least 0 because we want this region to be in the first quadrant. With that in mind, we can integrate this function from 0 to k to get the total area in the region, because it is precisely when x equals k that the function will leave the first quadrant, becoming negative. So our region R would look something like this, going from 0 to x equals k. So we'll just integrate from 0 to k, and then we can set that equal to 2 and solve for all possible values of the constant k. So we are integrating from 0 to k. What we're integrating is this function, which is easier integrated, not in factored form. So kx squared minus x cubed. And we are integrating this, of course, with respect to x. So we'll just go ahead and use the power rule here. That's going to give us k over 3 x cubed minus 1/4 x to the 4. We are evaluating this from 0 to k. When we plug in the lower bound of 0, everything's just going to go away. So all that's left when we evaluate this is k over 3 times k cubed, which is just k to the 4 over 3, and then minus 1/4 k to the 4. So in total, once we get common denominators, this is going to be 4k to the 4 over 12 minus 3k to the 4 over 12, which is just going to be k to the 4 over 12. We need this to equal 2 because we want the area of the region to equal 2, which then forces k to be the fourth root of 24. If we took the negative of this and then raised that to the fourth power, we would also get positive 24. However, we were told that k needs to be a positive constant, and of course we also know that k is positive because we are in the first quadrant. Thus, k equals the fourth root of 24 is the only possibility. That was part A. Moving on then to part B. For k greater than 0, write but do not evaluate an integral expression in terms of k for the volume of the solid generated when the region R, which we were just discussing, is rotated about the x-axis. So this will be pretty easy because it's just using this region from the previous part of the problem, and we are revolving it about the x-axis. So we would have some shape looking something like this. All the cross-sections are circles, where the radius of each circle is just the height of the function at the x-coordinate in question. Thus, the volume of this solid will just be the integral from 0 to k of the cross-sectional areas, pi r squared. Like we said, the radius of each cross-section, each circle, is just going to be the value of the function. So kx squared minus x cubed squared, because we have to square the radius. And we're integrating with respect to x. That's it. That's the volume. Finally, on to part C. Part C says, for k greater than 0, write but do not evaluate an expression in terms of k involving one or more integrals that gives the perimeter of R. So coming back to our silly little sketch here, let's erase the blue part because that's not relevant anymore. We are looking for the perimeter of this region R. So it would be easy to just say, let's write the integral for the length of this arc from here to here, but we don't want to forget about this part of the region. This part has a length of k because it just goes from 0 to k. And then this part on the top, we'll just have to use an integral for that. So the perimeter, which we might write as P, will be K, the bottom of the region R, plus, hopefully you remember the arc length formula. We need to integrate from 0 to K, and then what we're integrating is the square root of 1 plus the derivative of the function squared. So let's just go ahead and find the derivative of the function, and that's what we will plug in there. We have the function written here, so let's just take the derivative of that. So d dx of kx squared minus x cubed. We'll just use the power rule. That's going to be 2k times x minus 3x squared. And let's see if we can squeeze that into the parentheses. And that's it. That's an integral expression for the perimeter of the region R. Again, the arc length formula has us integrating across whatever the relevant bounds are, in this case from 0 to k. And the integrand is the square root of 1 plus the derivative of the function squared. That is all in a square root, just to make sure that's clear. And that's it. That will complete our solution to free response question 4 from the 2008 AP Calc Form B BC exam. This is free response question 4 from the 2011 AP Calc BC Form B exam, and it is a pretty big looking problem. Let's take a look. The graph of the differentiable function y equals f of x with domain from 0 to 10 inclusive is shown in the figure above. This is a graph of f. The area of the region enclosed between the graph of f and the x-axis for x between 0 and 5, we can see that's this region here. That area is 10. So I'm just going to jot that down. And the area of the region enclosed between the graph of f and the x-axis from 5 to 10, that's all this space here, is 27. I'll go ahead and write that as well. The arc length for the portion of the graph of f between x equals 0 and x equals 5, this part here, is 11. So I'm going to go ahead and jot that down as well. I'll just put a little green arc that has a length of 11. And then it also tells us the arc length for the portion of the graph between x equals 5 and x equals 10 is 18. I will draw that in red. So from x equals 5 to x equals 10, that arc length is 18. The function f has exactly 2 critical points that are located at x equals 3, right there, and x equals 8, which we see right there. Part A asks us to find the average value of f on the interval from 0 to 5. So the average value of our function f over this interval. We see that average value should certainly be negative. Let's take an integral and calculate it. So for part A, the average value of a function is found by just integrating that function, so the integral of f of x, over the relevant interval. In this case, that's from 0 to 5, and then dividing by the interval width. The width of this interval is 5, so divide by 5, or multiply by 1/5. So this will be 1/5 multiplied by the integral of f of x from 0 to 5 is the area under the curve, which was given to us as 10, although we can see that's underneath the x-axis, so that area should actually be represented as negative 10. So our final answer is negative 2. That is the average value of the function over the interval in question. Part B says, evaluate the integral from 0 to 10 of 3f of x plus 2. Show the computations that lead to your answer. This is pretty straightforward. We're just going to have to use some basic integral properties. The first thing that we can do with this integral of a sum is split it up into a sum of integrals. So this is the same as the integral from 0 to 10 of 3f of x, although we can take the 3 out of this, so we might as well. 3 times the integral of f of x from 0 to 10 dx. And then separately, we can add the integral of 2 from 0 to 10. Then this will be 3 multiplied by the area underneath f of x from 0 to 10. And we can split that up into 2 integrals because we understand there is a bit of negative area from 0 to 5. But then from 5 to 10, we have positive area. So let's split that up into these 2 integrals because we know the values of these individual integrals. So we've got that. And then the integral of 2 from 0 to 10, that's just a 2 by 10 rectangle. So that's just plus 20. So then this will be 3 multiplied by the area under the curve from 0 to 5, we already know is negative 10. And we were told the area under the curve from 5 to 10 is 27. And we know that is positive. So this would be plus 27. And we still have plus 20 at the end. Negative 10 plus 27 is 17, times 3 is 51, and 51 plus 20 is 71. So 71 is the final answer. All right, let's move on then to part C. Let g of x equal the integral from 5 to x of f of t dt. We are asked on what intervals, if any, is the graph of g both concave up and decreasing, and we must explain our reasoning. Now, g being concave up means that the value of its derivative is increasing. And it being decreasing means that the value of its derivative is negative. Now, that's useful because the derivative of g of x, by the fundamental theorem of calculus, the derivative of g of x is just our function f of x, which we have a graph of. So we're looking for where f of x is negative and increasing. We want it to be negative because that means that g is decreasing, and we want f to be increasing because f is the derivative of g. So if f is increasing, g is concave up. So here's this information summarized. We need g prime to be negative and increasing. But remember, g prime is just f of x, which we have a graph of. So let's see, where is g prime, which is f, negative? Well, it is negative from 0 to 5. So g prime is negative on the interval from 0 to 5. Then where is g prime increasing? Again, g prime is f, so let's look at the graph of f. We can see that g prime is increasing from here, this critical point at x equals 3, to here, this critical point at x equals 8. So it is increasing on this interval from 3 to 8. So it's going to be the intersection of these intervals, which is from 3 to 5. That's the intersection of these intervals where the necessary requirements are both met. So g would be decreasing and concave up. And there is our conclusion. G is decreasing and concave up when x is between 3 and 5. Finally, part D. The function h is defined by h of x equals 2f of x over 2. The derivative of h is, it's easy to find using the chain rule, but it just gives it to us, f prime of x over 2, because you would take the derivative of f and then multiply by the derivative of the inside function. The 1/2 would cancel out the 2. We're asked to find the arc length of the graph of y equals h of x from x equals 0 to x equals 20. Notice that h is based on our function f, which is defined from 0 to 20, but the input of f in h's definition is cut in half, which is why h can go from 0 to 20. When we plug in x equals 20, f is going to receive an input of 10, which is right at the end of its domain. I suppose we are going to have to shrink our work for the previous parts of this problem in order to fit the final part. So I will start writing part D over here. We are concerned with arc length from 0 to 20. So that's going to be the integral from 0 to 20. And we're finding the arc length of h of x. So the way we find arc length of a function is we are integrating the square root of 1 plus the function's derivative squared. Now, we know the derivative of h. It's just f prime of x over 2. So this is 1 plus f prime of x over 2 squared. Now, since we have an inside function, x over 2, this is a good time to bust out some u substitution. If u equals x over 2, then du equals 1/2 dx. And then we can say that dx is equal to 2 du. So then we can replace dx with 2 du and write everything else here in terms of u. we'll also be changing our bounds. If x starts at 0, then u also starts at 0. If x ends at 20, then u ends at 10. So this is equal to the integral from 0 to 10, now that we have bounds in terms of u, and we are integrating 1 plus f prime of x over 2, which is u, squared. And we're integrating with respect to u, but we also need that factor of 2. Let's just put that in front of the integral. And now we are basically done because we have written this integral, so it's actually just an arc length of f now, from 0 to 10. We already know what the arc length of f is from 0 to 10 because we have information about these two pieces. We know that the arc length from 0 to 5 is 11, and we know that the arc length from 5 to 10 is 18. So coming back down to this integral, which is now just the arc length of f from 0 to 10, it's going to be 11 plus 18, the arc length from 0 to 5, plus the arc length from 5 to 10. 11 plus 18 is 29, times 2 is 58. All right, there we go. That completes our solution to free response question 4 from the 2011 AP Calc BC Form B exam. Well, that was fun. Once again, I'd like to thank you for watching and encourage you to donate if you found this video helpful and would like to help me continue producing educational content. You can join Wrath of Math as a channel member for early and exclusive access to select videos, or donate on Patreon or PayPal. There are links in the description. You can also just share the video. That would be a huge help. It took an immense amount of work, and I hope it was useful for you. Thanks for watching.